Oh hey, what's up everybody? So for those of you who do not know me, my name is Caleb from Caleb the Video Maker 2 and CalebCareer.com. So I did a design series a while ago. It was my first video series here on YouTube. It was about 25 videos long, and then I went on to make a 67-part video series over MySQL, and I did a couple other ones. I have over 100 databasing videos, and I wanted to try to tackle this again to try to make it better, explain things better, and also bring you to a new level of skill. So what level of difficulty is this course going to be? It's going to be for beginners. So why do you want to use the series? Most platforms, programs, applications rely on a back-end database. That's how we store information in this world. Everything we do is powered by a database. So it's important that you know how to properly implement database concepts, designs, to know how to properly structure data. So that way you get the best optimized database. That will set you apart from the rest of the IT team or the rest of your classmates. It will give you the skills needed to get that job or whatever you want to do with it. Also, if you're just a business person or you have your own project and you need to learn how to build a website, or you need a database to store all the information you're using, well, this series will be helpful. Basically, database design is the fundamentals of databases. You should know how to properly structure data. This series is not going to be very specific on a certain database management system. So this isn't like MySQL database design. This isn't like Oracle. This isn't SQL Server. This isn't whatever else you use. This is going to be general database design, so then you can take these skills and apply them to any of the databases that you are working on that are relational. Which, I mean, through this series you'll really understand what that means if you don't get that. So the first part is going to be a lot of the concepts on the chalkboard, and I'm not going to write tons of scripts on here, so don't worry, it's not going to be confusing to where you can't see the code on a screen. Because in reality, a lot of database design is not done on a computer first. First you have to think about it, and then you kind of just draw out your plans, whether it be in your head or on a document, or if you use a database design program. I use a chalkboard because I can easily draw out concepts, thoughts, the way data is connected, and all of that. So a lot of these databasing videos, they're going to be on this chalkboard because that's all you really need. We're not programming a database, we're designing a database. And designing is art. You draw it, you design it. So a lot of the concepts from this video will be useful no matter what you will be using for your database. So database design. Before we talk about database design, let's first talk about a database, because we can't design a database if we don't know what a database is. That doesn't even make sense. So what is a database? That's a really good question. I'm glad you asked. Well, I can actually tell you what a database is, and that's what this video is about. So, a database is something that stores data. Alright, another vague term. Data. And I want all of you to think about data very broadly. Don't think too specific. Think of data as anything we can store in a database, or anything we can write down, anything that has a value. It can be anything. Data can be the list of every single customer of your store since 1995, or it can be a list of every single transaction in an online shopping center, or it can be a list of every user and their username, or it could be a list of every single weather event since 1927. It can be pretty much anything. It doesn't have to do with specific people. Data is so broad. So database is obviously broad too, because a database stores data. So yeah, just think of it like this. Here we have a database. A base is where we store data. Pretty simple. Alright, so now that's pretty vague, and I'm not sure if that was very helpful. So now let's break it down to where we see it from a technical standpoint. everything in this world, not everything, but almost everything, is ran from a back-end database. It's what stores all of our information. So, for example, I like to use websites for examples because they're very clear and they're very easy to understand the concept of this. When you go to a website and you sign up, you give them a username, you give them a password, and you give them an email. All of that, when you sign in the next time, it allows you to sign in. Well, how did that website remember what your username, email, and password was? That's because all of this information that you put in when you registered, well, all of these values are given to a database. So here you can say is our database. Sorry for my craptastic handwriting, but don't even worry about it. This is what's said to be the front end. This is said to be the back end. That's because we don't necessarily see what's going on back here. We can put in our email, our username, and our password, and it can get stored in this database. That way, when we come back again and we log in, we give them a username and a password, it takes that value, it checks it with the database to allow you to get into the account. That is a perfect example of a database. So a database can store that information, but it's not limited to only registration. You can use this to store all of your records of sales in a store, and all so forth. It just goes on. Don't think of it as a limited thing, because there's so many things you can do with a database. So many things. Next question you may be asking is, how does it differ from like a spreadsheet, for example? So a spreadsheet, basically, if you don't really know much about spreadsheets, it's basically where you have columns, and then we have rows, and we can store information about, like we can enter the values for each column. Spreadsheets are good if that's what you need, if you're a very small company, excuse me. But if you want to get to any complexity where you can, like, imagine if we wanted to select, let's say this was a spreadsheet for all of my employees. I own a huge business with 100 employees, and I want to select every single employee who has missed less than 3 days and have been an employee for at least 3 years, and I want to give them a $100 bonus. Well, that's something, if I had a spreadsheet, I'd have to manually go through that, check every single value. That's not going to work, because time's money in business. But anyways, with a database, we can run queries to get those kind of values, to figure out which employees have been a employee for 3 years and have only missed 3 days or less. So that's how it differs from a spreadsheet, basically what you can do with it. If you have a spreadsheet with 10 employees, or with 10 values, and that's like you can figure out all of your information in a couple of seconds, well, then you might not need a database. That's up to you. The other thing is with spreadsheets, it's either like all data or no data. Let's say this stored every single detail about every single employee that I had, and all I wanted was their name and their address. Well, we can't really do that easily with a spreadsheet unless we take all those columns and like copy and paste and all this extra garbage, or find some algorithm to do things fancily. If you know what you're doing, you can probably do it. But with a database, we can selectively choose which columns. So we can say only these 2 columns do we want returned, and we can ignore the rest. On top of that, we can allow different users to access different information. Back to the website example, we had users page, and then we had a database. When here you put your username, email, and password. That's stored on a database, but that's not necessarily the only thing that's stored on a database. A user might only get to access that, but a database administrator might get to access when they registered, the transactions they've made on your shopping website, or what they've watched, what they've viewed, the comments they've made, how often they visit the web page. It's pretty much limitless to what you want to do with the database. So we can see that 2 different users. This person only gets to view some things of the database. This person can view pretty much anything. With a spreadsheet, it's kind of all or nothing. Do you have access to the spreadsheet? Yes, I do. Well, here it is. If you don't have access, well then too bad, you don't get any of it. So that's awesome. That's a security feature as well, because you don't want this person to get all of the hidden information that's stored within this database. So hopefully that makes things pretty darn clear. The next video I'll kind of be talking about how data is stored in a database, because I was going to get into that in this video, but I kind of ran out of time. But for the sake of just your understanding, if you decide not to watch the second video, which you will watch the second video, right? Relations, that's a term where we get the term relational database. So this series is for what's known as a relational database. That is a specific kind of database, and that's going to be most of the databases that you work with if you're working with database design. We're going to be talking about the relation, very basic, don't freak out, but it is math. We're not going to go super in-depth with math. If you want to know more about the math, I have blogs on my website about that. calebcurry.com/blogs. Advertising. Not blogs advertising, I was advertising. Anyways, basically a relation is just a connection between data. So let's just think of a silly example. If we had the two sets of numbers, 2, 4, and then the other set was 6, 8. And then we kind of combined these sets. So we kind of like crossed here, and then we crossed down here. And where these cross is our new set. So we have the combined set of 6, 2, and then we have the combined set of 6, 4, and then we have the combined set of 8, 2, and then the combined set of 8, 4. And like you're probably wondering, like, what the heck does that have to do with database design? Well, somewhat. We kind of do the same thing with database design. Relation in relational database comes from this mathematical concept. But rather than combining sets of numbers, we're combining attributes of real-world things. So let's apply this to the database. First, you need to know two terms. The first one is an entity. The second one is an attribute. So, an entity is anything we store data about. Attribute are the things that we store. So if an entity is a person, an attribute would be their name, their username, their password, their hair color, their address, their phone number, their relationship status, the person they're in a relationship with, the orders that they've made, or whatever it is. It just depends on what you need to store for that specific application. So entity is what we store the data about. Attribute is what we store. When we apply this to this connection with the relation, we have the attribute types and the attribute values. So let's say we have this person over here, and we'll name him Caleb because it's an awesome name. Alright? And then we will also give him a username, Caleb Curry, with no spaces. And we'll give him a password, pi123. And then over here, we have the set of attributes for a table. We have name, username, and password. We can make this connection of data. So the name is Caleb, the username, Caleb Curry, password is pi123. That makes sense, although graphically it looks like a mess. So we store these in tables, which is exactly what we were doing with the relations. So we have up here in our columns, we have the name, and then we have the username, and then the password. Don't worry if you can't read my handwriting, you get it. We store this in a table. Alright? So these are the things we need to connect with this person over here, which we named Caleb, and I accidentally erased him, whatever. We'll just leave it at that. So that's Caleb, and we want to store this information in this table, which is a graphical way to illustrate how we're storing data in a database. So we take his name, Caleb. We take his username, Caleb Curry. We take his password, Pi123. We kind of get this table concept. It almost looks like a spreadsheet that we talked about in the last video. Although it is slightly different, and we'll be talking about that as time goes on. This guy is the entity that we're storing information about. These are the attributes that we need to store about this person or any other person. So we enter specific values for each one of these attributes to make the relation between the attributes and the entity. Hopefully that makes kind of somewhat sense, and if it doesn't, don't freak out. This is complex thought, and you don't necessarily need to understand every single detail to design a database. So I'm just trying to explain things, and we'll get through it. These are the attributes of this person, this entity. An entity is basically just anything we store data about. It's something. It can be a person in this case, but it can also be an order. It can be a customer. It can be a client. It can be a employee, an employer. Whatever it is, it doesn't even have to be a person. So now, the relation idea, you kind of understand that. We're just making the connection between the attributes and the entity. The value, the entity attributes, we're entering that in the database. That's kind of a weak explanation, but honestly it doesn't really matter that much for getting into basic database design. So if you want to learn more about that, just look up relation and database design, you'll figure it out. So now we have the entity over here, and then we have the attributes. So in table terms, you probably know rows and columns. You might not know specifically what they are, and I'm going to tell you. This right here is a row. Can you see that? Might be running out of space here. I think we're good. Yeah, we're good. So all of these values are a row. So a row is all of the attribute values for a specific entity. So this row, it'd be easier just to go like this. This row points to that entity, that person. Pretty simple. A column are all of the values for a specific attribute type. So the attribute type is username. We could have another person, Billy Joe, and his name, his password can be pizza with a U, and his name can be Bill. This is another person in our table. So this is talking about a different person. We have this person over here. He's pretty chill. Well, this row is talking about this entity. The username is a column where we have all of the attribute types username. So Caleb Curry, Billy Joe, and whatever more if we put more values into the table. Okay, so this is getting a little messy, so I'm just going to clean it up a bit. Erase. So just to summarize a bit, we have, very first thing, we have an entity type. That's a word you want to know, entity type. Which we talked about entities, I'll just tell you what an entity type is in just a sec. Entity type, and then we have the attribute type. So basically the type means it's a category. So the person was a specific entity, the guy who's named Caleb, That was an entity. It was a person. Then we also had the entity Joe or Billy or whatever his name was. Those were two separate people, two separate entities, although you could tell that they were somewhat similar. They were both in the same table. They were both talking about the username, password, and so forth. So the entity type is user. A specific entity would be Caleb or Bill or Jamie or Jake or whoever it is. So the entity type is basically the category of the entities that we're storing. The category is a user, and all the entities within it should be a user. So my camera stopped recording by itself for some reason, which is super annoying. But anyways, our entity type is the category of entities, such as user. Every single entity should be a user. Caleb was a user, Billy was a user, we could have Jimmy, John, we could have Catherine, we could have Caitlin, we could have Cassandra, we could have, you get the point. The attribute type is basically the categories of attributes. So we had the username, we had the name, we had the password. These are attribute types because we don't actually have a specific value. If, like, no one's name is name. When we actually give these specific values, they no longer become types and they become specific examples. So this guy over here, here's our entity. We can store, so basically, here's our entity. We can store attributes about this entity. The username can be Caleb Curry, blah, blah, blah. The name can be Caleb, and the password can be Pi123. So these are specific attributes about that guy. Now, these are all like complex terms and blah 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 blah. Who really cares? What really matters is, can you put this into a table for people to understand? Who really cares if you know the terms? But I mean, I'm sure your professor cares, so make him happy. Anyways, in a table, the columns are the attributes. So we could have, for example, an ID, a password, a username, an email. We could keep going, address, phone number, and whatever else. And then a row is where we give a value for every single one of these attributes, all talking about one entity. So like this guy right here. Well, his ID, for example, 72. His username is Caleb Curry. His email is coolguy@hotmail.com. Blah, 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 blah. All of this row talks about this guy. So basically, just think attributes are columns, entities are individual rows. Sweet. Then this whole thing right here, this is the table, and that is the entity type. So the entity type would be user, because every single row within this table should be a user. Oh, another thing I would like to mention real quick, another name in mathematics for a row is a tuple or a tuple. I think it's tuple, I don't really know. But that is another term you will hear. So yeah, tuple is a row. Thank you. So yeah, sorry for like yelling and getting all intense, but it was fun, right? This will be about database management systems, and because this series is over relational database design, it'll be specifically relational database management systems, and we'll talk about the difference. So first, let's just talk about in general, what is a database management system? So this is often shortened to be DBMS for Database Management System, and Relational Database Management System is the same thing except it starts with an R. So it'll be RDBMS. So I'm just going to write that because it's easier. Alright, so where we left off in the last video, we learned, well actually like both of the videos, we learned that a database can be used to store a ton of information. So we have this database, just think of it like a barrel with a ton of information just piled in there. So like usernames and like passwords and junk and transactions, and all this stuff is listed in here. And as you saw in the last video, it looked very similar to a spreadsheet. So what makes it different? We have all this data, now what do we do? What do we do, just look at it? No, don't be a noob. Obviously we do cool things with it, obviously. So, I don't even know what that was about. So what we can do is we can run what's known as a query. So a query, just sort of like searching our data, doing something with it, and giving us cool results. So a database management system uses our data and manages it, allowing us to view it in a human-friendly way and do cool things such as search for values, change the appearance of data, change the way data is stored, and so forth. So, for example, we have 6 billion users, okay, just for an example. And we want to delete anyone who hasn't been active in a year. Well, without a database management system, all we have is a bunch of data, and we'd still have to go manually do all that and delete all that. So the database management system is what allows us to easily run a query, alright, select everyone who hasn't been online in a year, and then we can delete everyone who basically just delete everyone who hasn't been active in a year. Basically, a relational database management system is just a subcategory of a database management system, a specific kind that is designed to work with relational databases. So yeah, not much of a difference there. So just some of the things that these database management systems can do. The first one is obviously run fancy queries to give us specific results, such as give us all of the transactions that were processed before 2011, June 10th. That's something fancy we can do with a database management system. It also allows us to change the way our data is presented. That's something known as a view mechanism. So basically, a view mechanism allows us to change the surface appearance of our data. So when we store our values in our database, we might have it to where we're going to store an ID, we're going to store a username. I'm just going to shorten these up to make it easy. We're going to store a username, we're going to store a password, we're going to store an email, and then we're going to store street address, state, city, and so forth. But let's just say this is how it is for now. Here is the actual table structure for the user table. So here are all of our attributes for a user. I'm going to get rid of this so it's clear. Well, with a view mechanism, we're able to get different views of this data at the surface level. So for example, if we had two people accessing this data, one, let's just name him Jim, and the other one, let's just name her Jamie. Yeah, Jim and Jamie. Let's say Jim, he doesn't really care about the emails because all he's working on is to find out information about usernames and passwords. So what he might do is he might create a new view of just the username and the password. Once again, I'm just shortening these just to make things simple for illustration. I probably wouldn't put them in the database like that, unless you wanted to, but whatever. So this is a specific view. We can select the username and the password, but the internal structure of the data has not changed. This is still how it's stored within the database. Jamie, on the other hand, she cares about the ID and the email. So she creates a new view, just like that. So these are both called views. So the view mechanism allows us to create different views. This can be used for database administrators as well as for other applications, such as when we have a web page. We may only want users to be able to access their username, password, and email. But stuff such as the date they registered, that might be all private on the database, so then we can just create a view giving them the information that they have access to. And that is a layer of security. So basically, if we have a huge database for a business, well, the database administrator is going to have access to it all. The president of the company will probably have access to it all. But the people who are advertisers, they probably only need to know information about advertising. The people who monitor comments on your website, they're not going to need access to the sales and the transactions. They're going to need access to the table for comments. That's a security feature that a view mechanism allows us to do by giving different views. So not every single person who uses the database has the privilege of creating a new view. Just because you can access the database does not mean you can do things such as update data, change the way it's structured, and so forth. That is probably something only the administrator or the owner of the business is going to be able to do. That means we can allow users on websites, they can only access their specific username and password. They can't access everybody's username and password, only theirs. But if this guy, Jim, who is hired at the company, he can access the username and password of every single user. That's a security difference between the two people, not allowing the user of the website to get too much information, and at the same time not limiting Jim to too little information. So that is a really good security feature. Alright, so what else? A relational database management system allows us to do transactions, which we'll be talking about as the time comes. Basically, a transaction is what it sounds like. It's when we do something with the data that, for the technical terms, basically it is either complete all the way or it doesn't work at all. If we have a multiple step thing, such as transferring money to an account, deducting that much money from the other person's account, and so forth, updating the data, boom, saved. If at any time the power goes out and the server crashes and it doesn't complete, well then the transaction is canceled, nothing is saved. That's something you can do with a relational database management system. So that's pretty much the basics of relational database management system. Just in case you're not really sure of like the terms and stuff, examples of relational database management systems, or just database management systems. MySQL is one. It allows us to build and run a database. SQL Server is one. Basically, like if you like Microsoft, it's run on the server and then you access it. So you have Microsoft Server. We have Oracle database. We have, I don't even know how to pronounce it, like PostgreSQL or something, and so forth. The list goes on. But basically, all of the big terms that you hear in databasing, they're referring to the relational database management system or the database management system if it's not a relational database. Don't really think of the database and the relational database as two separate things. They're used as one. But if you do want to be like conceptual about things, we have the database, which stores the information, and then the relational database management system, which allows us to manipulate that data. When we have something such as MySQL, we don't really have a difference between these two, and everything's just kind of like, okay, we use MySQL to create the data, it's stored, MySQL is kind of like all we do. The actual files, they're stored on hard drives on a server or your home computer, wherever you're running your database from. And the relational database management takes the data on the hard drive and puts that into presentable tables for people to, like the administrator, to view. Because if we have like a hard drive disk, let's just say this is a hard drive disk, and some of the data is going to be stored like right here. Other parts of data is going to be stored like right here. and some right here. Well, if this is a table, the relational database management system is going to be able to take that and put that in the appropriate location to make it presentable. So don't really think of it like, oh, we have a database and then a relational database management system. Just kind of think of them as one and whole in themselves. So we just have like MySQL. The other thing, finally, I know I'm kind of running along on this video, the other thing a relational database management system is going to do is it's going to create a consistency. I need a bigger piece of chalk here. Consistently, it's going to make consistency behind for the front end. So on a website, we could have someone put their full name in one box, and that can be stored on a database as two separate columns, first name, last name. Well, let's say if we updated this and we decided to make it one column for some reason, which I don't recommend, well, the front end didn't change because the only thing that changed is the back end. With a database, we can have consistency on our front end to make our users happy, never having to worry about things changing. On the back end, the things can change. For example, the way we store dates, or our time zones, or our character sets. Well, that's not going to affect the front end unless the data on here directly affects the front end. For example, if this is a username column and we delete the username column, well, that's going to cause issues because it's not a column on the database. But basically, when we have a database, the front end is generally consistent, as well as we have server-side scripting languages such as PHP or whatever else. Well, that is going to hide our database an even step farther. So basically, rather than saying, oh, there's no username column, it'll say something like error, try again later. Something very vague so people don't understand, like, oh crap, I can hack this guy because I know his database structure. I can figure out how to mess up his website or his business or whatever. So yeah, that was a server-side scripting language. I'm not going to write that out because it's huge. But yeah, that is the basics of relational database management system. Hopefully that was helpful. This video will be talking about SQL. So, SQL. Alright, so what is SQL? SQL is a programming language used to communicate to a database. Basically, we speak English, databases do not. So SQL is kind of like the mediator between computer, database, and human English. Think of it like that. It's almost English, it's very simple, and in this series we're not actually going to be programming any databases, although we will be talking about general SQL concepts, so it's important that you know about SQL. So SQL is not like a specific relational database management system programming language. It is a general language used for every single relational database management system. From vendor to vendor, such as MySQL to SQL Server or something else, it might vary a little bit, but the general concepts of SQL stay the same. So this is going to be a general concept that you should know about. So SQL first is used to define the database structure. And then it manipulates the data within. So basically we can kind of think of SQL as two categories here. One, it defines the structure, and then two, it manipulates. By that it means we insert data, and then we can search it or delete it or update it. These are the two subcategories of SQL. We actually, for some reason, named these their own languages. So this is Data Definition Language, or DDL, and this is Data Manipulation Language, or DML. Some people may say there's more categories, but I mean this is pretty much the main two. So think of it like this. just going to erase this here. Now that we have this, we have DDL, DML. When we have like a table, for example, I'm just going to write this down here, and we have the columns. So we have like ID, username, password. Well, that's data definition language. Data manipulation language is what we would use to insert a new value, such as the ID of 72, the username of Caleb Curry, the password of Pi123. That's data manipulation language. So when you think of a table, and obviously if you have a big database, you're going to have multiple tables. Well, all of the structure and the connection between tables, that's all data definition language. So it gets all of the main structure of the database, and then the data within the database is data manipulation language. So those are the two main categories. I just want to talk about some of the features of both of these languages. So basically when we define tables, we have a create statement. So basically all SQL I write in all capital letters. That's just a pattern that I've chosen. So create is an example of an SQL command used to create tables, and we can create a database this way. That is data definition language because we're defining the structure of our database. A command such as update, or So update, if we're updating the actual values within columns, well, this is manipulation language because we're not changing the structure. The column stays the same, just a specific attribute of an entity changes. We're updating Caleb Curry's username to Caleb Curry 123. Well, that's a data manipulation language. Another thing that SQL can do is what's known as a join. And joins are very important with a relational database management system. Because with a relational database management system, we break things up into separate tables. For simplicity's sake, for one. Sorry, was I out of the scene there? I think I was in. Whatever. Rather than having a spreadsheet with like tons of information, we break it off by entity. So here's a table about the user. Here's a table about the orders. Here's a table about the customers. Then we can join those values to get a new larger table, a new view that looks like a huge unorganized table. I mean, basically, it looks, it doesn't look like we broke it up into multiple tables. So if we have a table here, and then we have a table here, and let's just say we have, this is a sale table, and this is a user table. Within the sale table, we have a sale ID, we have a user ID, the person who bought the stuff, and then we have the objects that they bought. And I mean, this is just a silly example, just for you to understand the concept of a join. And then within the users table, we have the name, the user ID, and so forth. We can do a join here. We could take the objects that they bought, the objects that the person bought, as well as the name of the person who bought it, connected by the user ID. Which we'll talk about this more. Then we can get a new view which has the name and the items that that name bought. And it's all talking about the same entity, this user. So a naming convention is just a pattern that people do, or that you do, to keep things consistent. So not only will this naming convention help keep my database consistent across different tables and columns, but this naming convention is not only mine. Other people use this naming convention. That means when I go to a different person to review my database, they already understand what's going on. Now obviously there's multiple different naming conventions. There's not one way to do everything, and it's not required. This is just how I decide to do it, and this is because most people who use MySQL, which is what I learned first, use this. But for different relational database management systems, you may have different systems of naming things. So I'm just going to explain what I'm going to do. Anytime I write SQL, I put it in all capital letters. So, select is an example. Fortunately, we're not going to be doing much SQL, so I'm not going to have to write in all capitals on a chalkboard because it's quite complicated. But when we're talking about anything I name myself, I use all lowercase letters. I just use all lowercase letters because I just think it makes it more simple. So when we have a table, such as a user table, I don't capitalize the U, and then when I have an ID, I just put user ID, or just ID, whatever. But I don't capitalize ID, I just keep it lowercase. And for spaces, I just use an underscore, so I don't use any spaces. So basically that's my naming convention that I use, and yours will vary. And we haven't really got to this yet, so you might not understand this, but if I have a foreign key, basically if I have a connection over here to where we have the same column over here, I just make sure they're named both the same thing so I know what they're talking about. So yeah, some people do things such as put like user table, or they capitalize certain words. And if you want to look at other naming conventions for your specific relational database management system, go right ahead. In fact, I'd encourage it. But just so you understand what I'm doing here, I will be doing that. Another thing, when we're talking about stuff in the real world, sometimes I don't necessarily use that naming convention. Because if I'm writing everything I need to store about a user, well, I might just put, we need to store the user's address. I'm not going to put the underscore user's underscore address. I might just put the user's address with space in English. And then when I start making this into a database structure, schema, whatever you want to call it, then I'm going to convert that to just address, lowercase. We're going to be talking about, okay, what is database design? I mean, we talked about what's a database, but we never really talked about database design. Why do we have to design a database? What's so special about it that it needs design? It's not like we're building a house or something. Well, in a way, it's kind of like that. We're building schematics to build the best database. How do you measure whether a database is good or bad? Well, it has to do with data integrity, which we'll talk about that in more depth in an upcoming video. So data integrity is basically where all of your data is correct, it's up to date. There's no disconnected data. For example, if we have two tables and for some reason these tables are connected in some way, well, if for some reason this link breaks, well then when this table updates, this table gets left behind and then the data becomes incorrect. That's a data integrity problem because the data is not managed properly. So with a good designed database, we prevent data integrity issues. So all of our data is up to date. We don't have repeating data. We don't have old data that should not be in there. Which, if for example, like if you have a database, you can store lots of information from like long ago, and that's fine. But you don't want data that has recently changed and it hasn't changed in the update. So you want the database to always be up to date. Unless for some reason you're storing like an archives, let's say you have a store and you want to store an archive of every single order you've ever made or sold or whatever, well then you can store all that in a database and that doesn't really need updated because it's an archive. But if you have a customer in your database and the address is out of date and doesn't update, well then you have a problem. Another example is if the person if your database is designed badly and you have repeating data, well then one example of the data can update and the other one's left behind. So now you have like two addresses for one person. which should just be one address. That's another example of a data integrity problem. So we'll be getting into like specific cases of data integrity problems as we go on. But when we talk about database design as a whole, people usually break it up into 3 sections. 2 or 3, it just kind of depends on like what people, I mean it varies from person to person. So okay, first we have the conceptual, and then we have the logical, and then we have the physical. Alright, these are all known as schemas or schemas, however you want to pronounce it, but that's this. Alright, so we have the conceptual schema, the logical schema, and the physical schema. A schema, or just think of a schematic, like when you're building something, it just tells you the way the data is structured. The conceptual, this up here is when we're just kind of thinking about things, how things are related. We don't think of limitations as in, oh, we're not going to be able to do that because we only have this much availability or something. This is kind of like unlimited brainstorming phase. And as we move down, this is more specific to where we say, okay, this is how we're going to program our database. So up here, this up here is more general. This down here is more specific. Once you get down here, you have to start worrying about, alright, what kind of relational database management system am I going to use? But when you're up here, you can just kind of think of general concepts, how data is related. So the farther you go down to the physical, the more specific things get. I mean, that's pretty obvious. So rather than thinking of it like 3 steps, I kind of think of it as a continuum. We are taking our general ideas and moving them to specific implementations. Hopefully that makes sense. But basically, when we talk about these individually, the conceptual just talks about how data is related, because in a relational database management system, we have relationships between tables. If you think of, we have a users table, and then we have a sales table. And these users can go to this website and buy products. That's our example here. It can be anything, but this is just an example. Well, every single sale has to be bought by someone, specifically one user. So that means there's a connection between the user and the sale. So we have this connection here. That is part of the conceptual design. We say, this table, the sales, depends on the user. So that's because without a user, we can't have a sale because there's no one to buy the stuff. And a user doesn't necessarily have to have a sale. So it's dependent this way. That would be the parent, that would be the child. Hopefully that makes sense. When we get to the logical, we start planning out our table structure. So we have all these relationships between data. Well, then we can realize, all right, we have specifically a user's table. And we have X number of columns, the username, the password, the ID, the address, the phone number, the credit card information if that's something you need to store, anything like that. Then we have another table, and it is the sales. So we have the sales table. So we have user, the user table, and then we have the sale table. And then this is connected in some way. So we have a user can have multiple sales, and a sale can only have one user. That's logical database design because we're actually structuring our columns, our data types, our relationships. We're drawing those out, so we have this logical drawing or schema. The physical, that is when we start actually implementing that into a database. So when we're talking about just designing and we're not actually creating the database, the physical design would be figuring out what relational database management system will work best, what are our table types, what server are we going to store this on? How are people going to access this? Is it going to be over the internet? Is it going to be over computers, programs? So usually a database will be on a server, and this will be accessed by multiple different people. That's because the database is like the core of all data. For example, if we only had this one person using the data, well then we wouldn't need this huge database. We could just store that information on their computer because they're the only one on there. It doesn't even make sense. So typically, everything's kind of accessed on a server. So the physical would be, okay, what kind of server are we using? How are people going to access our data? Is it going to use a web form? Is that something we need to program? And then when you physically implement that, that's when you actually program the database, build the web form or whatever you are doing, installing the server and testing, building the users, who's going to access it, the views, what are the different views going to be, what data is going to be returned, and so forth. This is also when you really focus on security, because logically, when we're in the logical phase, we're still kind of thinking, okay, no one's going to try and break it. No, everyone's going to use the database correctly. But in the real world, that doesn't work out that way. People, either they try to break things, or they just don't know what they're doing, or there's errors, or there's incorrect data. Well, that's when, somewhere along this continuum right here, is when we need to start worrying about security. We don't want people breaking into our database, and we don't want our database to fall apart and have data integrity issues. So hopefully that clears some things up. So the database design, just to sum things up real quick, database design is using skills that you know to build a database that is not going to have data integrity issues, update anomalies. We'll talk about those too, but that's basically when, if for some reason you're storing two of the same data, like if my address is in the database twice, well that's a problem, because when I update my address, only one may update, for example. And now the address says I live in two different places. That's wrong. So a database design is a method to separate information over multiple tables, rather than having one huge table like this, where I store my address, we store our sales, we store our customers, we store our favorite video games, we store our relationships with, yeah, you get it. So basically, this is a bad design because it's all in one table, and when I have to update it, so we have, let's just say this is a row, right? And I have, the columns are ID and username, and then we have, oh, this is going to need to be a little bigger, and then we have username, we have address, here, let's go phone number, it's easier, phone, and then we have favorite color. When we store it like this, well, if we need to put a new favorite color, we have the ID 7, that's me, we have the username Caleb Curry, we have the phone number 1-800 ... favorite color camo, and then if I want to put a new favorite color in, well, we can't because we don't want to, we already put one in there, so we need to create a new row. Say 7 Caleb Curry 1-800 ... and then favorite color green, no, red. Well, now we have all this duplicate data. We have this in here twice, we have this in here twice, we have this in here twice, and we have to have two rows for favorite color. So you have to find a solution to this problem. But now, if I decided to update my phone number because I got a new phone number, well, now I'll update it and I'll change it to 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever it is. Well, now I updated my phone number, but for some reason we have a data integrity issue because my phone number is in here two different ways. That's a bad database design. And in this series, we're going to be talking about fixing problems like that. And the best way to do this would be to like separate it into multiple tables. Plus, you probably don't need to store your favorite color unless you're running some kind of like art website or business. So it's possible, but we can do the same thing with like orders. How many orders? If I had to put my orders in that table, which is another bad idea, we have the same data integrity issues. So this series is going to talk you through getting rid of those data integrity issues so you have the best database design for best performance. We're going to be talking about data integrity. Alright, so what is data integrity? We talked about it a little bit in the last video, but this video is going to be going over it in more depth. Data integrity is just having correct data in your database. So when we're databasing, we don't want repeating values, we don't want incorrect values, and we don't want broken relationships between tables. For example, in the last video I gave the example, you have a table here, and this is the user table. This is weird writing like this. And then we have a table over here, and that is the sale table, which is where you sell products, for example. This is just an example. You can implement other examples, but this is just to illustrate my point. A sale is when a user buys product. That means a sale needs a user as the buyer. Otherwise, there's no sale. We can't have a sale if no one bought it. Does that make sense? That means the sale is dependent on the user, and we have a relationship. The user buys stuff. Stuff is bought by a user. This is known as a, can you see this? This is known as a relationship. Now, do keep in mind that the term relational database does not come from the word relationship. It comes from relations, which is the mathematical connection of sets, which we talked about that in an earlier video, but just don't get that confused. But relational database does have relationships between tables. So this, if for some reason this was broken, and now we have a sale that was bought by a user or no user. So for example, let's say this sale was bought by user with the ID of 7, okay? And then we have a user of ID of 7. So there's a connection. The sale was bought by the user of ID of 7, which points back to the user. Make sense? That's data integrity. But if this relationship is broken, and it says this sale was bought by the user with the ID of 7, and then this person is removed from the database, well, now this sale points to a table or a user that doesn't exist. And that might be practical in some sense to say that sale was bought by that user when he did exist. But for things that need to update consistently, we don't want that to happen. So that's an example of an integrity issue. So you want to keep that relationship to say, okay, well, we got rid of the user. We need to update the sales to say, well, either the person is deleted or also do something with the sales. So, yeah, sorry if that was a little confusing. Okay, so the three main types of data integrity. First one is entity integrity. We talked about entities in like one of the first few videos. An entity is anything we store data about. So we had the user to begin with. This is an entity. What it means by entity integrity is basically unique entities. When we have a user, we often give them IDs. This is known as a key. So an ID is used to enforce uniqueness among the entities. Like for example, if we had a table for users, and we store the name of the person, and then we stored their address. No, let's just go their phone number. Yeah, sorry. Because when we talk about addresses, it's best to break it up into like street, state, and I don't want it to go through all that. So we could potentially have a person with a repeating name. So let's just say his name's Caleb, and his phone number is 1-800-YOU-WISH. Alright, well, if we had another person, if they both lived in the same house, for example, and this was their house phone, well, sometimes people will name their children the same name as them. So now we have two people with the same phone number, and you look at this and you say, okay, well, either we have two people with the same phone number, or we have two rows talking about the same person. And we don't know, because we don't have proper data integrity. So a way to solve this is to either add more columns to where the row would be unique, such as a social security number, or we could add an ID column, and this would be like 6 and 7. So now we're talking about two separate entities. This is talking about this guy, because his ID is 7. This one is talking about this guy, because his ID is 6. They're two separate entities. That's entity integrity, having uniqueness among your entities. We have uniqueness with the rows, and we also have only one user table. We're not going to have another user table because that information should go in the original user table. On to referential integrity. This is the one we talked about earlier, is when we reference the ID of a table in another table. If we had a comments table on the website, right? And we say who the comment is by, we have a user ID which points back to this ID over here. That's because the comment has to be posted by a user. Otherwise, we have a comment that didn't have someone who posted it, which doesn't make sense in the practical world. So we always have to have referential integrity, which basically says every time there's a comment, there needs to be a person who posted that comment. And that connection needs to remain. It needs to stay. If for some reason this is disconnected, and then this user is removed, or this table is changed, well then this could change. I mean, this stays the same, and then there's a disconnection to where this is changed, and this is old, outdated data, where either the user no longer exists, and the comment still says he does, or something else like that. That's referential integrity. And that'll make more sense once we start designing and stuff. But yeah. Domain integrity, that brings up a new word, domain. Domain is basically just the acceptable values for a column, per se. It's what we are storing, the range of what we are storing within a database. So when we're talking about tables, we have columns. So these columns up here, let's say we have a phone number. Well, that means we should have a certain number of digits. We have the area code, and then the 3 digits, and then the 4 digits. And that's at least the US. It might change other places. But that is 10 digits. So we know that the phone number should be 10 digits, and it should be numbers. So if for some reason I put the word cake in the phone number column, well, for one, this is going to cause an error if we have domain integrity, because it's not a 10-digit number. It's just a word. That's not the proper domain. It's not a digit, it's not numbers, and it's not 10 of them. So we know that's going to cause an error. So that's the basics of data integrity. When we don't have data integrity, we have errors. When we have data integrity, we do something to correct those errors, such as saying, oh, these all need to be numbers. That's how we implement data integrity, by setting database rules. And how you do that with the database, well, that kind of varies upon the relational database management system that you use. Some relational database management systems allow for general rules saying, okay, this has to be a range of this numbers. Some of them are more vague where they only allow you to implement data types. Data types would be like integer 10 digits. So when we talk about practically implementing data integrity, different relational database management systems have different things you can do. Almost every single relational database system that I know of, I'm pretty sure all of them, but who knows, they allow for data types. So a data type is pretty self-explanatory. It's the type of data. So in database, we classify things as generally integer or text or date. So we either have numbers, text, or dates. That's like 3 general categories, which we'll be talking about that more in a future video. But the data type can put limits on what we're allowed to store. For example, we can say, okay, we only want a character column with the maximum of 20 characters. That means we can put a string in the column that says, I like pizza, yeah! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That'll fit. But if I wanted to change this pizza to lasagna, well then I just added a couple extra characters. That might cut it off. I'm not sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's the maximum we could put in that data type. That's an example of implementing that data integrity for the characters. So this will be for the domain integrity. We can also have referential integrity with what's known as foreign key constraints, which allows us to connect tables. Because when we draw tables, we could say that they're connected in some way. But how do we enforce that in a database? We use foreign key constraints. For example, we can say if this is the parent, let's say this is the users, and this is the comments. The user places a comment. So this is the parent, this is the child, because the child can't exist without the parent. You can't have a comment without a commenter. Well, using foreign key constraints, we can say, alright, if this user gets removed, also remove all of the comments by this user. That's an example of a foreign key constraint. As for the non-repeating data, that is done with just designing your database in the best way. So yeah, I know that video was kind of jumped back and forth from concept to concept and maybe a little confusing, but I'm sure you'll get it as time goes on. I just want to do a little bit of review as well as go over the vocabulary that we've learned. So if you don't really want to know, we're going to go over some new ones too, but if you don't want to review, then feel free to skip this video and the next one. So this video will be about data and database design terms. So the very first term we learned was data. Data is pretty much anything we store in a database. You pretty much know what that is, so that one's pretty good. Database, that is what we store our data in. And then we have a specific kind of database, which is a relational database. And what's special about a relational database is that it stores things in tables. We have a database management system, or database managed, DBMS for short. That is how we manage a database using code. That's how we control our database. We have a specific kind of database management system called a relational database management system, which is just used to control our tables and the values within our tables of a relational database. Pretty simple. Now we're going to introduce a new word to you, which is null, or null, however you want to pronounce it. I've been told I pronounce it wrong, but I don't really care. Anyways, this is when someone does not enter a value within a column on a table. So if we have a table and we have something such as fax number, well, not everyone is going to have a fax number. So when we have a guy, let's say we have an ID here, we have a guy with the ID of 7, and we don't have a fax number, this emptiness is said to be null. So basically, you'll hear empty value, although by definition, null means no value, so it's kind of a bad definition, but who cares? Null basically means there is no data in that specific field. And we'll be getting into more terms like that in a second. So that is what null means. That's one you will need to know. Another one is an anomaly, or anomalies. So, anomalies are basically errors within our data our data integrity. So when we have an anomaly, it's something that goes away from what we expect or from the normal. When we update something, for example, and instead of updating one column, it updates 10 and it wasn't supposed to, that's an anomaly. So yeah, you'll need to know that as well. The other one is integrity. We implement database integrity to protect against anomalies. So we went over 3 different kinds of integrity. We went over entity integrity, we went over referential, and we went over domain. Real quick what these are. Entity integrity is saying uniqueness among the table. Referential keeps the connections, the keys, foreign keys, primary keys, they keep them connected across multiple tables. So we could say these 2 tables have some kind of connection. And then domain is basically saying a column within a table has all of the expected values. So we have a phone number, we would expect numbers, not text, or not a date. That is domain integrity. And the word domain is basically the range of values that are acceptable to store within a column. So these are our data vocabulary that you should know. Now we're going to move on into the design terms. Yay. Okay. So designing is what we're here for, so this is fun. Very first thing you need to know is an entity, which is anything we store data about. A user, a mortgage, a transaction, a credit card information. Anything, the comments, a comment. They're all entities, it's what we're storing data about. Then we have attributes. Attributes are the things we store about the entity. A comment, an attribute of a comment would be the date that it was made. The length, how many characters is it? Who posted it? That's an example of an attribute. A relation, if we're talking about mathematics, it's a connection between 2 sets of data. When we're talking about databasing, put very simply, it's just a table. So a relation is another name for a table, where we have data within our database. So we can have a structure of different tables. So these can be connected. Just, I don't know, however you want to connect them. This can be our database, Well, each one of these different sets of information or data is known as a relation. It's a table. Next term is a tuple, however you want to pronounce that too. Just winging it here. That's another thing for a row. It's all of the attributes about a specific entity. So if we have this guy, we can say his name is Caleb, his phone number is blah 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 blah, his address, his age, his birth date would probably be better, how long he's been a member of this website or whatever it is. All of these values about this entity, that's what that is, a tuple. That would also be a row on a table, because we physically represent relations with a table. So when we have a table, we have the columns, so we have name, phone number, address, social security number, and then when we enter all of those for a specific person, we have the ID of 7, the name Caleb, the phone number, blah blah blah, the address, blah blah blah. That is known as a tuple or a row. Another term is a table, which we just talked about that, which is just a physical representation of a relation. Tables are what we store in a database to organize. Am I like cutting my head off there? Can't really see. To organize our data. Within a table, we have rows and we have columns. The rows would be a specific individual entry within our table, so like that guy we just drew, all of his values would be his row. The columns are that specific, a specific attribute of that person, such as a name. This is the column where we would put the value Caleb. Alright, now we also have another three more terms that we haven't learned yet, which you will possibly hear. They're kind of older terms, but they're just talking about the same thing. You may hear the terms file, record, and then field. So what are these talking about? Well, file is just another name for a table. A record is another name for a row, and a field is another term for a column. So other than that, we have the words value. A value is the information that we put in to a specific column. So here is a value, Caleb, or subscribe, or 700, or June 16th, whatever it is. Those are all values. Alright. Oh man, it's already 10 minutes. Dang. Alright, then we have an entry. You may hear the term entry, which I like to use this for it's almost like a verb. When you enter data, you get an entry. So basically an entry is just another name for a row. So there's obviously a lot of similar names, and we'll be making a table saying what word. Just give me a minute. Database design. The process of designing your table to remove anomalies and have data integrity. Schema or schema, however you want to pronounce that. That is just a that's just a drawn out structure of our database. Then we have a new term here. It's called normalize or normalization. Normalization is basically just a bunch of steps that we're going to follow to help us get the best database design. So that's part of database design when we go through these normal forms to get the best database design. We'll talk about that more in an upcoming video. But I want you to know that the term normalization is the process of building the best database design. The other one, naming conventions. A naming convention is just a consistency used to make things consistent. So we name tables a certain way, we name columns a certain way, we name our database a certain way, we draw our database schema a certain way. So basically, convention is anything that is done repeatedly to create consistency. And the last one here is keys, which I'm not sure if I talked about this or not yet. I think a little bit, but not much. A key is something to make everything unique within a table. This is how we make connections among tables. We connect IDs. We may say, oh, this comment was posted by the user with the ID of 7. Well, that points back to the user table. We do all of that with keys, and we'll learn more about those as time goes on. Alright, so you see we have a lot of terms, and a lot of them are repeats, for this meaning the same thing. For example, we have a relation, and then we have table, and then we have file. So relation, table, and file are all talking about the physical structure, a table, pretty much. Record, I'm going to circle these ones. Record would be a row, so we have a row, and then we have a tuple. These are all talking about rows within a table. And then we have, how should I do this? Let's cross them out. We have columns, and then we have attributes, and then we have a field. Those are all talking about a column in a table. And also entry, you can kind of think of that as a row, because you enter data into the table and you get a new row. A value is just a specific, you can think of it like, I'm going to erase some of this. We have this table and we break it up into columns. So we have ID, name, and then phone number, for example. Those are our column headers, and then we have specific values. 7, Caleb, da 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 da. And then we have another guy, 8. Well, if we separate this into cells, which is another term, we have a specific value that we put in here, such as John. That is a value. Now, entity, that's the only one that's, so we just went over value. Entity is what's left that's not circled or crossed out or squared or something. Entity is, I don't like to really assign this to like a row or a table or anything, because an entity is just something we're storing data about. So that could be an individual row, or it could be the table type. So for example, we have a table for users. Well, the user is the entity, but a specific entity would be a row within this table, because we'd have the entity for this guy over here, and then we'd have one for this guy down here, or for this chick over here, or lady, I should say. So these all get their own rows, you see. So an entity, that's just something we store data about. This video will be just some more vocabulary. There's not as many. We're broken up into two categories. The first one is SQL. So first we learned about SQL, which obviously is a programming language used to, by the way, I never even mentioned this, I'm horrible. Structured Query Language is what SQL means. That's what it stands for. It's used to connect to your database. Oh, sorry, I just got distracted. I was waving this paper, and like my lens is like flashing for some reason. Anyways, the next part was data definition language, which is used to define, it's part of SQL. So SQL has data definition language and DML, data manipulation language. DDL is used to define the structure of our database. Data manipulation language is used to insert values in our database, as well as update them, delete values, and search values and so forth. The other thing was, I never really mentioned this, but I do want to mention it here, SQL keywords. So anytime we have the word keywords in a programming language, it's talking about something that is reserved that you're not supposed to use for your user-defined data. So for example, select in SQL. This is a word that your database is going to recognize as, okay, we want you to do something, we want you to select data. It's a keyword because it's already defined. So I don't want to name my tables or my columns any keywords because it can cause errors or confusion or just make things complicated. I always put SQL keywords in capital letters. Alright, so that's pretty much all for the SQL. Here's my eraser. Go America. And every other country. Alright. Presentation. So the very first thing is we have the front end of an application. So the front end is what the user sees. The back end is what's going on behind the scene. When we have a website, we don't just have what the website looks like. We have code that gives us that look. When we put in data to forms, we have languages that communicate with databases to create a easy to follow, non-confusing front end. But the back end is complicated as heck. So that's the difference between front end and back end. Front end is what any user at a particular time will see. The back end is what's going on behind the scenes. So often when we're working with databases, we will program a front end because we don't want everyone accessing our server. It's insecure and it's just not a good idea. So we often create a front-end application to access our database. Most commonly a website, although there's other forms, but whatever. So if here's our database, rather than people signing into the server and using SQL code to get information, we often program front ends for people to access this data in a different way. So each one of these front ends would be like a website page, for example. So here would be a registration page, here would be your users page, here would be your profile, your home page, here would be, if you like, you can even have different tier systems. So this could be a page where the website administrator can add or delete users. They have that extra privilege. This is also the view system, which we will talk about in a second. Well, the front end doesn't allow us to directly type in our own SQL. It only allows us to use what the front end gives us, which is then communicated to the database. So that's what a front end is. The back end would be the server-side code used to communicate with the database. So when we're talking about clients and servers, we have those two terms. We have client and then we have server. So very first thing is client. Client is, think of it if we have this wall here. Over here we have a computer. And then over here we have a database. This is the client side because we're accessing the database. Over here is the server side. So client side and then server side. I don't really have room to write that, but yeah. The server serves instances of this database to the client where they can access the data in some way. Depends on how the privileges we give them. So when we're talking about different privileges for different people, we use what's known as a view. So first let me finish this. Client side and server side. And we communicate from the client side to the server side by a server side scripting or programming language. Oh, that's huge. Whew, now my hand's tired. We can give custom views. So a view is just taking the data from the database and illustrating it in a different way than how it's actually stored. For example, a user on a website can visit, let's say we're on like a social network and I visit my friend's page. It'll tell me their name, possibly their username if that's what they use, their data registration, their phone number if that's public, for example, anything like that, their relationship status. Although information that is private may only be accessible to the user who owns it. For example, their password or their email or their friends list. That might be a different view depending on what page you are on, and the user that you are. So I may be able to access my own password and email, but that might be private to other people. That's the view. Views often use joins, which basically connect data from multiple tables to create a new table. If we have two tables here, users table, comments table. Can you see that? Can you see it? You better be able to see it. Well, a comment is always given by a user, and we connect it using the ID. It's called a foreign key connection. Well, this ID, let's say it's the ID of 25, right? Well, instead of having, okay, this comment was by the person with the name, with the user ID of 25, we wanted to say Caleb Curry. So we have a join taking the name from the user table and connecting it with the comment of the comments table to get this new generated table. This is just a view. It's not actually stored in the database like this. We're just creating a new illustration of how the data really is stored. And then we can have the name of the person followed by the comment or comments of that person. You may be asking, why don't you just use the name as a reference? Well, that's because multiple people can have the same name, for example. So we always need something that's unique for this connection. Whether, if you don't want to use an ID, you could use something like a natural key username, for example, but I often use IDs, and we'll be talking about that more in upcoming videos. So yeah, that is all of the vocabulary that we have gone over so far, pretty much. If you have any questions about any of those, just leave a comment. I recommend that you write all those down. I should have told you that at the beginning. But anyways, I recommend you write those down as well as the definitions. Study those, learn them, and especially study from the previous videos. Study all the different terms that mean the same thing. Because after a while, you get kind of used to those terms. But if you're just learning and you don't know that these are talking about the same things, well then you can get confused very easily. So I recommend you study, alright, a row is also called a tuple and is also called a whatever, blah, 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 blah. That will help you, that way when I say whatever word it is, you know what I'm talking about and you don't have to like check your charts or whatever, or go watch other videos. So that's something I definitely recommend that you memorize. As well, for the SQL stuff, it's not as important, like the DML, DDL, but I do recommend that you memorize all of these terms as well. We'll be talking about atomic values. So, atomic values basically just mean that it means that the value stores one thing. Everything we store in a database should be one thing. When we have columns, they're about one thing. All of the values within that column are one thing. We have a column name. Well, what does a name consist of? You can have a first name, middle name, and last name. Well, although we're talking about one thing in name, it's not really necessarily atomic, because we're storing 3 names within one name. So if we wanted to make this atomic, the best thing to do for database design would be to break this up into first name, middle name, and last name. So now we have Caleb, Daniel, Craig. 3 separate names, right? Alright, so when we do store things in a database, we want to try to make them atomic. Now, we don't want to go to the extreme where we break everything apart to where it doesn't even make any sense. But just think of like atom. An atom, atomic, when this word came about, we never really split an atom, so we thought of an atom as the smallest indivisible, I think is the word, piece of information in this world. Now we can split it, but whatever. So sometimes you may think that, well, this isn't really a good term, but everyone will still use this term. So just think of atomic as the smallest one individual thing stored. Now we don't want to go to the extreme. For example, if we have the word subscribe, this is a word. It's one word. Don't go to the extreme where we separate it into like individual letters, because that'd be ridiculous. It's like, alright, we store in a table, instead of having first name, last name, we have first letter of the first name, second letter of the first name, third letter of the first name, fourth letter of the first name. That doesn't make sense. We want to break it down until we can treat it as one thing. For example, a phone number, it often has an area code. Well, we don't want to break a phone number up into multiple portions. I often just store phone numbers as one because you treat it as one thing. When it comes to addresses, well, an address consists of like multiple. We have a street address. We have a city, and then we have a state. We have an area code, or zip code, I mean. So addresses, I often break those up into multiple columns rather than storing one address with 1, 2, 3, Epic Lane, legit California, 73821. Rather than storing all of that in one column, I break this up into street address, city, state, area code. And then that allows us to run more complex queries on our data, because we can select all of the users from the state of California, or we can select all of the users who live in this city, or pretty much anything like that. So this is part of one of the normal forms, which we will be talking about in the future. But as for now, just think of storing everything as one. So not only do we want the column to be about one thing, like an address is just an address, or a phone number is just a phone number, but we want the values within that to be singular as well. For example, we could have a column, favorite movies. This isn't going to work because within that column we could store unlimited movies, and that is also improper. So that's not going to work as well. Every single column header should be singular, favorite movie. And you may be asking, well, how would you store multiple movies? Well, that has to do with more complex relationships, and that is something we'll be talking about very shortly. But the solution is not to store multiple things within a column. This video will be about relationships. And I don't mean relationships as in dating advice, because I probably couldn't give any of that. But Besides that, we're going over database relationships. So what is a relationship? Well, in a database, everything is connected. Think of it like a giant web. Somehow something is connected to something else. Rather than storing everything in a giant table, sorry, my board's kind of wet, so it's not really writing very well. We split that, and then we have two smaller tables for manageable data, simplicity, as well as data integrity reasons. So now, we still have to maintain the connection between data, so we take one huge table, break it into two tables, and then we have what's known as a relationship. There are multiple kinds of relationships, and we'll be talking about that in the next video. But for this video, we'll be talking about the general concept of relationships. So relationships talk about entities. An entity is anything we store data about. So this is an entity, and this is an entity. And they are related in some way. They're connected. There's a relationship between them. This eraser is crap. Die! Ah! There we go. Piece of junk. Okay, there we go. Except now my chalkboard's all wet. Alright. Oh, where was I? So we have to worry about entities. There's two terms that we talked about earlier, entities and attributes. Entities are anything we store data about. Attributes are the things we store about the data. Well, when it comes to entities, attributes are what we store about the entities. So basically we have entities, and then we have the attributes for that entity, right? And then we have a different entity. So that is part of our database design. We figure out all of the things we're storing data about. Think of like a college. We could store information about the student, the professor, the classes, the faculty, the whatever else. So we can have multiple entities and then multiple attributes about that entity. And then we can have a third entity. So just think student, professor, class. This is all part of our database. So our database structure consists of three entities and attributes about each one of those entities. What's an example of an attribute? Well, it could be the student's name, the student's address, the classes they're taking, the whatever. It doesn't really matter. They're a major. That's another entity. We could have an entity about the majors, such as science or whatever else. And then we can have attributes for that, like the classes that are required to get that major, how long it takes, and so forth. That will become part of our database structure. Well, these are still related in some way because we have a student is going to school for a major, so there's a connection from this entity down to the major. So let's just replace these with like, alright, here's student, and then, okay, that looks like crap. Can have, let's put some specific examples in here. We could have a student, we could have a professor, just gonna put prof, and then we can have class, and then we can have major. Well, a student goes to school to get a major, a student takes classes, the classes are taught by a professor, the professors typically have a specific area that they teach, so they might be part of the major, like the teachers for that major, whatever, students. Yeah, you get the point. Everything's connected. So when we design relationships, That tells us how we want to structure our tables. That's going to make a lot more sense in the next video. So I just wanted to introduce the idea of relationships in this video. The next video will be talking about a specific kind of relationship. So, 1, 2, 1. That is a type of relationship. There are two other ones. 1, 2, many, and many, 2, many. Here are our three types of relationships, and we will be talking about each one of these individually in the next 3 videos. This one will be over one-to-one relationships. So a one-to-one relationship basically just means that one entity has a connection with one other entity, and that's all they can have. I like to think of a marriage. So we have a husband and wife. This is a one-to-one relationship because a husband can have one wife and that wife can have one husband. The husband can't have multiple wives, and the wife can't have multiple husbands. It's one-to-one because one entity is limited to one other entity. This entity is also limited to one other entity. It's a one-to-one relationship. So another example of a one-to-one relationship would be a social security number. Alright, so a social security number in America is basically just a unique number every citizen is given. There are, I think there's occasional repeats, although generally you think of a social security number as being unique to one person. So we define it as a one-to-one relationship, even if there's possibilities of being repeated data. One person only has one social security number. Generally that social security number is only supposed to have one person. So we have a person, and then we have a social security number. One person has one social security number. One social security number is assigned to one person. If you want to draw out your relationships, you can say person has one social security number assigned, so assigned to one person. So a person is assigned a social security number is assigned to one person. We would not, even though there's a possibility that the social security number might be repeated, we wouldn't design it this way because that's like saying the social security number is supposed to be assigned to multiple people. It's not supposed to. It's supposed to be unique for the person. So we design it as a one-to-one relationship. We're going to be talking about a one-to-many relationship in the next video, and then a many-to-many relationship. And after that, we'll be talking about how we design this within a database. How do we structure our tables? In the previous video, we talked about a one-to-one relationship. That is one of the 3 kinds of relationships that we can have. The other one is one-to-many. What that means is that one entity can have a relationship with multiple other entities, but a specific entity can only be related back to one other entity. I know that sounds a little confusing when we're talking about entities and all this conceptual high-level thinking. But think of it like comment on a website. When you go onto YouTube or whatever and you go below, you can leave a comment on my videos. that comment is only owned by you. It has your name. That is a one-to-many relationship. The reason for that is you can make many comments, but an individual comment is only owned by one person. So to draw that out, you have a user and we have multiple comments. You can see that the user is able to make multiple comments, but each individual comment, like this one for example, is only owned by one user. That is a one-to-many relationship, or 1:many. Can you see that? Yeah, I think you can. So this is how a one-to-many relationship works. If you want to think again of like the marriage thing, think of a king. We'll just name him King Sam. And Sam demands to have multiple wives, and he's super controlling of his wives. So Sam has multiple wives, right? Sorry, I'm just kind of drying off my chalkboard here. We have Sam the king over here. Give him a crown. Give him a big smile. And he is just royal and famous among the lands. And he's really selfish with his women. He demands to have 500 wives. Or however many wives he desires. So we have all of his wives over here. So he has these two wives, and then he has this wife over here. She's not so good looking. But anyways, he is married to these three wives. Although he's very protective and very selfish with his women. And he does not want these wives to marry other men. They're strictly married to the king. So the king can marry multiple women, but each woman can only marry one person. Whoops, I kind of already have the line drawn. So they can only marry one person. They're not able to go marry another guy. That would be, oh no way, that ain't gonna happen. Off with their heads! See what I'm saying? It's not gonna work. So that is a one-to-many relationship. In the last video, we talked about one-to-many relationships. The video about that, we talked about one-to-one relationships. Well, now we're talking about the third possibility of relationships, and that is many-to-many relationships. So when I think of many-to-many relationships, I like to think of a polygamous marriage where multiple husbands can have multiple wives, and multiple wives can have multiple husbands. I like to just draw this out so you can kind of understand what this would be like. We have the king right here, right? So let's say he's the king, and he decides to marry 3 women. Let's kind of make them real quick. Da, 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 da. Man, this guy's... Why do you need 3 wives? Come on. Oh, there we go. Alright, so this guy is married to these 3 women, right? And then he's very protective, but then he decides, oh, what the heck. They can marry different men if they want. Who really cares? So, this girl marries this other guy, right? So now she's married to 2 people. Right? What's wrong with her? Only the king can do that. Well, not now, because it's a one-to-many relationship. One king can marry multiple women, and one woman can marry multiple men. So this guy is married to this girl, and this girl's married to this guy over here, and this guy is married to this girl over here. So Sally is married to Jim, who is also married to this girl over here, see if I can draw one here. And this girl, surprisingly, is married to this guy, who's married to Kathy, who is also married to Jim. And by the way, Jim is married to the second wife of the king, who the king is also married to this girl over here. And you see, well, it gets very complex very quickly. That is an example of a many-to-many relationship. Now, obviously, you're not going to be storing like stuff like this in a database. So let me think of a practical example real quick. I like to think of a college. Specifically, a class and an instructor. Alright? Actually, let's think of a class and a student. So here is a class, and here is a student. Okay? Now, one class. How many students can be in a class? Multiple. You know that. So, we can have multiple students in this class. Let's draw boxes for quicker. So let's say all these boxes are students. A class can have multiple students. Well, not only that, but a student can take multiple classes. So this student can take this class, and this class can be taken also by that student, and this student over here. And then this student can take another class, which can have this guy in it, and this guy can be in this class as well. And by the way, he is all, oh shoot, I dropped my chalk. He is also taking another class, so he's in that class, which has that student and that student. And it just gets very complex. So you can see this might be very, very difficult to store within a relational database. And there are reasons we actually can't store this in a relational database. And you might be thinking, well, what if you need to store the classes that a student is taking and the students within a class? Well, we will be talking about in the upcoming videos with solving many-to-many problems. Many-to-many relationships do not work in a relational database. The only two that will work is a one-to-one and a one-to-many relationship. But this is just the concept. You think of a concept of a many-to-many relationship, think of a class and a student. Class can have many students, and a student can take many classes. In the last 3 videos, we talked about one-to-one relationships, one-to-many relationships, and many-to-many relationships. This video, I wanted to talk about how we design these relationships. I decided I was going to break them up into 3 videos, so first we'll be talking about designing one-to-one relationships, and then one-to-many, and then many-to-many. So this video will be about designing one-to-one relationships in a database. Alright, let's begin. So the first thing we need to realize is that when we have a one-to-one relationship, the attribute side, so we have an entity. So let's just say we have a connection between a person and their username. All right. So we have this guy. Here, let me get rid of these boxes. I don't need those. We have this guy, and he has a username on a website. We'll just say it's Caleb Curry, because that's usually my username for things. And we'll just name this guy Caleb. All right. Well, that username, the only person who's going to have that username is him. And he is only going to have one username. That account is only going to have one username. That's a one-to-one relationship. So we need to realize that this is exclusive to this person. It's all his. No one else owns it. No one else is connected to it. It's only his. So that means we can often store one-to-one relationships as attributes rather than entities. So rather than his username being an entity, it's an attribute. If you don't really know what that means, don't worry, I'll be explaining in just a second. But just think of it as it's exclusively his, so that is it describes him. What is this guy's username? It's Caleb Curry. It's an attribute of that person. When we're talking about one-to-many relationships, though, or many-to-many, we think of like a class. The students of the class are not exclusive to that class. They can take other classes. Therefore, it wouldn't really make sense to store them as attributes because it's not really, it just doesn't make much sense. And I know it'll be clear. So just wait a second. So we can actually have a table. The relationship between the account and the username of the account can be stored just as a column within the table. So we have an ID, and then we have a name, for example, and then a username. This username is exclusive to this ID of this person. So like 6 Caleb Curry. That is how we would design a one-to-one relationship. We would put it within the same table. And if we have a new row within our table, we now have a new person. This person can't have another username like Caleb Curry. They have to have a different one. So we can make it John123. This name is exclusive to that person. So we just store it as a column within our table. Make sense? So here are our individual rows. This points to this ID. It's an individual entity. So the entity is the account. The username is an attribute to that account. There will be occasional times when we store a one-to-one relationship over multiple tables. And I will explain now when that would be the case. Let's just think of an example of a database for a credit card company. We have a relationship between the card holder and the card. So, by card holder, I just mean the person who gets the card and can use it to buy things. The person who owns it, pretty much. And then we have the card. Alright, now let's just say this company only allows you to have one credit card. So this card holder can only have one card, and this card can only be owned by one card holder. That means we have a one-to-one relationship. 1 to 1. How would we store this in a database? Well, if we just went with the attribute thing that we talked about earlier, here's what it would look like. Here's our table. And I'm just going to list the columns. So we have the card holder table. First thing is we would have like an ID for the card holder. We would have probably card holder's first name, the card holder's last name, and then we would have the card. So we could say, well, that's their card. Let's say we could assign every card an ID or a card number. So we could say card number. If they have a card, we can give it a value. If they don't have a card, we can leave it null. Well, that can be considered an attribute of the card holder because all these point back to the card holder. Now, if we want to store more information about the card, such as the issue date when the card was given to the person, so we could say card issue date. Well, now we can see that this is relying on the card, not the card holder. So if we want to store extra attributes about the attribute in the one-to-one relationship, we can move that to a new table, and we can make it a card table, give it an ID, and then we could say card number, and then issue date. Now we can store as much information about this card. So if we want to store the max amount, the late fee, pretty much anything we want to store about this card can be stored in this table, and we can replace this card number with a reference. So we have a card ID, and that points back to this ID. You see what I'm saying? This is a one-to-one relationship over multiple people. Just like this card has a connection to the card holder, there's a one-to-one connection over multiple tables. The reason we did this is so we could store more information about the card. Because if we stored it all in one table, we would have bad database design. And I'll show you why in just a second. Alright, so here's our table. Can you guys see that alright? We have the ID, and then the name of the person, and then we have the card number, and then the max amount, and so forth. Well, you can see that this table is really about two things. It's no longer about one thing. We would have to say this is a user and card table, which is not proper because we're not following the rule of one, where a table should be about one entity and a row should be about one entity. Because now we have the user side and then we have the card side. It's like trying to store two tables in one. The only time it's acceptable to have the card number in the users table is when we don't store more information about it. Because now all we have is a card number. The card number is about the user. It points to the user. But the max amount of the card has nothing to do with the user. Therefore, it's dependent upon the card. So a one-to-one relationship, in conclusion, a one-to-one relationship, the way it is stored is either an attribute within the table, or if you need to store more information about the entity, then we can have another table. And then just use foreign keys to connect them, which that's something we'll be talking about in an upcoming video. Almost always, though, you will be seeing a one-to-one relationship used as an attribute. So when you think if you have a one-to-one relationship between something, you have a connection. Let's say it's a dating website. The user is in a relationship with another user. That's a one-to-one relationship. We could just have that as a column within our user table. So we could have the user table. We could have the user ID, with the name, first name, last name, a phone number, whatever else. And then we could say relationship. That's a one-to-one relationship. We could just have that be an ID of another person. And we don't have to worry about having another table for that. This video will be talking about designing one-to-many relationships. First, I want to bring back an example from the last video into this video so we can kind of explain the differences between one-to-one and one-to-many. So in the last example, we had a credit card company where a person is allowed to have only one card, and a one card can only be owned by one person. Let's draw that out. We'll just draw the table and the columns within that table. So we have two tables here. We have the user table, and then we have the card table. This is when we store a one-to-one relationship over multiple tables. Otherwise, we could just store it as a column because, I mean, we're only storing one thing. We have the user ID, And then we have a card ID. And then to connect these as a one-to-one relationship, we have a foreign key, so we put a connection with the card ID in the user table, the user ID in the card table. So card ID, user ID. What that does is it connects these tables. So the user ID to this user ID, card ID to this card ID. That is how we would make a one-to-one relationship over two tables. And then we can store other stuff about the user in this table, other stuff about the card in this table. Now to convert this to a one-to-many, we can change this to something very small. A one-to-many relationship would be saying one user can have many cards, but a card, specific card, can only be owned by one user. So there's no, a card can't be owned or co-signed or owned by two people. Now the way we do this is, let me just erase these columns real quick. Let's just start from scratch. So we have a user table, and then we have a card table. Once again, we need IDs for both of them, so we have a user ID and then a card ID. The user owns multiple cards, and we don't know how many they own. They can have one, they could have two, they could have three, they could have four, they could have five. So it wouldn't make sense to put the card ID in here as multiple columns. Because if we put 5 columns for card ID, well then what if someone had 6 cards? What are they going to do? They're not going to be able to have a 6th one. So what we do is we put the user ID in the card table. Which points back to the user ID in this table. So now, if we made specific examples of this, let's say we had this guy here. Let's give him a top hat, yeah. Alright. So we got this guy right here, and his user ID is 63. Just random generated number by the database. Well, we also have cards over here. So we have this credit card. We have this credit card. We're actually drawing our cards here. So we have the barcode and the name and the codes and all that crap. And then we have this card over here. We make a connection. We want all of these to point back to this guy. So we give it a user ID. We could say the user ID 63. 63. 63. So now we know that each card is owned by the user with the ID of 63, which we can figure out is this guy. Whatever his name is, we can join that. So now we store a one-to-many relationship in two tables where the many side gets a foreign key to the one side. And if you don't know about foreign keys, that's fine. Basically, in simple terms, a foreign key is just that ID connection. This user ID is a foreign key that points to the user ID in the main table. Foreign key points to the primary key in the primary table. This is also said to be a parent-child relationship. This would be the parent because every single child has to point back to the parent. That is how we store a one-to-many relationship in a database. So how would we know if we had this example, we had comments, a comment section on a shopping website. So you're allowed to leave a review. Yeah. Let's say you can leave a review. And we had this table, this table set up. We had the users, and then we had the reviews. And we had a user ID, and then we had a review ID. I just give that to every single table. I give every table an ID. Then we have the username, and then we have the actual review. So the user has a username, the review has the actual comment, and we could also say, we have a review title. So we could say like, oh, this review is this product sucks, or this product's really awesome. And then we can have a paragraph saying why that product's awesome, for example. Right now, this is not properly designed because there's no connection between the user and the review. Because if we look at the review table, who posted the review? It doesn't say. All we have is the review ID, the review, and the review title. It doesn't say who posted it. So if we put a key, a foreign key that points back to the user table, that would say that is the parent, the person who posted that review. So we could have a user ID which points back to the user ID in the primary table. Is this a one-to-one relationship, or is this a one-to-many relationship? Well, we could have multiple reviews, and each one would point back. So we could have another review, and we could have the same ID. Let's just think of some examples. Let's say we have the review ID of 6, and then the review is awesome or good, and it's by the user ID of 62. Well, then we could have another one with the review ID of 7, and it could say, great. And then we could have it from the user ID 62. Well, these are both from the user ID 62, so we could say this is a one-to-many relationship because multiple reviews point back to one user. If we wanted it so a user can only post one review, well, then we need to put the review ID in the user table. So now we have this sort of like this double connection thing here. Because this review ID connects it. So it's saying only one review ID can be from the user. And honestly, this could probably be improved because the review is not necessarily connected to the user that directly. For example, if the website is solely for giving one review, well, then we could give it a review ID. But that might not be the best example simply because the user might buy multiple products and each review could have a product ID, you see? So, I mean, it kind of gets complex and you just kind of have to study. But the review ID would probably be best to make it a one-to-many relationship because it wouldn't really make sense to have it as a one-to-one relationship. We want it as a one-to-many because multiple reviews for multiple products can be given. So this points to a product, this points to a product, this points to a product, and they're all by a specific user. Alright, so yeah, that's just some basic design concepts that you will need to understand. When you have a one-to-many relationship, just store it over two tables and give a foreign key to the many side pointing back to the one side. Before we start the many-to-many relationship design, I wanted to talk about parent-child relationships. So we have, when we design these relationships, a table is always the parent and a table is always the child. And when we're talking about keys keep things unique, and they're used to connect tables that are related. So every table has a key that keeps it unique. When we create a foreign key, it references that primary key in another table. So the primary key is the parent. The foreign key is the child. child points back to the parent. It inherits the values from the parent. For example, the parent's ID is 86, then the foreign key pointing back to the parent is 86. It's the child. So in a one-to-one relationship, where we just store everything in one table, which is the most practical way to do things, we don't have to worry about primary keys or foreign keys. We just have one table, and that's all we have. Then we have columns within this table. So we have the user ID, the password, the username, the whatever else. All those are just columns within a table. We don't have to worry about a parent or a child because we're not making any relationships across multiple tables. But when we get to one-to-many, that's when we have this table pointing, or it has many children. So you would say this is the one side, it's the parent. Then we have each of the parent's children. These all point back to the parent with a foreign key. So if you think of like comments on a YouTube video, every comment has a poster or a user account of a person who clicked post a comment. That means that the commenter is the parent and the comment is the child. Another way to think about that is if you were given a comment on YouTube, you can figure out who posted that comment. That's because the child always points back to the parent. Now, if you look at a user account on YouTube, such as Caleb the Video Maker 2, awesome channel, check it out and be sure to subscribe. Well, you don't necessarily know every single comment that that parent has given. There might be a feed in there that says recent comments, but when we look at the child, we always know the parent because it inherits the values. But the parent doesn't inherit anything from the child. Think of like in real life, you can see a married couple and you don't know if they have children or not. But if you see a little baby, well, you think, alright, that baby has a parent or parents. That's the similar idea with database design. Think of this wall here between the parent and the children. The children inherit values from the parent, such as the foreign key 87 that tells us who the parent is. That is important. I know it seems like, okay, who really cares who's the parent or child? Just get on with the database design, you noob. I'm going to unsubscribe. Well, this is important because when we get to understanding how to design each relationship, we need to understand where we put the foreign key. Which table does the foreign key go into? That is decided by the child because the child always has the foreign key that points back to the primary key. So, user ID, primary key. User ID, foreign key. Points back to the primary key, user ID. So foreign keys always go in the children. Primary keys go in the parent. When it comes to many relationships, we have problems with parent-child relationships, and that is why we can't store many-to-many relationships in a database. And that's what we're going to talk about in the next video when we talk about many-to-many relationships specifically. But just know that when we have an entity, I want you to think of whether or not it would have a parent. A lot of the times it would, but other times not so much. But if you think of an order for a store, an order needs a parent because an order is when you buy product. Who is buying it? Someone has to buy it. Otherwise, it wouldn't exist. The child would not exist without the order. So let's relook at this. This is the user, and this is the orders. We can't have a child without a parent. Logically, it just doesn't make sense. So if there's no parent of the order cannot exist. We need to keep that connection. An order needs someone who bought that order. Hopefully that's kind of making sense. So yeah, just keep in mind parent-child relationships. I'm not trying to repeat myself, but I'm trying to repeat myself so you get this drilled in your brain. Foreign key goes on the child, primary key goes on the parent. And soon we'll be talking more in depth about keys. So just for now, memorize primary key and foreign key. Primary is the user ID. The foreign key is a reference to that user ID. It's in a foreign table and it points back to the original table. This video will be about many-to-many relationships. Boom! And we're talking about designing many-to-many relationships. So, I said a couple videos ago that we have problems when we design many-to-many relationships. They don't work out right, they don't, and I mean, I never really explained why. Well, this video, I'm going to explain why. Let's think of a good example. A college. A class can have many students, and a student can have many classes. So we have two entities we have to worry about. We have the class, or let's just pluralize it because it makes more sense. The classes, and then the students. So let's just think of an example of a way we would try to design this, and it's not going to work out right, but we'll just try. All right. Here we have a classes table. And we have a specific class, such as math. Math 101, whatever, really. So we have math. You can't even read that. My handwriting's so bad. So we have math 101. And then we list all of the people within this class. So we have student number 1. And then student number 2. And then student number 3. Alright, well, we can try that, except what if a student drops out? Well, then we have a null value, which we don't want to have those if possible. And what if we need 4 students? Well, that's not going to work because we only have 3 columns. So, how else could we do it? Well, we could try just having students. Well, then every single column could have, like, 100 students, and we already learned about the atomic rule. We only want one column to store one value, one student. So what do? Well, okay, that's not going to work. Let's try over here. Let's try it on the student side. We have a table for students. So we have Jimmy, and he's taking the first. All right, yeah, let's list the columns. So we have the name. And then we have class number 1. And then we have class number 2. And then we have class number 3. Well, that's cool. What if he wants to take 4 classes, though? Well, then we have to add a new column. And let's say someone psycho crazy guy takes like 20 classes. So now we have it all the way down to class 20. And then a new person comes to the school, and he only takes 1 class. So now his first class is like math, and then there's 19 columns for that guy who are empty, because we have to have the columns for every single person. We think of it like this. If we drew that out so where you could see it better, we would have a table, and then we'd have the ID of the person, and then the classes. So we'll just put like class 1, class 2, class 3, class 4, class 5, class 6. Let's just leave it at that. And we'll just kind of make rows for these. And we have a new guy sign up. So we have a guy with the ID of 6. And his first class is math, right? And then his second class is geology, and then Spanish, and then fashion, and then biology, and then chemistry. And then we have a new guy come, and his ID is 8, and he only takes science, right? Well, now we have null, 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 empty, nothing. We wasted all of this space. And you can assume that's going to keep happening. So that's wasted space in our database, bad design. So how do we possibly do this? Well, the trick is, because we think of, if we're trying to think of like parent-children, who's the parent in this situation? Well, a class has multiple students, so that would make the class the parent and the students the children. But a student can have multiple classes, so that would make the student the parent and the classes the children. So how is it that this is the parent and this is the parent at the same time? That means this points to a child and this points to a child. So this parent is the parent of this parent, who is also the child of this child. Which, that just like blew my mind. I don't even know what's going on. So, the way we do this is we break it up into two one-to-many relationships. So this many-to-many is going to become a one-to-many, and then a second, alright. Okay, just for you guys' information, these colon things, I think the correct way to do that is many to n for like the n keep going on. But just don't worry about that. We'll talk about that in upcoming videos. I'm just writing that for my sake. So we're gonna break this up into one and many, and then another one to many, but the other way. So that is how we fix that problem. Alright, so let's implement that with classes and students. What we need is what's known as an intermediary table or a junction table. They're both the same thing. I'll write that out so you can hear me. Intermediary or a junction. There's also like 50 other names for this table, but I mean, just intermediary table will work fine. So, intermediary. And what that is how we connect our tables. So we break this up into a total of 3 tables. So we have the intermediary table, which is the one I just talked about, and then we have the students table, and then we have the class table. So, class, student. This is the intermediary table. So we have a one-to-many relationship going this way, and then we have a one-to-many relationship going this way. So, one, many, one to many. I know that seems a little confusing at first, but trust me, it'll make sense once we start explaining things more. So we have one to many, and this is the intermediary table. Alright, so let's just draw this connection so we kind of can visualize this a little more. Kind of like split this to see how it works. So we're storing the many side of both relationships in one table. That's because we know that a one-to-many relationship is spread out over 2 tables. So 1, 2, 1, 2. The 2, it's being shared. So what would we name this? We would say, like, we could name it class students, for example. And these, we're going to have foreign keys that point back to the class and the students. So now that we kind of understand what it looks like when we draw it, let's give specific examples to illustrate this. Actually, like what it would look like, whatever. Alright, So let's say we have our classes over here and our students over here. Okay, so first things first. We have math. We'll just keep it simple. Math. Science. I mean, obviously it'd be more in-depth, like Math 101, Math 205, or 1200, or whatever. And then we have English. But just for simplicity's sake, let's say these are the only 3 classes in the college. Alright? Then we have all of our students. We have Caleb, we have Celeb, we have Caleb, and then we have... Man, I'm so conceited. All I ever talk about is myself. Alright, let's get rid of my name. Let's go with Johnny, and Jake, and Sally, and Claire. Oh, not Claire. Alright, so here are all of our students for our class. Classes, students. We connect these in the middle. So first things first, we give them all an ID because that will be our primary key. So we'll just give these random assigned numbers, which is pretty much what a primary key is, a surrogate primary key. So we'll give this one 63. This is something our database would do for us. This one will be 75, and this one would be 89. Hopefully you guys can see that clearly. We'll do the same thing over here. So John will have the ID of 8, Jake the ID of 17, Sally the ID of 16, and Claire the ID of 4. Just kidding, 666 because she's evil. 666. I'm just kidding. We'll just go with 6. All right. Now we use the intermediary table to connect these IDs. So we have this table here. We have 2 columns. We have the class ID, and then we have the user ID. And then if you wanted to title these tables, we can make it classes, class students, and students. It's an intermediary table. What an intermediary is, it's something that connects 2 things. It's like it allows this table to talk to that table. So it's a connection between these 2 tables. We put the ID of the user with the class that they're taking. So let's say John is taking English and Science. We would have 8, 75, 8, 89, writing really big, I'm going to run out of room really quickly. And what this does is, using this intermediary table, we can figure out that all of these user IDs point back to a specific person, and these IDs point back to a specific class. We are not repeating data because we need to know the user of this class ID. This is a foreign key pointing back to one specific value. So that means if John decided to drop out, well then we have foreign key constraints to get rid of these. That way we don't have to worry about incorrect data or users. I guess this should, I'm sorry, this should be like students, sorry. But we don't have to worry about students who, we don't have to worry about students being enrolled who don't exist. So that is the solution to a many-to-many relationship. This video is getting really long. So Sally could do the same thing. We could say 16 and then 75. She's taking Science. Claire, she's taking math. We can keep going on if we really wanted to. We can make this table as big as we wanted. And basically this is the easiest, best way to use as much databasing resources, storage, as possible, as well as now we solved the parent-child relationships. That's because we have the parent over here, we also have the parent over here, they point to the child table. So this child table becomes the child of both of these parents. Sort of how in real life, every single person has two parents, and the person is this entire row. Okay, so yeah, applying that to this, the parent is the class and the student of the class, and the child is a row where we have both the class and the student. This right here needs to be unique. It's an individual child. We can't have 663 again, because that's saying Claire is taking science and math. Claire's taking math and Claire is taking math. That doesn't make sense. So this right here is unique 63 to 6. You can't have it in there twice. So the child is an individual connection between the parent and the other parent. So yeah, that is how you properly store many-to-many relationships. And I know all these relationships are kind of complex and you don't really understand with like a stupid chalkboard. But like I said, we will be getting into on-screen computer videos in the introduction. I said that in the introduction. We're not going to do that in the introduction because that wouldn't even make sense. So yeah, we will be explaining these concepts and then we will be applying these concepts to actual databases once we get through all of the database concepts. This video will be a summary of all of the relationship garbage that we learned, and basically this video is just going to be like all of it in one, and it's going to be awesome, and it's going to make a whole lot more sense after this. So the very first thing that you need to realize when it comes to relationships is that there's not always a defined relationship for every circumstance. And it's sometimes it's something that you have to decide on your own. So in my old database design series, which if you want to check that out, just go to my YouTube channel, a lot of people were confused about, okay, is a student to class, is that a one-to-one or one-to-many or a many-to-many relationship? Well, that's something that you're actually going to have to decide on your own sometimes. So you have to think logically about the application of the relationship. So let's think of the example of a class and a professor. What kind of relationship is that? I don't know. Let's try to find out. So we have the class, and then we have the professor. People would ask me, like, okay, what kind of relationship is this? Well, it depends on the application. If it's, it can literally be all three. It just depends on what you need for your application. If it's a one-to-one relationship, that means a class can be taught by one professor and a professor can teach one class. If it's a one-to-many relationship, that means either a class can be taught by one professor and a professor can teach many classes, or the opposite, a class can be taught by many professors, but a professor can teach only one class. Or it can be a many-to-many relationship. A professor can teach multiple classes that can be taught by multiple professors. So it depends on the college, because some colleges are going to allow a class to be taught by multiple professors. Other colleges are not going to allow that. So that depends on the application of the database. If I'm building a database for a college that does allow multiple professors for a class, that means it's a many-to-many relationship because many professors teach many classes. Many classes are taught by many professors. Right, so when it comes to designing one-to-one, one-to-many, and many-to-many, I'll show you how to do all three of those for a class to professor. Alright, so if we have one-to-one, we could have, for example, we could have the professor, right? We could have a professor table. I don't even know how to spell. We'll just put prof. I don't know if there's two F's. I don't know. Who cares? Professor table, right? If it's a one-to-one relationship, we could have the professor ID, the name of the professor, and then we could have a class. That's the class that they teach, and it's the only class that they teach. That class is only taught by that professor. that's how you store a one-to-one relationship. And typically you're not going to do that with another entity. When it comes to like a name, you typically will do that because the name is just assigned to that person. A class can typically professors can teach multiple classes unless you're some kind of adjunct teacher. But class, in this case, is a one-to-one relationship. If we wanted to make it a one-to-many relationship, well then we would break off class here, get a new table, class, we'd have a class ID, and here we could put more information about the class. So we'd have the class name. This is the most common way of storing information on two tables. You very rarely store a one-to-one relationship over multiple tables, but it is possible. We talked about that earlier. And we'd have class name, and then we could have more information about the class. And then we have a foreign key, class ID. That would make this the parent because class ID points to class ID. If you wanted this to be the parent, well then we would switch that. We would make professor ID, which would probably be the most logical way to do that. But you have to keep that in mind because it can be a one-to-many direction, a one-to-many this direction, or it can be a one-to-many this direction. And obviously, typically the class is going to be the many side because a class can be taught by a professor can teach multiple classes. That means the professor is on the one side, the many is the class, which means we need to give the professor ID on this side. So the prof ID is a foreign key referencing the prof ID in the professor's table. That is how you draw a one-to-many relationship this direction, one-to-many, parent-child. Now, if we wanted to make that a many-to-many relationship, we would actually have to break this up even farther into 3 tables. So now we have the professor's table, and then we have the class table, and then we have the probably class professor's table, which is the intermediary table. So we have this table here, this table here, this table here. This will have an ID, professor ID, and this will have an ID, class ID. Then you reference this in this intermediary table where we'd have professor ID of like 6 with the class of 7, professor ID of 6 with the class of 8, which is basically saying this professor with the ID of 6 is teaching 2 classes. Now, when it comes to IDs for this table, this whole thing can be an ID in itself, or if you want, you can give it a new ID to say class professor ID. And that's kind of unrelated, so that's pretty much, we'll get into that later, but that is pretty much the sum of designing relationships. One-to-one is typically in one table, one-to-many is 2 tables with the child having a foreign key pointing to the parent, and then a many-to-many has two parents with the intermediary being the child pointing back to both of the parents. Hopefully that is all crystal clear and awesome, because now you literally know how to design every binary relationship in database design. And by binary, I mean a relationship between 2 tables. So you can have a binary relationship, which we talked about. There's one-to-one over 2 tables, there's one-to-many over 2 tables, and there's many-to-many over 2 tables logically. But then we have to break those up into the best way to store those in a database. But this is basically binary because we're talking about 2 entities. A class and a professor. A student and a class. You can have relationships between multiple tables, but that is something, multiple entities, but that is something we will have to address in a future video. Oh, didn't see you there, guys. Anyways, in this video, we're going to be talking about keys. So, a key is not something you use to unlock a door. Keys in database are something else. A key keeps everything unique, basically. That's the easiest way to remember what a key is. So when you think in a database, we kind of structure things in tables. I mean, we don't kind of do that. We do. We do that. We do that. Ha 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 ha. Anyways, if we have a table here, we have the columns, which are the attributes of each thing. So, like, let's make it a user account table, because that's always the easiest example. So we got user. So that's the title of the table. Now each individual row within this table is going to be a new user. Each column is going to be a thing about the users. So the columns can be username, first name, last name, password, and email. Just for an example. I mean, you can really put whatever you really want in there. Well, a key is something that is going to separate this row from the rest of the rows. So in this example, think of the things that could be duplicated. Think of all the possible values that you could put within one of these columns and think, is it possible to duplicate it in your application? I mean, yeah, it's possible to duplicate it if you allow it to be duplicated, but what naturally should not be duplicated? So typically when you sign up for a website or a game or something, they'll ask for your email, right? Now, when you sign up, you put your email in, you typically have to go to your email and click like confirmation or something to register your email so they know that it's a genuine email account. Basically just so they can have your email and they can send you emails and stuff, but yeah. That is an example of what we could use as a key. That's because every single row within this table should have a separate email. Some websites allow you to use the same email more than once. If that's the case, then this would not be a good key. This kind of key is known as a natural key because it's naturally already in our table. We don't have to define a new column just for the sake of a key. And we'll be getting into more of that in upcoming videos because I'm doing a whole bunch of videos over keys so you get them like really good. All kind, like I'm going to go over pretty much everything. But anyways, if you make it so where only one person can use a certain email, and that email can only be used by one person, well then that could be used as the key. The way that works is it basically, let's say we have the emails 123 at blah blah blah, ABC blah blah blah, XYZ blah 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 blah. And these are 3 separate rows. Well, this is going to let us know which person we're talking about. And like now, if someone has the same first name and last name by chance, let's say we have 2 Caleb Currys, Caleb Curry, Caleb Curry, we can't use the name as a key because 2 people have it, and it's going to confuse us because, okay, do we have 2 people with the name Caleb Curry, or is one person Caleb Curry in the database twice? Is that an error on our part, or what? So we can't have the key be in there more than once. So it's never, it's always unique is what I'm looking for. So the key is always unique. You see it? You see it? You see it? Yeah, I think you can see it. Alright, so what is another example of a key that we could use in this table? Let's get rid of this email. Let's say we're not using the email anymore. And let's say the website allows multiple emails from different people. So like if my mom signed up and then I wanted to sign up, I could use my mom's email. So we have 2 people from the same email. That's an example of some websites that allow you to do that. But I mean, Not tons of websites do that, but it is a possibility. It all just depends on what you want to do. It's up to you because, well, I guess it's up to the, if you're making a database for yourself, well then it's up to you. But if you're making it for someone else, then you get their rules and you follow them. Let's think of some other ones. Alright, well, email, let's just say it's not email. Password. Well, that's really a bad one because passwords, they're not necessarily unique because two different accounts can have the same password. And if you didn't allow that to where they could have the same password, you'd try to put in a password for your new account and it'd be like, oh, this password is already in use. And then you're like, oh. So then you can try that password on other accounts and try to hack into people. So that would not be a good database design, obviously. So password, that ain't going to work because not every password is unique. First name, last name, it could possibly work, but it's really bad. Maybe first name, last name, and middle initial or middle name. But even that, there's people with the same first name, last name, and middle name. So, and that's first name won't work, last name won't work, and the combination of first name and last name won't work. And yes, keys can be a combination of two columns. We'll be getting into that too. What we have left is username. Well, a username is a generated word that is used to represent your account. It's typically not a name or an email. It's something like Caleb123 or whatever. You know what I'm saying? So then when people talk to you, they're talking to Caleb123 rather than Caleb Curry. Or they could put the name there, but some websites use usernames, or some games use usernames, or programs use usernames. So you have a username and a password. Well, a username is always unique, because if you have two people with the same username, when you try to sign in, how is the database going to know which one you're trying to sign into? You know, they have to be unique. So hopefully that kind of makes sense. That could be used as a key because we could have the username Caleb C, and then we could have dog123, and then pie. These are three different people. All the other stuff, first name, last name, password, email, they point to that key. So we have a first name and a last name, a password, and an email for the user with the username Caleb C. That's how the key works. We have a first name, a last name, a password, and an email for the person with the user. I'm sorry. We have first name, last name, pass, email for the user with the name dog123, and then we have a first name, last name, password, and email for the user with the username pie. That's kind of how the key works. The other thing is that the key should never be changing. So the second thing, never changing. Now why is this? Well, that's because when we create keys, we use them to kind of structure our entire database. Everything points towards the key. In the last example we had, I'll just draw a key for representation. Let's say this is the key, and we'll just say it's the username, right? Well, every other column points back to that key. So we have the name of the person, we have the password, and we know that these are pointing to this specific person. If we got rid of this key, and now we have two people with the name Caleb, with the password pie, well now, are we talking about the same person? Or are we talking about two separate people? Or what? We don't really know. But now if we give it keys, I have a key, let me get that key back. So this, let me see if I can draw a key right. Probably not. Ugh. Close enough. Alright, here's our key. Now we know that this Caleb points to this specific person. We could have it be the username. Or you might often see numbers like 72, the ID, which we'll talk about that too soon. Now if we have a separate key, like this, well then that is a different person. So we could have this guy have the username CalebIsAwesome72. This guy be like SexyChick74. See what I'm saying? So that's kind of how the keys work. We never want them to change because then it's confusing because all of these objects are part of this key, basically. This key is used to define uniqueness. Well, if we can change it, it questions the integrity of our database because between tables, we connect things by keys. So let's say this is a user table, this is a comment table. If we have it to where we can change the key, well then this connection is, you're going to have to update this connection all of the time. Now if we have 50 tables connected to this user table, I'm just going to draw 4, just to make it simple. I won't draw all 50. Well now, when we update this key connection, so we have a comments by a user, we have sales, we have friends, we have messages, whatever, it doesn't really matter. Well then we change this key, well that means every single one of these connections are going to have to update. That requires a lot of work from the server. Make sense? So we don't want them to change because we don't want to have that extra work from our database. So that's one thing. Unique, never changing. The other thing, these are just 3 general rules. There's some other suggestions and stuff, and I'll get into that soon. But the other thing is never null. That means empty or no value. So when we have a table and we have a key value, let's say we have a user ID. This guy's 6, this guy's 5, this guy's 4, this guy's 38. It doesn't really matter the order. And then we have their name, and then whatever, blah, blah, blah. Well, we don't want it to where we can have a blank ID and still have information. Like Sally. This Sally doesn't have a key. That is another thing we do not want to do with our keys. So here are the 3 main rules, and we'll get into more in upcoming videos. But a key should always be unique, never be changing, and it should never be empty. You should not allow a row without a key. This video I wanted to talk a little bit more about introduction to keys, although I'm going to go just a bit off topic, and I'm going to talk about indexes. So I don't think we talked much about these in this series yet, but we are going to be talking about an index. Alright, so what's an index? I'm not going to be explaining every single detail of indexes because we're not really talking about indexes in this video, we're talking about keys. So I'm just explaining enough so you understand how this relates to keys. So think of an index. Best example I have is a book. So if I have a really awesome book like physics or something, well what I can do is I'm like, oh, I want to know about this. I can flip open to the back, right? And I can travel to the index. And I'd be like, oh yeah, ooh, that looks nice. Page 7,832. And then I can read about that. Well, that's a lot quicker than being like, oh, I want to know about this. Page 1? Not on there. Page 2? Nope, not there. No, not there. Oh, nope, not there. No. Nope. Nope. No. And keep going through the entire book until you find it. That'll take forever. Another good example is a phone book. When you go through a phone book, you have everything's alphabetic and it has the data right there. So when you think of an index in a book, it points you to the data, whereas a phone book, it just has the data there. You can be like, oh, I'm going to go to the letter G, find grandma, and call her. Right? That's kind of how an index works, and it's very similar for a database. If we had a table, and it's like a user table, boom, 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 user. And let's say we have 6 billion rows in this. That's a pretty crazy number. And we want to find everybody with the name Caleb. Just Caleb, yeah. We want to find everyone with the name Caleb. Well, without indexes, basically the database is going to go, row 1, does it have the name Caleb? No, it doesn't. Row 2, does it have the name Caleb? No. Row 3, yes it does. We'll put that back in the return statement. And then it goes through every single row within the entire table, which can take ages. So if we give it an index and we order that data in a way that the database knows how to find certain, like it could know exactly where the C's are, well then it can go straight to the C's, grab all the Caleb's, and boom, it's done. It's like super fast. That's kind of how an index works. Well, what's that have to do with keys? Well, when we define a key, it's actually a type of index. That's because keys and indexes are used for select statements, where clauses, and joins. So if I could do something like select everything from users, for example. There's just like a SQL example. I mean, it'll vary from whatever programming, like relational database management system you use. But this is a general example. And then I could say, where, now this is where I specify, holy cow, sorry, dropped the weight, it's holding my books. Anyways, I'm selecting all of the columns, and then I want to select every column where first name has the value Caleb, for example. Well, that's how we would do this. This right here, this whole where thing, well, it's best to have an index for that. Another thing we commonly do are joins, which is basically combining two tables. And I'm not going to go into all the syntax for all that. Basically, if we have a table over here, users, and then a table over here, comments, and we want to generate a new view where we have all of the comments from a user and all of the information about that user, we could have a new generated view, and we can join these statements. And how does it know how to join it? It uses the key, right? So if we have a primary key, and let's say we used username. So the key, I'll draw the key here. The key is username. Well, how would we join it? We would say, I want you to take this table, and then combine all of the rows where the username is Caleb Curry over here, and the username is Caleb Curry over here. So that way it knows all of these comments are from Caleb Curry, which we can assign to that user with the name Caleb Curry. Or you might often see it with like an ID number. So it could be like ID 6. Take all the comments from the user with the ID of 6, join it with the, take all the rows with the user with the ID of 6, join it with all of the rows with the user of ID 6, and it combines them, individual rows for each ID. When we make a primary key, or just a key for now, well, we're defining an index so the database can easily access the order of our data and combine things. So that is how indexes relate to keys. Key is a type of index. There are all kinds of types of indexes. Look up tables. So what is a lookup table? Well, I have to kind of explain something else first before we're going to get into this. So just kind of relax and take a good look. I'm going to erase this so I can have some room. So let's say we have a membership table or membership database, and we have a user table or members table, and within that we have like a membership status, okay? And let's say there's like 10 options, I guess. So you could have like bronze, silver, gold, platinum, titanium, and then like not a member, or like trial member, or special member or member above all members. I don't know, I'm just kind of making stuff up. Anyways, some people will create what's known as a lookup table. So they'll have a table over here with every single option for the membership. So we could have the memberships, and then within here we would have each individual row is one of the membership statuses, right? So we have like 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just going to go with 9 because it can't fit anymore. 9 individual rows. And then so that's one column. The ID, for example, which, I mean, we could use a different key if we needed, but for this we'll just use an ID. And then we have a column to say what the membership status is. So we could have like gold, silver, bronze, platinum, and so forth. Now, we can have a members table and then a column within this member table can reference the key of the membership. So remember, like 1 or 2 videos ago I talked about how keys make connections between tables? Well, this is how that's done. Here's an example of a connection using a key. What we would do is we would have like the member's user member name or their ID, for example, and then we have their first name, last name, address, phone number, billing type, whatever it is, and then we would have a column, membership, you see? And within here, let's just say, for example, we didn't have this table. This was gone. We just had this member table. Well, when we have 6,000 rows within here, the membership type would get repeated lots and lots of times. We would have like gold, 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 bronze, platinum, 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 bronze, gold, platinum, bronze, and go on for all of the rows. And that would work. That is a possibility for your database. I'm not saying it's going to cause your database to explode or you'll get fired or anything. Well, unless you're told not to do that, you might get fired. That's a possibility for the database design. Now let's think, what kind of relationship is this? One member can have one membership, and a membership can have multiple people having that membership. So it's a one-to-many relationship. The one side is the membership. You'd have one of these, and then you would have many people using that. So that means, if you remember from the relationships, we need to take the key from this one and put it over into this table. And now, if we add this new relationship in, we don't have all of that repeating data because all we do is reference one individual row. And there's some other benefits to that, which I'll explain in a second. So now we could be like, rather than gold, 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 silver, bronze, platinum, we could have 1, 1, 1, 2, 3, 4 for all of our rows. And we'd still have individual information like Caleb, Jimmy, Jake, Sally, Sammy, and Sarah. Well, when we do this little connection thing, we have a new connection between these tables. We're taking the key of the membership, which is this column right here. So here's our key. And we are taking that key and we are moving it over into the member table. So now this column right here, within the member table, points back to the key of the membership table. This is known as a foreign key. Now, this will help protect the integrity of our database. That's because there's only 9 possibilities for the membership, and if someone puts something else we could flag an error. The other thing is we can have it to where it will not accept an empty value. And then, if for some reason we decide to change our, like let's say we wanted to change silver to like, I don't know, diamond, well then we could change it here. And because this value is not over here, it's only a reference, it will automatically figure it out because you see the key never changed. The key is still 1. So 1 still points using 1. So this connection is still here. The value, oh I'm sorry, I guess it should have been 2. Whatever. You get my point though. We can change the name of gold. We can make it epic. If you want an epic membership. Well now, we didn't have to change 6,000 rows within our member table. We only had to change 1 row within our membership table. And all these connections stay the same. So the IDs help create better connections between tables, requiring less maintenance for our database. And it also protects our integrity because we don't have to worry about incorrect values within the membership because it's all connected back to the membership table, which we change from here. So when we update Epic, it updates every single instance of Epic within our entire database. Or it gives us an error or something. We can set it using what's known as foreign key constraints. Foreign key constraint. So because we're using what's known as a relational database, which is the type of designing we're doing right now, we have relations, tables, and everything is connected across the database. It's not all stored in one individual table, but to protect our integrity of our database, we create connections between keys. That way, we don't have to worry about incorrect data. So, what do keys... Oops, I dropped my chalk. What do keys do for us? Let's write it out. Well, first thing, they protect our integrity. I made a video over integrity, so if you want to check that out, be sure to do that. So they protect our integrity. How do they do that? Well, we don't have to worry about only some values updating. If you remember, we had the members table, and when we updated gold and we named it Epic, it updated every single row within the member table. So it protects all of our values, so it updates, less maintenance for us, less incorrect data. What else does a key do? Keeps everything unique. And you might have saw that in the member table, we used the key number 1 multiple times. We had 3 people with the member ID, the membership ID 1. So 3 people had gold, for example. Well, it's still unique because they're still only talking about one individual gold. Over here in our membership, we had gold was one of the options. We could have 3 people Alright, you see? Oh, forgot our arms. These 3 people can all have a gold membership, and it's still unique because we're only talking about one individual value with 3 references to that value. If we got rid of these foreign keys and we just had to say what membership status they had, well now this guy's going to be gold, this guy's going to be gold, this gal is going to be gold. So now we have 1, 2, 3 times. That gets rid of the uniqueness from the key. So it protects our uniqueness. It improves our speed. So basically improves functionality of our database. I'm just going to put function, I'm running out of room. And it does a whole bunch of other things. Basically, it makes updating easier, so less work for us, because we don't have to go through manually and check every value. We can just update that individual value, you know? The other thing is it allows for added complexity. This is a long one. Oh, my hand's getting tired. Oh, okay. I doubt you can even see all that. Okay, so here's just some examples. I'll show you how we could say it allows for added complexity. Let's see. I'm going to redraw the example we had, but I'm not going to draw it super in depth, so don't worry. It won't take that long. We had members, and then we had the membership. All right. Now let's focus on this membership table. Let's make it a little bigger, actually. What we had earlier was we had an ID, we had 1, 2, 3, 4, and so forth. And then we had the title of whatever they are. So if you wanted to draw this better, you could put the column headers, so we could have like ID, and then we could say name of the membership. And then we could title the table, we could have it membership. Yeah, so forth. Well, what we can do, we can have added complexity because now we can add a new column and we could say more about the gold membership. So we could say price, and we could have a monthly price of $60, for example. If we didn't do this whole lookup table thing and we put it all within our members table, let's see how that would look. Let's try it. Alright, let's have the members table, and let's not even have a membership table. Well, now we have the guy with the ID 7, 89, and 3. And we'll have their names be Caleb, Tommy, Tracy. So those are those 3 people I was talking about with the gold memberships. Well, what membership do they have? We got gold, gold, and gold. Now, how much does that cost them? 60, 60, and 60. Just with this little example of 3 people, we already have 4 unnecessary values because we have repeating data. We have G, and then we have G twice more. We have 60, 60 twice more. That eliminates the functionality of our database because we're having tons of repeating data. So you might think the best way to do this is get rid of this price. Well, now we get rid of the complexity of our database. And sometimes complexity is a good thing because it allows us to store more information. When we use the when we use the lookup table, we can just have that as another column. And we could put more things. We could have another column saying, how long does this membership last? We have another column saying, I don't know, special perks, or what can you use within our gym, or what can we use? And are we allowed to bring friends? What's the price for friends? We can do all that kind of stuff within this table and just reference that within the other table. It's only a set number of options, so we reduce the repeating data. If we wanted to do it all, well, we'd have to put each individual column, and we'd get tons of repeating data. You know what I mean? Yeah. So that is an example of how because that would take forever. So that's very common. It's common for things with a set number of options. So like membership type, there's only so many options you can have. States sometimes. Sometimes people do it for sex, male or female. Some people do it for I can't think of anything else right off the top of my head. But anytime there's a set number of options, they will often put a lookup table with the ID, the name of that option, or what that option is, like gold, silver, bronze, or male, female, or California, all the other states, Wyoming, Texas, Russia. I'm kidding. Well, then we only have a set number of options. So that's the then we could put more information about it. We could say male, and then like what the male is allowed to do on the website, or anything that allows for extra complexity for our database. In the last couple of videos, we've talked about all of the characteristics of keys in general. We talked about the word key. In databasing, keys are the key to success. Anyways, this video we're going to be talking about specific kind of keys. Because all of the last videos were kind of concepts, but now we're going to be talking how do we actually implement that into a database. I understand that we want keys and we want references from table to table and we want it all to be connected, but how do I do that? Well, the main two types of keys that you're going to hear are known as primary and foreign. And actually, we're not going to be talking about these two kinds of keys in this video. Surprise! We're going to be going a little bit broad, a little bit more broad. So when you're like a beginner and you're learning database design, you'll probably learn that these are the two kinds of keys. When you want to learn more advanced database design, you'll learn about different categories of keys. So before we get into these two, which if you guys haven't heard of those, just hold up. If you have heard of those, keep holding up. We're going to be learning about what's known as a super key. Now, for some reason, I think this is one word with no space, and I don't know why there's no space there. So if someone knows, if like one of you guys watching know, let me know, because I really want to know. It's driving me crazy. The other one that we're going to be learning is candidate key. Alright, so before we learn about the candidate key, let's just focus on the super key. So I'm just going to erase this. Alright. So what is a super key? Well, a super key is any number of columns that forces every row to be unique. Now, if for some reason your table is structured to where you can't have every single row be unique, you need to consider adding some kind of column to enforce uniqueness, such as an ID, or some you need to make sure that everyone using the database understands how that table works if it's a special case. But generally, every table you will be able to make unique. Now, when you work with databases, you'll often see IDs, so like user ID. This is a type of key. Then you also will sometimes find keys such as like username. The difference between these is that this one's kind of just made up for the sake of the database. User ID of 748. What does that mean? Absolutely nothing. It's just a number. Username actually has some real-world connection. We'll be getting into the difference between these in an upcoming video and which one will be best to use for which situations. But as for now, we'll just be using kind of natural, practical columns that are already in the database rather than IDs. But the same thing can apply with just like an ID field or a column. So let's learn about the super key. Super key. It's like Superman, but it's a key. Just like a giant key that just goes and breaks through doors. It doesn't even use the handle, it just breaks through doors. Anyways, let's learn. Okay, let's say we have a table here. Big table, right? Now I'm going to put some columns in this table. That is not straight enough for me. Close enough. Now it just looks worse. Whatever. let's say we have a user table, just because I always think that's the absolute easiest thing to use. And we're going to have a username, email, password. Then we're going to have first name, middle name, last name, and then we'll have birth date. So every single row within this table is going to need a value for each one of these columns. I know this is really bad handwriting, but it doesn't really matter how it looks, just understand the concept. There, now it looks a lot better, I know. You're welcome. Now you can actually understand what's going on. Okay. Some instances for databases, you will allow people to put in blank values. So for example, if someone doesn't have an email, for example, we could make it optional. That way some people have null or no value at all, other people have values. But for this case, I'm going to say everything is required because let's say you use your email to sign in or to verify your account. Dang it, I always drop my chalk. How do we make sure that every single row is talking about one entity and every single entity only has one row? Everything is unique. If we have a person, I'll draw a little guy over here, right? And he wants to sign up for this website, so he goes to this website, here's his website, he puts his information in, and that information goes into a table, right? He probably won't actually have access to the SQL, because if just some random user on your website has access to your database, kind of got some security problems. But anyways, what's going to happen is he will be entered into this, and all of his values will be put into these value spots. So we have a username, make it CC, email, cc@blah-blah-blah.com, pass it's pi, first name is Caleb, middle name Daniel, last name Curry, birth date 02/13/90. So this guy inserted all that information within this database. And if you can't read it, it doesn't really matter. Now, when another guy comes, or let's say a gal, so this lady comes and she's all like, oh, I want to sign up for this website. So she signs up for this website. And she puts her information in. And this also goes in the database as a new row. So this is just the column headers. This is separate from the actual data. The rows, though, they have individual values. She can put her values in. I'm not going to write them all out because you guys get the point. How do we know that each individual row is unique and that talks about one individual entity, in this case a user? Typically whatever the entity is what the table is titled, so the entity would be the user. How do we know that every single row is talking about only one user, and every user only has one row, the rule of one? We don't want Caleb to be able to come in here, create a new account, and make his username CC and all the same stuff again. Now in some instances we may be able to allow them to make more than one account, like I could make an extra YouTube account if I really wanted to. That would be okay, so I could have the same, a different username, a different email, same password, same first name, same middle name, same last name, and the same birth date. The only thing that changed is a username and email. Now, what the table is trying to define has kind of changed. We're no longer trying to define the person, we're trying to define the user account. Because now there's two accounts and they're completely separate entities. Hopefully that kind of makes sense. But you don't really need to worry about all the specifics. I'm getting completely off topic. So what were we talking about 10 minutes ago? I think we were talking about super keys. It's any number of columns that forces every single row to be unique. If you take all of this information and compare it with another, let's create a new row. Let's say this lady here actually ended up putting her information in. Her username is A, her email is B, password C, first name is Hi, middle name is Yo, and her last name is Hello, and she was born 03 16 72. That is her birthday. Well, now, if you compare these values, they're different. Not every single individual value has to be different. For example, this girl's last name could be Curry, and that'd be perfectly okay. But all of the values as a whole have to be different. So if, for example, someone came in here and put all of this information up here, down here, CC at blah blah blah, Pi, Caleb, Daniel, Curry, 02, 1390, that is not a unique row, and it would cause an error. So the super key could be all of these columns right here. Now, super keys are usually not defined within the database. That's because they're so broad. You have all this information, of course it's going to be unique, simply because you can only use a username one time. Typically the email is only one time. So if someone comes down here and tries the username CC, well then you already got an error, it's not going to work. So all this extra columns right here, kind of unnecessary, because we could simply do that same thing with just the username. So a super key is any number of columns that creates a unique rows. A candidate key is the least number of columns. Where did I write that? Can you see down here? Yeah, okay, we're good. So a candidate, I'll explain why it's called a candidate in a second, or in the next video or something. A candidate key is the least number of columns. So for this example, we're not going to allow two people to have the same username. We may allow them to have the same email. We may allow them to have the same password, first name, middle name, last name, and birthday, but not the same username. Because then how do you tell them apart? You can't, because all of their information is the same. They're exact clones to the database. And we do not ever want that within our database, typically. I mean, I can't really think of any examples where you would want duplicate data. But, okay, anyways, the candidate key is the least number of columns needed to force every row to be unique. In this example, the username is enough to make it unique. So we can take the candidate key and have it to be just the username, or I guess we could circle the column, because all throughout the rows are going to be unique. So the candidate is least, and super key is any. Alright, now when it comes to database programming, let me clear this up so your brain doesn't explode anymore. It takes forever. I'm on a time limit here, guys. People are going to stop watching. Alright. Now that I just got my chalkboard to listen to me and erase the stuff. When we're talking about database programming, there's not really a time where we're ever going to tell your database that this is a super key, because super keys are not practical. They are for designing your database only. When I looked at that column, first thing I do is I think, super key, yes, every single row can be unique. That's the first check. So you ask, can each row be unique? That's the question. That's to define, that's what the super key is questioning. Can each row be unique? And even better word, can every row be unique? Because every single row within a table has to be unique. That's what the super key is asking. Once we figure that out, if it can be unique, then we move on to figuring out the candidate key. So now we ask, how many columns are needed? Can you read that? Hopefully. So the first question, can every row be unique? Yes, that means we have a super key. That's all we have to worry about. We don't have to figure out which columns or anything like that. Can every row be unique? Always. Think about all the possible values. Is it possible for a duplicate? If it is, you got to figure something out. If it's not, you're good. So every row can be unique? Yes. Check. Move on. How many columns are needed? Now you figure out the least number of columns needed in order to create unlimited uniqueness forever. So no possibility of uniqueness. And we are allowed to put some kind of like limitations. We can put a unique, we can use the word, it might be different for different relational databases. But if we use a unique index, for example, every single column, every single value within a column has to be unique, and that's a requirement for people to put in. So if it's not unique, we give it an error. That's how we force values to be unique. So how many columns are needed? Once we figure that out, we have what's known as a candidate key. So in the last example, it was just one because we could use the username. Now, the next thing I like to figure out is how many candidate keys do I have? I'm just going to use CK for candidate keys. How many CK do I have? What does this mean? Well, we can actually have more than one candidate key. In the last example, we had a username. We also had an email. Okay? Well, email could also work as a candidate key because you could put a requirement that every account has a unique email. Some websites are cool with people using the same email more than once. Some websites aren't. Usually they're not. So there might be a chance where we have more than one candidate key. Or if rather than using the username, you want to use something else, you could have it to where we could have, let's say you can use your email more than once, we could have first name plus last name plus middle name, or middle initial. So that eliminates most possibilities of uniqueness. But there's still a possibility that people have the same name. So then you add birthday. So now you have to find someone with the same first name, last name, middle name, and the birthday. Very rare, still possible. So then we could add a third, I guess 1, 2, 3, a fifth column. We could make it email. Or we could do something such as address. Alright, let's go with address. This could be a candidate key because we have first name, last name, middle name, birthday, and address. They all have to be unique as a whole. What are the chances of a person living at a certain born on a certain day? Also, what are the chances of two people having the same name, same birthday, and living at the same place? Unless you had twins and you named them the same thing, and if that's the case, shame on you. I'm just going to confuse people. That could be a candidate key. Now, is it the best candidate key? Probably not, because we're using 5 columns, and it's still technically possible to have a duplicate, but very, very, very rare. Alright, so how many candidate keys do I have? You figure them out. I like to write out the possible candidate keys, and then we move on to the next step, which is defining the key that we will use for our table. Once we have the candidate keys, we can choose one of them. They're called candidate because there's an options. Like you could have your first candidate key. You could have candidate key 1, you could have candidate key 2, and then you could have candidate key 3. This could be the username. This could be the email. This could be that long first name, last name, password, blah, blah, blah. Or whatever you really want it to be. Now, you have to decide which one will be your primary key. We're going to be picking up from where we stopped last video, which we were talking about candidate keys. So this video, we're going to be talking about primary keys, which is the next step. So what is a primary key? Well, in the last video, we defined some possibilities for candidate keys, something we could use as the main key. It's a candidate because we have to pick it to be our primary key. So we have a list of possibilities. One of them was a username. Another was an email. And then if you don't have something simple like this, you could do something like your full name, which that would be like first name, last name, middle name, and then plus an address, which address would probably be broken up into like street, city, you know, all the parts of an address, and then possibly your birth date, or just DOB. So here are just some possibilities for candidate keys. We could have username, email, first name, middle name, blah, blah, blah. Well now, once you have all your possible candidate keys, you want to pick one to be your primary key. So how do you do that? Well, once again, you got to make sure we look at the rules or suggestions for keys. This is specifically talking about primary keys. We want our primary key to be unique, never changing, and never null. So username is never going to change, right? So that's pretty good. You always need a username when you sign up for an account, so it's never null. And it has to be unique because two people can't have the same username. So this would be a good primary key. Let's check out email. Well, you can make it unique. You can require people to only have, like, you can prevent multiple emails. So when you create an account, you can only use an email that has not been used. That's an option. So that's possible. Never changing. Well, it depends. Depends on if you use your email like a user account username, like you sign in with your email and you have a password too. Well, then the chances are you're not going to be able to change it. Although now you can probably update your email and stuff. So it's possible to be never changing if you prevent people from updating their main email. So possible, and never null. You can require someone to have an email. So that's possible. All three of these are possible. So this is possible. I'll just put a dash. First name, last name, middle name, address, date of birth. Well, probably the whole group as a whole will be unique. The chances of finding someone with your same name, living at the same place as you, with the same date of birth is almost impossible. So, unique, practically yes. But possible, you can possibly have a duplicate. So, possible. Never changing. Oh, well, people can get married, so their last name can change. First name can even change, or middle name can even change. You can move. You can't be born a different date. I mean, you can't be born again, like, unless you become a Christian. But anyways, never null. Well, some people might not have an address. Either that, or they might not have a middle name, or something like that. So, this is probably not the best primary key. So, in this example, I'd probably go with the username. And then, you define that as your primary key, and then you can use that to make connections between tables. So you have a comment by a username. That's the connection. That is a natural key, and we'll be talking about surrogate keys in the next video if you know anything about that. But basically, you can use your username as an ID, rather like as a primary key. So you could have, let's say this is my username. This can be the connection for all of my rows by me. So if I have a table for comments, a table for users, a table for sales, well, if I buy something, Caleb Curry, connection. If I'm a user, well, connection. If I post a comment, connection. It all kind of points back to the user table because that's going to be the parent of the relationship here. So this could be a primary key. So that's a primary key. Now this will also be indexed because primary key is a type of index. So you can do select statements really easily with that and everything like that. So that's going to be how you connect most of your data. Now, the other candidate keys that we did not choose, they're known as alternate keys. An alternate key, it works. I mean, it could be the primary key, but basically it's all the candidate keys that were not selected as the primary key. You're not required to define all of your alternate keys in your database. In fact, you don't even need any alternate keys. But you may want to, because oftentimes they will be something you're doing searches for, or connecting tables, or whatever it is. Alternate keys might be useful, so you can create an index on the alternate key. So I could create an index on the emails, for example, because I said that was a possibility. Well, now that'll be an index, and it will probably be used because you might want to do data by the emails, like selecting everyone by their email. You know what I mean? Maybe, possibly. Basically, you can do a select, and then you can choose the columns you want to choose, and then the table, and then you can say where, and then you could say like email has the value legit at awesome.com. Because you have an index on that, it's going to work better. So if you have a really good alternate key, I recommend you index it, simply for good design, and it'll help your database run faster. But if you don't really want an index on it, then don't do it, because that's just another thing your database is going to have to maintain. It's going to have to update the index as well as the book. Sort of how if I have a book here, and I change the insides of the book, well then the index in the back is going to have to change too. So alternate keys, you can set them as an index if they are good and useful, if you will be searching for that kind of information. So that is introduction to primary keys and alternate keys. So we got I think I'm spelling this right, by the way. Surrogate, and then we have a natural. Alright. So we talked about primary keys in the last video. That's as far as we'll get for defining a key. These are categories of primary keys. So we define a primary key, and then this is just kind of like a descriptive term. We don't have to define in our database surrogate primary key or natural primary key. This is more for database design, to know like the difference between types of keys. Hopefully that makes clear sense. And if not, just stick with me. Alright. Okay, so up to like all these key videos I've been doing, I've been using natural keys. Let's define a natural key first. It's a very natural definition. It's something that's naturally in the table, something you naturally want to store. When you have a users table, you naturally want to store the username and the email. Those can be used as natural keys because they fit all the requirements for a primary key, and it's already in there. You don't have to make up something. You don't have to think of a column to add just for the sake of having a key. We want to be able to have a key for every single table, but sometimes the natural key is not very obvious or not so natural. So we want to try to find a natural key when we're using natural keys. Generally, when you create a database, so let's say this huge box is our database. Within this database we have a bunch of tables, and then within each table we have a bunch of columns and rows. See what I'm saying? Well, these are all connected in some funky way with relationships. Well, when we define a database, typically, I mean maybe not always, we want to try to either always use natural keys or always use surrogate keys, which are just made up keys. We don't want to kind of flip-flop, switch, and I can't think of any other words, because we want to try to keep it consistent. Otherwise, people using the database are going to be confused. Is this a natural key or is this a surrogate key? Is this something that actually has real-world value, or is it just a made-up number? So, let's say we are using natural keys. There are a couple problems with natural keys, and this video will be explaining the difference between these two, and then the next video will be talking about pros and cons of each, basically. So natural keys are what's naturally already in the table, something we wanted to store to begin with, right? The thing is, they have real-world value, so your database might adapt, and the meaning of your keys kind of adapt too, which, once again, I'll explain that all in the next video. Surrogate keys, they are a column that's just added to your database, no matter what, even if you have a good natural key, because remember, you want to either use all natural or all surrogate, usually. So if I decide to use surrogate keys, I'm going to give an ID to every single row within every single table. So we have, let's say we have a user table, and then we have a sale table, and then we have a comment table. What we do is we give every single table an ID column. So we have a user ID column in the user table, we have a sale ID column in the sale table, we have a comment ID in the comment table. So now when we have, like, let's look at the comment table in depth. We have the comments. We're going to have a column. We're going to have a column for the comment ID, and then we'll need a reference to the user that posted the comment. So we'll have the user ID as a foreign key, which points back to the user table. So that's kind of how that works. Now we just have random numbers. The ID is just a big number that has a feature known as auto increment. That means every single time you make a new row within this table, it's going to raise the ID by 1. Then when you delete columns or something and you have gaps within your numbers, it doesn't really matter because the number has no real world significance. Typically, surrogate keys are kept completely private. No one knows the surrogate key except for the people working with the database. You're not told your surrogate key. So if I created an account on a website, and then I put my username and my password, and then I go to I sign up, register, and do my email junk, and then I sign in and go to my user settings, it's not going to be like user ID equals 45 or whatever. It's going to be private. The reason for that is because the world doesn't have, the number doesn't have real world meaning. Therefore, it's private to the database only. If I started giving that number out to everybody who has one of these IDs, or something like that, or if I started putting it on sales reports, well then I'm giving that number real meaning in the world, and it's starting to become a natural key. So hopefully that kind of makes sense. Natural is something that's already in the database. Surrogate is something we just add. The thing that's kind of cool about surrogate is if you're struggling to find a really good natural key, you can always use a surrogate key. The problem with that is you always want to try to be able to naturally make everything unique. Like in a user table, we have a username. That's going to keep things unique. So even if we use a surrogate key, we can still index this username, and that can be used sort of as if we assign it as a natural key. The only thing is we're making connections between tables using the surrogate key. So for this table, we could have a user ID, and then we could have a username. For just an example, the user ID would be the surrogate key. This would not be the natural key because we can only have one primary key, and the primary key is going to be the type surrogate. So the user ID is a surrogate key, random number, generated number. The username, we can index it and use it like a natural key with when we search the database and everything, but we're not going to use it to make connections between tables and references with foreign keys. So hopefully that makes things pretty clear. In this video, I wanted to talk about the pros and cons of surrogate or natural keys. So basically, we're going to compare and contrast them here. So over here on the left side, we got surrogate. And then over here on the right side, we got some natural. Alright, we're going to have a little battle here, right? We're going to figure out which one's the best. Let me just box this to keep this out of here. Alright, so what are some good things about natural keys. Alright, well first, one of the first good things about... Oh, that was really weak. One of the first good things about natural keys is that you don't have to define any new data. If you don't remember from the last video, let me just redefine them here. Natural keys are columns used as your key that are already defined within your table. They're natural to what you want to store. Surrogate keys are just kind of added, like a user ID or a car ID or a credit card ID or a comment ID. They're surrogate, they have no real world meaning. So, natural, not natural. Get it? Cool. So some good things about natural is you don't actually have to define any new data. I don't know if you could hear me there or not, kind of stuttered on that. But anyways, you don't really have to define any new data because it's already within your table and you can use that as your natural key. So you're required to store less information in your database, so you get smaller data. You have a smaller database, right? So that's one good thing. So what's a downside to natural keys? Well, a downside is that sometimes you're not going to be able to find a really good natural key. Because if you look over here, we want our keys to be unique, never changing, and never empty, or null. Well, if we have a natural key, we have to find one that fits all three of these, and it has to be a good one that would make sense to use as a natural key. Like, you might not want to use a combination of 20 columns to make natural key, right? But that's one of the downsides to a natural key, is you have to figure out what natural key to use. And there's not always a great option. Now, optimally, you should have a natural key, or at least something that could be used as a natural key within every table, to have the best design to ensure uniqueness, not just by a surrogate key if you use one, but by naturally what's being stored. So, like just an example, if we have a comments table, we could have a comment by a certain user on a certain web page or whatever. And what forces it to be unique? Well, the combination of that, as well as the date it's posted, or the time it's posted, that's going to be unique, because you can't have two comments from the same user at the same time on the same web page. It's not possible, right? I mean, unless you like glitch the system somehow, which shouldn't happen. Well, that's an example of using natural keys. The downside, like I said, you might not always be able to figure out what to use for your natural key. That one was a good example because naturally we could figure out a natural key. Right? Following me? The other thing is, natural keys have real-world values, real-world meaning, right? So you have connections to real-world meaning. So, for example, in the comments, the actual comment, in combination with the user who posted it, in combination with the time it was posted, and the page it was posted on, or any of those 4 columns to be used as a natural key. Well, those have real-world meaning, and as your database develops over time, the database application might change or be updated, or new meaning is given to the database and what it's supposed to do. That means that your natural keys could change over time and have new meaning, or the actual values could change in some instances, and we do not want that, obviously, because it has to be unique, never changing, and never null. If, for example, we make it to where we do have to change the natural keys, well, that would kind of be like crossing this one out. And that's possible, like we could update the values of all the keys, but that's going to require us to update all connections between tables. And that's going to require a lot of resources from our server, and that's just a bad design in general. So those are most of the cons of natural keys. So yeah. Let's move on to surrogate, right? Okay, so surrogate keys. Well, obviously the first downside is you have to add a column to your table no matter what. Even if you have for example, if it's naturally unique, well, you might, like if you have a comment from a username, well, that username is going to help ensure uniqueness, and you still add a surrogate key, well, then you're adding unnecessary data because you're adding a new column and you have to store all these numbers. One of the pros of surrogate keys is that they're typically numbers, where oftentimes natural keys can be words or anything like that. That's good because typically numbers are easier to work with, but not always. Now, a couple other things. besides the fact that you have to add a new new column, which requires you to store more data, it's that it can be confusing sometimes when all you're working with is just combinations of numbers, and we have a column, let's say like a commenter for a comments table, and we just have we have the value like 7,462. Well, this kind of clear. It's talking about the user with the ID of 7,462. Sometimes columns won't be very descriptive though, and that would be a fault in the designers, so make sure you name your columns right. But when working with other people, you can sometimes get confused exactly what reference is what, and you have to do a little bit more thinking and check the actual database structure, the way it's programmed, or however else like that. So that's a couple things that are confusing. Okay, so now you're probably wondering, okay, so which one am I supposed to use? Well, it just depends on what you want to do, if you prefer to use natural or surrogate keys. But typically, you'll want to pick one and use that throughout all of the database. I said database really weird there. I was like, database. I was like, database. Rather than database, I was like, database. Anyways, so let's say I decide to use surrogate keys. Well, that means every column should get a ID, or at least a combination of IDs. Natural, if I decide to use natural, well, that means every column should try to be used as a natural key. Because if we mix and match, sometimes we're going to have a surrogate key, sometimes we're going to have a natural key, and it's going to be super confusing, and we're not going to know what's going on. So typically you want to kind of keep one or the other. The other thing is, I don't know what the other thing was, but yeah, typically one or the other. Now, for my sake, I personally am going to use surrogate keys, although that's not saying that they're better in any way. I just prefer surrogate keys because it's simple for me, because every time I make a table, all I gotta do is make an ID with the, like if it's a user table, all I gotta do is make a column, user ID, and boom, we're done. That's all I gotta worry about, and I don't really have to worry about it ever changing or it ever becoming something different or anything. It's just a random number, 7,254. Well, that has no real world meaning. Now, keep in mind though that if you do use surrogate keys, you shouldn't have them have any real world value. So, for example, a student ID, if we give these student IDs out to the students, that's not really a good idea to use as the surrogate key because it's actually a natural key. It has real world meaning. So those are just some things, and you can find tons and tons of stuff on the internet about natural or surrogate keys. It's basically like a war between two database sides. Oh, we're the natural keys. Oh, we're the surrogate keys. Ah, I'm gonna kill you. Boom. You know what I mean? So yeah, don't freak out. Just figure out what works best for you. There's some minor performance differences, but I mean, I don't really know all of them. So yeah, believe it or not, I don't know something. I'm kidding. But anyways, try them both out if you want. Look up stuff. Look up which one performs better or which one will work best for your application or your database, because that's really what matters. So this is a big subject, and there's a lot of important things. So I'm going to be separating a lot of these concepts up into separate videos. So the next 2 or 3 videos, this video and 2 others I think, will be over foreign keys and a lot of things that have to do with foreign keys. What is? Sorry. Anyways, this video will be talking about introduction to foreign keys and what exactly they do. All right. So a foreign key is a reference. And what does it reference? It references a primary key. So that's the most basic definition of a foreign key. Now this can be a primary key in the same table or a primary key in a separate table. So let's kind of see how this would play out if we do some drawing, right? Let's think of a class for a college database. So this database has has all the information for a specific college or multiple colleges, and one table is for classes. We also have a table for instructors and for users and anything else that's an obvious entity. So let's look at the class table. So we have a class table. We'll just draw it out here. Within here, we could have a class ID, which, like I said, we're just going to be using surrogate keys for most of this. You can do the same thing with natural keys, and if you have no idea what I'm talking about, just pretend I never said anything. So yeah, we have a class ID. That's an example of a surrogate primary key. We could also have an instructor. You see, so we can have an instructor ID, right? And we could have, let's say, a room number, because we could have a table for every single room, which talks about more information about the room. Or I don't know if that's a really good example. Or we could say we have a bigger building or a bigger college, and we have a table for each building. So that's probably a better example. So we could say building ID to say which building it is in. Alright, so here are 3 IDs, so you can assume that they're all keys, because almost all IDs are going to be keys of some sort. Which one is the primary key? Well, this one right here, the class ID. This is the primary key because it's the class table. Every single row within this table is going to have a class ID, whether it be 1, 2, 3, 4, 7, 12, 843, 64, whatever it is. It's going to have a class ID, every single row. So every single class is going to have its own ID. But we also have an instructor ID, and we also have a building ID. Well, since these are kind of unrelated to the class, you can assume that they're foreign keys in this example, because we're not going to have an instructor ID for a class necessarily by itself. This is going to be an instructor ID for an instructor. So that means we have another table for instructor. So this is our instructors table. I think I'm spelling instructor right. And we have an instructor in here. Instructor ID. Well, this, you can tell that these are a reference here. And we can also have a building ID. So this references another table. And that would be the building. And then we have a building ID. Let me see if I can get this. Sorry, I'm taking forever to write and I can't even write nice. But that says building ID right there. And this references that there. So you can see there's a connection between these tables. Now we'll get more into drawing relationships better, like rather than just using lines. We'll talk about more of that in the future. But as for now, we can see that these reference these columns. So the columns point to each other, and also each individual row is going to point to each other. So let me explain that a little bit more. When we have a row within our class table, let's draw this table out a little bit better so we can kind of see how it would work. So let's say this is an actual example of the values within this table. We have a class ID, an instructor. I'm just going to put I and then the building ID, just for simplicity. Okay. Dun, 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 dun. Just because I don't feel like writing all that out. So we can have a class ID, and just to make things more, just to be more accurate to what a normal database would be, we could say like the name of the class, like biology or whatever. So we could have a class ID. We could have 7 for a value. We could have the instructor ID could be 63. We could have the building ID of 16, and then the name could be biology. Well, every single column is going to have column rules or requirements. For example, these 2 columns here, individually, this one is going to have a rule that says every single value within this column, so as we go to the next row, the next value, every single one is going to have to reference something from the instructor table because it's an instructor ID. So that's one of the column rules. Now, same for the building ID, we could say that every single row has to reference a value within the building ID. Alright, so that means the row right here, let's say this row individually, this one right here, the class ID with 7, biology, references the instructor with the ID of 63 and the building with the ID of 16. So you can see that the column has rules set to say that every single value within this column, every single row, is going to have to reference an instructor and a building. Now each individual row, we could say, oh, this specific row references the building and 16 and the instructor 63. You see? So that's kind of how foreign keys work. Let me clear this out, kind of draw it out a different way. Let's take a look at the building table. Okay, so let's just draw a little square just to represent it. And let's say within this table, we're not going to structure the columns or anything. We're just going to say we have the building 7, 16, and 14. So these are 3 separate buildings, and we could have names for the buildings and all kinds of other things. Now, we have within the class, let's say this is the class table, right? And we have the class ID, so the class ID would be like 64, 38, 123. It doesn't really matter what number they are. And 8, right? And now we're going to have a reference to the building ID. So let's say we have 7, 7, 7, 14, right? So here's just an example. So over here we got the class ID. We got the building ID. And then we got the building ID. And then we can have more information about the building here if we wanted. Well, you can see that there's a connection between every single value, every single row within this class table has a connection with a building ID. So the entire column, building ID, has the rules that every single value within that column has to point to a value within the building ID of the building table. Now each individual row has a value that points to a specific row within the building ID. As you can see, these are all individual rows. Sorry, it's getting a little crowded here. We can see that 3 of these classes in this class table reference one building, and that's the building with the ID 7, and that could be the room legit building 74, or whatever you want to call your building. It doesn't really matter. So that's an example of a relationship using foreign keys. Foreign keys are what keep things connected. So let's say the name of building 7 was legit, because I really don't know what else to name it. Well, now we have the value legit as its name, and we connect with the ID. So rather than putting legit, legit, legit and having repeating data that could be easily messed up, for example, if legit was changed to legit with 2 T's, or just change the name completely, well now with this foreign key, it's connected so it updates automatically. So yeah, that's kind of how foreign keys work. Just keep in mind that every table has one primary key. Now that primary key can be a combination of multiple columns if you want, but it only is defined as one primary key. For example, we could have the combination of first name plus last name. This group could be the primary key, but we're not going to have the first name primary key, and we're not going to have also the last name primary key, because that's two primary keys and we can't do that. We can have the combination of the two. But with foreign keys, you can have multiple columns having foreign key relations to different tables. But keep in mind, each column can only have one reference. So in the class example, we had a teacher ID. Well, that teacher ID, here's the class table. And let's say the teacher ID is 7, 6, and 5. Well, this can be a reference, and we could also have another foreign key. We could have the building ID, which could be 6, 12, and 8. So although we are only allowed to have one primary key in a table, we could have multiple foreign keys referencing different tables. If we wanted it to be where the instructor, I think it's supposed to be an I. So the instructor, to where the class can have multiple instructors, well, that's a many-to-many relationship, and we're going to have to redesign our tables with an intermediary table. So hopefully that's kind of making sense. I just want you to realize that the primary keys are what sort each individual tables, the foreign keys are what connect tables, and that you protect that integrity with foreign key constraints, which we'll be talking about in the upcoming next few videos. This video I wanted to talk a little bit more about foreign keys and a characteristic known as not null. Alright, so this keyword here might vary from relational database to relational database, but it's probably something similar to this. Not null, which we learned about null when we talked about this over here. It's basically saying the database will not accept someone not answering that column, for example. So if it's not null, you have to give that column a value every single row. So the rows are each individual entry within the table. If you have the column characteristic of not null, for every row it's going to be required that it has a value. So think of like a fax number. Does everyone have a fax machine? No, most people don't. So if I set it as not null and I didn't give it a fax number, then it would throw an error and cause problems. That's an example of how not null works. Now this is important when it comes to foreign keys because it has to do with what's known as cardinality, which we'll talk about that when we start designing databases a little more. But it's basically whether or not a relationship is required. So this is going to dictate what kind of values we can put within our table. Back to the fax machine, if we have it to where it's not null, that means every single value, every single row has to have a value. That also means that if someone doesn't have a value, they might not be able to put any information in this table. So by putting this restriction, you are eliminating all rows that aren't going to have a value. You're preventing them from happening. You see what I mean? Yeah. So if the case is where you do want people who don't have fax machine numbers to be able to enter data into your table, well then you would not want to use not null as a characteristic because that's going to prevent them from doing that. Now this is important when it comes to foreign keys because if we require a relationship, we set it as not null, and that means every foreign key value for that column, every single row is going to have a relationship for that. So one of the biggest differences between primary keys and foreign keys is that primary keys are required all of the time, never changing, never null. Right? Drop my chalk. Dang it! Ah! Alright. Well, foreign keys are a little different because we can have them to where they're not required, they can be empty. Because sometimes that relationship is not there. Or they could update, like we could have a new relationship in this table, which we want to eliminate as much possible updates as possible, but sometimes that's required, and that's why we use foreign keys to keep things connected, so when things are updated, they update across the platform. Now, we don't want the primary key values to change, but we could have the foreign key references change. For example, let's say we have a table over here, alright, and we'll just have it, we'll have it be cars, okay? Or we'll just have it to the car, right? And we have two rows, and we have a car with the ID of 6 and a car with the ID of 10, right? And we have this guy over here. And we have a table for him. We'll just make it the user table. And let's say for some reason we wanted to make a connection of what car he owned. Well, he might currently own 6, right? And we don't ever want the value of 6 to change and still be talking about the same car. Let's say this car is this one over here. This is some flames, right? And this one over here, we got a legit car. Boom, right? So these are 2 separate cars. 10 talks about this car, 6 talks about this car. We don't ever want it to happen to where this number gets updated, 8, or we change the primary key and it's still referring to the same exact car, because then we have a changing primary key. But with foreign keys, it can change in the sense that, oh, I no longer own this car, now I own this car. So, we didn't have any primary keys updated, but the foreign keys, which would be this connection right here, did update, alright? So that kind of is a little bit of a difference between primary keys and foreign keys. Primary key values should never change. Foreign key values can change because references change. Hopefully I didn't just lose my train of thought. I think I'm going, but kind of hitting a blank here for a sec. Okay, so let me just illustrate this in a college, right? One of the important things between these tables that have a primary key and a foreign key connection to that primary key is that they have to be of the same data type, which is the type of data, whether it be int or character or date, and basically it has to have all of the same characteristics, like the collation or the character set or the storage engine. Now, the only thing that can vary is the not null characteristic. Because if we have the primary key over here, well, we know that the primary key is never null. So we always have not null for the primary key. I'll just put NN for short. The foreign key, on the other hand, it's not always required to have a connection. For example, in that previous example, we had the user table, we had this guy over here, and then we have this car table of the cars that the user owned, right? You could have one car, right? Well, he might not currently own a car, therefore we don't have a connection to this table, therefore this connection is optional or not required. Yeah, that doesn't even look like English, but close enough. So let's think of another example. If we have a college, well, we might be early in the semester where every single class, before people have registered, every single class doesn't have an instructor yet, and we're still trying to find an instructor, although we know that's the class that we want to have. So that means we have an instructors table, we'll have the instructors over here, and we have a class table. Well, a class table is going to have a foreign key pointing to the instructor for the instructor of that class. Unless the case of a many-to-many where multiple instructors can teach multiple classes, then we would need an intermediary table. But that is not the case here. If you need to learn more about that, check my relationships video. But for now, we would have a class ID and an instructor ID. Right? And then over here we have an instructor ID. As it says INS, instructor, close enough, right? Now, this is going to be a reference to this over here. Now, what kind of values is this going to accept? Let's give some examples. Let's say we have, here's a row, we have the class ID 7, the instructor ID 83, and we'll add a column, we'll make it the name of the class. We have a column and it's math. Right? And then we can have another value within here. I think I'm off screen now. Then we can have an instructor over here. His name, his ID could be 7, and his name could be Jake. Right? So this class ID is 7. Yeah, let me change this, it's going to get confusing. Let's make this 16. Alright, so this class ID is 7, and it's by an instructor of 8, which we don't actually have over here yet. So that means we either have another row or we have an error, because we never want that to happen. So let's say we have another class. Got any room? Okay, we have another class over here, and its number is 8, and it's taught by Caleb, right? So now we have an instance of a class. We got the class ID 7, the instructor ID 8, and the name math. So the instructor ID points to this instructor over here. This is the parent. I'm sorry, this is the parent. This is the child, because this is a foreign key reference to the parent. So that means this relationship is a foreign key. Now, with the not null thing, if we made it to where it's not null, if we added the characteristic not null, well, that means this row is going to have a value for the instructor ID. That means every single value for instructor ID is required. What does that get rid of? That means it's impossible to put a class in this table that does not have an instructor ID. That could cause a problem if you have a class created but you don't have an instructor yet, or if the instructor drops out and you have to find a new one. So this one might be a bad time to use not null. If we got rid of that, well, now we could have a class with a primary key but no foreign key connection. Now we have a class with the ID of 7 and it's math, and the current teacher, we don't have one. And we still have this guy over here. He's not teaching that class, but he's still in the system. Jake's still in the system. The class is still in the system. That is a good example. So for this one, not null might not be the best idea. Other examples, having not null would be a good idea because it forces that relationship to be there. Here, let me think of another quick example real quick. If we had two entities, we had a card for a credit card company. So we had the card, and then we had the person holding the card. So the person who bought the card, or was getting the card from the bank and is using it to buy their groceries and their gas, and they're ranking up thousands of dollars in debt. Well, that person would have a relationship with this card because he's the card holder. That's the card. Now, if we had a table for this, we'd probably have a card table, and we'd have a person ID, which would reference the person table, right? If we set this to not null, that means every single value or every single row within this card table is going to require a card owner. If we got rid of this, that means we could have cards in here that were outdated, that don't currently have an owner because there's no connection, we broke that owner, or new cards that haven't been given out yet. So if you want this table to just be for cards that currently have an owner, so we could have it owned cards, well, then we could have a not null column with the same data type as person ID. And now every single value is going to have a person ID. Does that make sense? So that's kind of the introduction of not null and how that works with foreign keys, and how sometimes you will want them to be not null and other times you want them to be nullable or not required. I got a bunch of writing on the board, but don't look at it yet because I just want to talk to you guys for a minute. I just wrote it so you wouldn't have to watch me write like 50, 100 words, because that'd just be boring. So instead, I'm just going to talk instead. So much better, right? Anyways, last video and throughout the series we've talked about foreign keys. And as we know, they keep connections between tables in a database. So table 1, table 2, boom, foreign key. Connect from this foreign key references the primary key of this table over here. That's kind of how foreign keys work. They protect the integrity of our database. They keep everything consistent. Think about if there was no foreign key constraints, which keeps it updated and everything, then we would have to manually update all connections between tables. and that'd be a big waste of time, and it'd just be easier just to store everything in one giant table, which both solutions, either manually doing it or storing everything in one giant table, is not going to work. So we need foreign key constraints to protect the integrity of our database, right? It's called referential integrity. That's a big word, sorry. Alright, so now, this concept, these words, might be specific to a certain relational database management system. So these are from MySQL, but if you're using a different relational database management system, yours might be a little bit different. But in general, the concepts are pretty similar, so you're not wasting your time if you don't use MySQL, because you need to understand how foreign key constraints work. Alright, cool. So first of all, foreign key constraints, make sure that if you update the parent, the children are going to update, or cause an error or something like that. It's up to you. You can make the decision. And it's also going to prevent you from creating children when there's not a parent with that primary key. For example, if we have 5 users with the user's ID 2, 4, 6, 8, and 10, and then I make a comments table and I add a row that's like from the user 745, well, that person doesn't even exist, so that's not going to work. So that's why foreign key constraints are important, because they, once again, protect our database and make it pretty much self-managed rather than us having to manually update everything. So let's begin. Alright, let me get a piece of chalk. This one looks nice. I'm getting pretty low. This is the biggest piece of chalk I have left. Alright, so when we create an SQL statement, we can add these two keyword phrases here, on delete and on update. This refers to the foreign key constraint. So but it's talking about the parent. So when we update the parent, we want get away, you stupid fly. Alright, when we update the parent, we want the children to do something. When we delete the parent, we want the children to do something. That is what these keywords mean. So these keywords, it's talking about the foreign key constraint, and it refers to the parent. Alright, so let's just draw some basic tables just to kind of keep things. I'm not going to give any specific examples yet. I'll just kind of draw things out. So let's say we have a parent here. And as you learned in previous videos, the parent is the primary key, right? And then let's reference this primary key with a child. Okay, let's not draw this line yet. And then we have a foreign key. This primary key is a column within the parent, and every single row has a unique value. The foreign key is a column within the parent, and it references the primary key. So the value 400 in a row could reference the value 400 in this row, in a row of this table. You get it. I've explained it enough. Now let's just make another child table. So these are both foreign keys that reference the same primary key, but they're two separate tables. So yeah, like we could have a user table, and then we could have a comments table and an orders table, for example. They both are bought or commented by a user. So these foreign keys reference primary keys. So every single value within the table of the children, within the foreign key column, needs to be a value that is present in the parent column. Now, these values right here, these options, refer to the parent. So when we delete the parent, or when we update the parent, we want the same thing to happen to the child, or whatever the options are, and we'll talk about the options in a second. So that's kind of how these work. Now just to kind of clear things up, I'm going to erase these words here, just because it's getting a little crowded, you know? I want it to be peaceful. Alright. Okay, so this is kind of how it's working. Foreign keys point back to the primary key. these options refer to what happens to the parent. Now these options right here, these refer to what happens to the child. Okay, now it's getting real confusing. There's arrows everywhere and like graphs and diagrams and whew, but you'll get it, don't worry. Restrict, you might also hear as no action, is, well, at least for MySQL, in different database management systems, these might be different. But anyways, restrict is going to throw an error. So if we try to, like, we can give one of these for each option. So on delete, we could either give restrict, cascade, or set null, or null. On delete, we could have it restrict, cascade, or set null, just to add more errors, you know. But let's say we're working with delete right now, and we want to use restrict. So within our SQL statement, we could say on delete restrict. So on delete restrict, and that is going to give us an error whenever the parent is deleted. So if I tried to delete the user with the ID, I don't know why I'm writing all that out. Let's just say the ID of 504, and then this child has a row that has 504 within the foreign key column, well then it's going to throw an error and it's not going to happen, and the parent will not be deleted. Not going to happen. So that's how cascade on delete works. I'm sorry, restrict on delete. Now restrict on update, if we updated that parent and changed their primary key, so let's say we changed 504, and these children both reference 504 with the foreign key, and then we change this to 508, and it's not going to work, and it will go back to what it was originally. Because we have it restrict. We're not going to let that happen, you see? Alright, what about the next option? Cascade. Cascade will do whatever we do to the parent to the child. Let me clear this up a bit. This is confusing me. Alright. Just smearing chalk all around, you know? Totally helping. Alright, so now if we cascade on delete, that means if we delete the parent, we're going to delete the child as well. So we delete 504, and boom, children are deleted, boom, child deleted. So now 504 doesn't exist at all. So like for example, if this was a comments table, and we had a comment from the user with the user ID of 752, and we deleted 752, the user, well then obviously all of his comments by him should be deleted too, because we'd have a comment by a user that doesn't exist, which isn't supposed to happen. So cascade on delete would do that. On update is if for some reason we updated the primary key, which obviously shouldn't happen because primary key should be never changing, but you still want that protection on your database. On update, if we have cascade, if we change like 504, let's say these people exist again. I'm just going to erase this because I don't... Oh, yeah, okay. So these people exist again, 504, 504. These references 504. And if we update this to 508, well that means all of the children will update as well. So now it connects within different tables. Finally, we have set null. And what that'll do is it will basically just set the children as null for that specific value. So if we deleted the parent, this is just going to get rid of the value. The row should still exist, but the actual foreign key reference, it no longer references anything. It's empty, so it's not referencing anything. So the column for that row, so like let's say we have a comment, and it's a comment from Billy Bob with the ID of 504. If we delete that, well now we're going to have a comment with no poster or no commenter at all. It's just no value. That's what set null will do if we use on delete. On update, same thing. If we change the ID of the parent, change it from 504 to 508, well all of the children are going to be set to no value as well. Alright, now there's one important thing with set null. The children have to have, they can't have, I should say, the not null characteristic. We talked about that in previous videos. I'm just going to put NN for short. If this is not null, and we update, if we have on update set null, and we update 504 to 508. Can you even, have I been cutting this off this whole time? Alright, we set 504 to 508. I think you can see that one. Yeah, you can. If we change 504 to 508, and this is not null, it's going to be like, we can't do it because we can't set it to null, because it has the not null characteristic, which means every single row has to have a value for that attribute or that column. So I'll give an error and it'll go back to how it was. So that's an introduction to foreign key constraints. Sorry if I talk fast. But yeah, cool stuff. It's important stuff, so learn it, study it, and learn it for your specific relational database management system. In this video, we'll be talking about simple and composite and compound keys. These are categories of keys. So like when you define a database, you can say, alright, this is a primary key, or you can say this is a foreign key. But you don't have to say, oh, this is a natural, simple primary key. Like those are just categories. You don't have to define that within our database. So these terms that we're learning are more for design's sake, so you know the best design for your database, but you don't actually have to define it, right? Like for example, this piece of chalk right here, you can define this as a white piece of chalk. Now what kind of white piece of chalk is it? Well, it's X brand or whatever. You don't have to define that when you're telling someone, oh, here's a piece of chalk. That was the worst example ever. Moving on. Alright. Simple and composite. Okay, so simple means that the key consists of one column. Composite means it consists of two or more columns. This is most common with natural keys, because natural keys can be a combination of multiple columns, whereas a surrogate key is just a random number, one column. So surrogate keys are simple. Composite keys are multiple columns. So for example, we could have a first name plus last name plus email. This could be an example of a composite key, because this whole group as a whole is the primary key. So we could have Jim, Jake, and legit, or awesome, at whatever, just blah 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 blah. And then we could have another one with the same exact name, Jim, Jake, and we could have a different email. Well, these two are still separate. They're unique because the combination of the three are unique. Jim and Jake repeat, but the email is different. So these as a whole are different values for primary keys. So that's an example of a composite primary key. The reason is because it consists of three columns. 1, 2, 3. This is an example of a composite key. A composite natural key, to be specific, because we're using things that are already naturally being stored within our database. Now let's think of a simple key. A natural one, or a username would be a good one. Because the username can be something that can be used by itself as a key. It's simple because it's only one column. Pretty simple, I know. Alright, so I want to talk about another term you might run into. And that is compound. Okay, now, I want to clarify that some people and some relational database management systems don't clarify the difference between these two, composite and compound terms, and they just use them interchangeably as meaning a key with multiple columns. Some people go a step farther and break these up into two separate terms. So we're going to be defining both of the terms, but you might see them used interchangeably. So don't be so super technical about the details, and don't be like correcting people, oh, hold up, that ain't a composite key, that's a compound key. Duh. Because most people are just going to look at you like you're an idiot and not really care. Alright, so anyways, moving on. A compound key is basically when it's a key that has multiple columns and they're all keys themselves. So this is the most common example of this is for intermediary tables. So think about it like this. If we have a a table used to store information about videos, we could say it's a video table. We could also have another table over here. We could have a user table. Actually, here, let's do it this way. We're going to have a comments table, okay? And then within this comments table, we could have a column of what video they're commenting on. You see, well, this is a many-to-many relationship, right? So, this might not work out well with database design because one user can comment on multiple videos, and then one video can have comments from multiple people. So the best way to do this, rather than having two separate tables like this, we would create video table, and then we'd have an intermediary table, and this would be video comments or user comments. You see what I'm saying? So we get a connection between the user and the video to create an intermediary table, and it's split up with two keys. So we have the user ID and then the video ID, and then we could have another column for the message or the date or whatever else. Well, you can see, if you don't know what I'm talking about, go see my videos over designing many-to-many relationships. But otherwise, if you do know what I'm talking about, moving on, you can see that the entire key itself, every user and video ID combination has to be unique. That might be a bad example because a user could comment on the same video more than once. So this is probably not the best example. Let me think of a good one. But anyways, this would be an example of we could add another column in here to make it unique. We could have the date and the message. So the message has to be unique, and the user ID has to be unique, and the video ID has to be unique. That would be a composite key. A compound key, let me think of an example real quick. So a good example of this would be for college. We could have a student table, and we could have a class table, right? So this table holds information about the student, this table holds information about the class. Now how do we show enrollment? Should we make columns for every student here? No, because it's a many-to-many relationship. That means we need an intermediary table between the two. So this is a good example. Sorry about my bad example in the last one, but that's a good example of a composite key because the two columns themselves wouldn't be enough, so we'd have to add another one, which is not a key in itself. But for this one, we could have a column. We'll name the table student classes, or just student class, whatever you want to call it. Student classes, and within here we could have the IDs, student ID and class ID. Now this combination between student ID and class ID must be unique. So let's say we have the values 7 and 4, 7 and 6, 7 and 7, that would work. But if we had something like 7 and 4 again, we would get an error because that's already in there and that's not going to work out so well. So the combination has to be unique. And these are also both foreign keys which point to another table. So both of them are keys, and the primary key is compounded because we have the student ID and the class ID as one giant ID, or one giant key, I should say. Because the combination has to be unique. We can repeat 7 on this side, and we can repeat like 6 on this side, but we can't repeat the combination of 7 and 6. They have to be unique as a whole. So composite keys, that's when you have at least one is not a key in itself. For compound, they all have to be keys. So for the composite, let's look back at the example we gave in the last one with the videos, the video comments. Let's say this is the intermediary table blown up just so we can see it real big. This is the user ID, and then we have the the video ID. Well, this isn't sufficient to make uniqueness because a user could comment on the same video more than once. Like if you're replying to comments or something like that. So we need another column. We could add a timestamp, or we could just say the time column. And this is going to keep a unique time because you can't comment on the same video at exactly the same time twice. Right? So that would ensure uniqueness. So we can ensure these three as a whole are unique. That's an example of a composite key because at least one column is not a key in itself. This is a key because it points to a users table. This is a key because it points to a videos table. This is not a key because it's just a column for that intermediary table. So those are the three terms I wanted to talk about in this video. One other thing I wanted to talk about real quick. I'm not going to say what the best technique is for this. I'm just going to say what some people do. With an intermediary table, some people will give it a surrogate key on top of the compound key. So for example, with the college, keep switching back and forth between examples, I'm probably confusing you. They might add something such as enrollment ID, and then we have the student ID, and then we have the class ID. These are both foreign keys, and they might use this enrollment ID as a just a surrogate key for this table, although it's not a requirement for certain relational database management systems. Some relational database management systems or frameworks or something are not going to be able to work well with composite or compound keys, so you might need to have a simple key, which in that case you could still have the idea of a compound key. This group right here, the student and the class, you can have that indexed or whatever you want, or you can just enforce uniqueness with that. But then you can use an enrollment ID, so you could have like 7, and then you could have student 6 in the class 4, and then you could have 8 with the student 4 in class 12, and then you can have 9 with the student 16 in class 4, and then we could have 10 with student 16 in class 12, and so forth. That's just an example of what some people do. This video is just going to be a quick review. I'll actually be using my notes here just to make sure I get the main everything, because I'm not going to try to memorize like 10 videos of content. That's just crazy. Crazy, I tell you. Alright, but anyways, first thing we started with was super keys. So a super key was just any number of columns that ensure uniqueness within a table. So we have super key, which I still don't know why that's only one word, which just confuses the heck out of me, so someone please explain that. Then we had a candidate key. Now the difference between a super key and a candidate key is that a candidate key is the least number of columns used to enforce uniqueness. Now you can have multiple candidate keys if you like a certain group. So if that's the case, you have to pick one as your primary key. The primary key is the one you select as the main key for your table. All the other ones you can assign as alternate keys, which if that's the case, they still can be unique. You can still enforce uniqueness upon those, but they're not used as the main key within your table. Alright, what else? Alright, well then there's, that's pretty much all the ideas with finding a primary key, and then when you reference that in another table, you have what's known as a foreign key. Foreign keys reference a primary key. It's a connection. That's how you make connections between tables. If you have a user table and then you have a comments table, well, the comment is posted by a user, so you can reference that user in that comments table. And we talked a lot about that, so I'm pretty sure you guys got that pretty well. Now, this is pretty much all you got to worry about for primary keys and foreign keys. You just got to worry mainly about these two. These ones are less important about finding and figuring out. these two are essential. I'm not saying these aren't important, they're important, but really, defining a super key is kind of pointless when you know there's the candidate key. You don't have to say, okay, well, all of these define uniqueness. That's one super key. All of these define uniqueness. That's another super key. Oh, finally, we're down to the correct size for a candidate key. That's our candidate key. And then I'm check marking, by the way, just so you know what that is. And then, oh, okay, we got a total of 10 candidate keys, 5 super keys. Now let's find a good primary key. Oh, this one looks nice. We'll use that one. We'll set the rest as alternate keys. That's just complexity that is unnecessary, when it's easier just to say, oh, there's a candidate key. It's already the smallest that we need. We'll use that as our primary key. And now let's see if we have any other alternate keys. Oh, we don't have any good ones? Oh, too bad. It's fine. Who really cares? Oh, we do have some good ones. Oh, yeah, let's set those as an index and make sure they're unique, and we'll use those for some searching later on. That's an example of how you would find a primary key. You don't have to make this manual labor for like 20 hours to figure out which primary key to use. Alright? Then you reference that primary key in other tables to the foreign key. So that's why these two are the most important. Foreign and primary. Those are the two you should focus on the most and memorize, okay? The alternate candidate super key, and they're kind of important, but not as important. Alright, so let's take a look at primary and foreign. Let's just, let's clear this out for a second. Oh my god. Alright. Primary. Now there's some categories. Dude, I dusted, and now it's like, whew. Can't even breathe. There's some categories of keys that we can talk about. So the first one was surrogate and natural. So surrogate and natural keys. A surrogate key is just a random number that has no real-world value or no real-world meaning. Just like an ID, user ID, student ID, college ID, classroom ID, store ID, sale ID, record ID, song ID, picture ID, whatever you want it to be, I don't really care. As long as it's an ID and it's a surrogate key, then yay. I don't know what I just did there. But anyways, natural is something that's already naturally in the database, and you just define it as your key. Now typically when you want to use keys in your database, which you will because it's your relational database, you will pick either surrogate or natural keys, and you'll use them throughout the rest of the database. You're not going to switch from surrogate and natural. You're not going to be like, oh, this one has a natural key, we'll use natural, but this one doesn't, we'll make it surrogate. That's a bad design. You should be able to enforce uniqueness by the columns that are already there, and then you can add a surrogate key if that's what you want to do. And if by any chance you cannot possibly define uniqueness without a surrogate key, you're pretty much required to use a surrogate key. But that situation should try to be avoided. But there's times when you literally cannot find a natural key that will be sufficient. So you guys kind of follow what I mean. Surrogate keys, random numbers, natural keys already in the table. Boom. Simple. Alright. Speaking of simple, we'll talk about the simple key. Alright, so we got simple, we got composite, and compound. Okay, so simple is basically a one-column key. Composite and compound are multiple column keys. We talked about those in the previous video, I believe. Yeah, so that's pretty much all the categories of keys. When you define your primary or foreign keys, you're not going to have to specify if it's a surrogate, natural, simple, composite, or compound. This is for our sake to design the best way, because, for example, do you want to use composite keys or do you want to use simple keys? That's a good question. If you decide you want to use simple keys, which, by the way, surrogate and natural is kind of thing you do throughout your entire database, you can kind of switch back and forth from simple and composite. For example, you could have a users table, and we could have a students table, a class table, and then we could have an enrollment table with the students taking certain classes. We could use I guess we could use a compound for this table, and then we could use simple for these tables. That's something you could do. But you should still use either surrogate or natural. Just pick one and use it throughout your database. Hopefully I'm not talking too fast, because I'm going pretty quickly. If I am, just let me know. So I just need to calm down a couple decibels, because I'm kind of hyper. Okay. No, the other thing we talk about is foreign keys and foreign key constraints. Well, the main kind of foreign keys, the main kind of foreign key constraints were on update and on delete. These protect our integrity of our database. You define these whenever you make a table. When you use the create table statement, or create, or whatever your relational database management system does to create tables, the chances are you're going to say that you have a foreign key. I'm just going to put FK for short. And then you have a constraint, and you can usually name that constraint. So you could be like blah blah blah, name it whatever, and then we could say on update or on delete. And the options were, the ones I taught you were do nothing, or basically throw an error, or we could update the children, or we could basically get rid of the value for the children. So that would be restrict, cascade, and set null. But your relational database management system might use something a little bit different, which is fine. Yeah, that's about it. Yeah, that's pretty much it. Yeah. Cool. Alright, so yeah, that's a summary of keys. So yeah, that was a ton of stuff. Okay, so there's a couple different names for this. So basically, it's just a standard. It's a standard for drawing databases. And the couple terms you might hear, or acronyms I guess, EER model, ERD, or ER model, or just database design, whichever one's easiest. But basically, these are some terms used to refer to a method used to draw out your entire database structure. These videos I've been drawing tables and lines and drawing tables and lines and stuff and all kinds of cool things like that, but actually I haven't officially designed any database. So what we're going to do, now that we've learned most of the concepts, the only thing we haven't really covered is normal forms, which we'll be getting into those, but anyways, and I'll make them easy, don't worry. So what we're going to do is we're going to learn the standard for drawing these databases. We're going to practice with that, and then we're going to learn the normal forms, and then we're going to design databases. It's a lot of stuff, but we're going to do it. So we're going to be getting into the standards of drawing databases, and obviously the standard's kind of rough. I mean, there's not a specific way you have to do everything, because that's annoying and dumb. So what we're going to do is we're going to be drawing pretty simple things, and I'll just be kind of illustrating kind of how that works in this video. So what this means is enhanced entity relationship model, enhanced relationship diagram, enhanced relationship model. Yeah, I think that's what they stand for. I don't think it stands for relation. I think it stands for relationship, which there is a difference, as you should probably know by now. A relation is a table. A relationship is a connection between two tables. Yeah, so anyways, yeah, so we're going to be talking about these designing techniques. I'll probably just call them like ERD or EER, or who knows what I'll call them. But yeah, the way you do it is you define your database structure. So anything that is DDL, pretty much. Data definition language, part of SQL, we talked about that a long time ago. We're not going to define the actual values. For example, if we have a table for users, we're not going to put in a row, oh, Caleb Curry with the password of sweet pie is delicious 24, and the email of yeah@yeah.com, and the telephone number of 1-800-YOU-WISH, or anything like that. We're not going to put anything like that in there. We're just going to put the columns, username, password, email, telephone. 3D. That is so cool. Okay, anyways, let's get started. So to draw a table, a database table, you just draw a square. It's like super easy. Okay. Wow. Who would have thought it would have been so easy, right? And obviously, doing this on a chalkboard is not very convenient because, for one, you're limited in space, and for two, most of you guys don't have chalkboards, and for three, I don't know a third reason, but most of this is actually done on a computer, and we will be doing that, hopefully, soon. So, stick with these concepts we'll be getting into on the computer design for whatever reasons, and obviously as I make new videos in the future, that's what I'll be doing. So for now, we'll learn the concepts, and you can download entity relationship design programs such as MySQL Workbench. I made other ones like Vertibello or something, I don't remember what it's called, and a couple others which you can design for any relational database management system on that one. So go check out my other videos, or my playlist. I think it's under reviews or something. But I don't know. Look up database design on my channel, see what I got. You can also just look up EER or ERD relationship or design, and you can get all kinds of apps and programs to help you design your databases. And then some of them have what's known as engineering, so you could forward engineer your database design and it'll basically just program your database for you, and it's super easy. Yeah, but I'm getting way off topic, so let's get back on topic. Okay, so here's how we draw a table. What we do is we give it a table name, so you put the table name either right here in a complete column like that, or just right above it. So we'll just put it up above it right now. So this is a user table, and then what we can do within here is we put the columns this way, vertically. I mean, we write them horizontally, but we list them this way. We're not putting them across here. Because if we put them across here, we would assume that we're going to have row value, like Caleb. Password is awesome, email is legit or cool, and then like password, I already said password, but we're not doing that. We're just going to put the columns. So the first column we could have is user ID, because we're just going to use a surrogate primary key in this example. So I could have user ID. Now, when you get into it, you can also put other things like data types in here and any other restrictions you have, such as not null if you wanted. But for now, and for most of the design, for design concepts, I'm not going to do that because I'm going to be writing the same thing over and over again. And you kind of only do that when you're finalizing your database. So you can kind of worry about the data types later on, but for now we're just going to get the columns, figure that out. Good, we'll go from there. So user ID, username, the password, and so forth. Hopefully you guys can read that, probably not. And then what we do, if we want to create another table, guess what we do? Oh, we just draw another box, right? And we connect these with lines, and we can, there's certain ways to draw lines that represent different relationships. Like that's one way to do it. Or we could have like, yeah, I mean, you get the point. Oh, I found a nice big piece of chalk. Cool. Alright, so that's how you do that. Now, that's pretty much all the basics of entity relationship diagram drawing. Just remember, we put these in here, the columns, and what we can also do if we wanted, we could put indexes down here. We could put like index types, and then we could also draw our relationship types with different lines, and we can draw our foreign keys by either putting them down here or doing some other kind of thing. Now there's also other conventions you might have heard of or have used, like UML and other design techniques, and I'm not saying those are bad, I'm just saying this one's super easy for beginners and for experts. We actually talked about this a little bit, but we haven't really designed it or anything, because now we're talking about actually drawing out databases. Cardinality is basically the relationship type between a row of one table and rows or a row of another table. So I thought of the best example I have for this is a credit card database. So like basically a credit card company has a table for credit cards, and then a table for cardholders, or the people who order the credit cards and use them to buy things, and basically they're the credit card company's customers, I guess. So I will draw those tables out just so you can see this. I'm not going to draw them real big or anything, but just so you see how the connection works. So we have the card holder, and then over here we have the card. And there's some kind of relationship between these two tables. Now, the only two possibilities for cardinality are one or many, obviously for both sides. So you can have one to many, or many to many. Those are the only three possibilities. Now, another thing to think about when it comes to many, you might even consider that as not a possibility, because you'd have to have an intermediary table, which we talked about that when we talked about designing many-to-many relationships. When we're talking about many-to-many relationships here, it's logical, which what I mean by that is we're drawing it as a, just like this, and we would say many to many. And then when we actually implement that in a database, we would have to have a card holder, card holding table, and then the cards table. That would be how to draw a many-to-many relationship. So hopefully that kind of makes sense for that. So in reality, when you're actually drawing out finalized products of databases, the only possibilities are one-to-many or one-to-many. Because even if you have an intermediary table, this is going to be a one-to-many relationship, and then a one-to-many relationship. And there's a certain way to draw those out. That's what I'm going to be drawing right now. So a one-to-many, it's pretty simple. The one side, all you have is a straight up and down line like this. The many side, you have this. This thing that we're doing right now is known as crow's foot notation, because it looks like crow's foot. I think that's why they call it that. I don't really know. But this is a one, this is a many. So when we're drawing it, one, many. We could also have one to one, of course. So that's another possibility I forgot to mention. One to one. Now before we start drawing it on both sides, I think it's easy just to think about one side. Like think of a card holder relationship to a card. We would have one card holder. Now that we have that side figured out, we just think about the card holder. Then we can add in the card, and we have many cards. So one card holder can have many cards. And that's how you would design the line between the tables. Like that. Now there's another thing we need to talk about known as modality, which we'll talk about in the next video, but for this we're just going to keep it simple, just drawing these things here. But you might see also like circles. You might see a circle here, for example. We'll talk about that in the next video. So now you know how to draw a one-to-many relationship. So what does this exactly mean? That means one row can be connected with many rows in this table. It's not necessarily the table, but the rows within the table. So we could think of a specific card holder. We could have a card holder with the name Jack, an ID of 2, and we could have many rows over here, cards. We could have a card with the ID of ID 6, ID 8, ID 12, and you can see this guy has a lot of credit cards. So all of these rows can be connected to an individual row within the card holder table. Now let's look at it the other way. We could have a many-to-one relationship, or basically a one-to-many going the other direction. So we could have this. So now one card can be connected to multiple people, but multiple people can't be connected to one card. I'm sorry. One card can be connected to multiple people, but one card holder can only be connected to one card. So that means one person cannot own more than one card. So now we think of it the other way around. We have a card with the ID 3. We have a card with the ID 4. The ID of 6. It doesn't really matter what the numbers are. And then we have a card holder. We just got a guy named Jack, which ID of 3. And then we got Bill, ID of 2. Well, we can have one card attached to many people. So this card could be attached to many people, which means these people co-own a card. They're both the owner of one card. But now you have to realize an individual card holder can't be connected to multiple cards. So Jack cannot own another card. That's not going to work out. If you wanted that to work out, then you'd have to have the intermediary table, which we talked about in designing many-to-many relationships. And this video is less to be a review of relationships, but more of how to draw them. So you have to realize the difference between all of these possibilities. One-to-one, one-to-many, or one-to-many. It just depends on the actual application. Modality, it's basically whether or not the child is a required child, if the relationship is required. We talked about that when we talked about the column characteristic not null. So, think of it like this. We have a credit card company, we have a table for the card holder, and then we have a table for the card. Obviously, the card holder, the ID for the card holder, the person who owns the card or buys the card from the credit card company, they're going to have an ID, and that's going to be a not null column, meaning it has to have a value. That is obvious because it's going to be the primary key, surrogate primary key, and it has to have a value. So we have like this guy, and he has an ID of 7. We have another guy with the ID of 12, and then 368, and so forth. Those are IDs, you see? Card, that is going to have a column, which is a foreign key, referencing the card holder, because the card is the child in this relationship. So the card holder has the primary key. Can you see that down there? Yes, you can. Card is going to have a foreign key, which connects to these. So this is going to be a foreign key, meaning these are the people that own certain cards. So we have a card with the ID of 12, we have a card with the ID of 48, I'm just making up numbers right here. We have a card with the ID of 98, we have a card with the ID of 112. Well, they each have an owner. You see, this is the owner. And this is a foreign key, which references the primary key. So 7, this card is going to be owned by that person. 7, this card is going to be owned by that person. 7, this card is going to be owned by that person. So all of these 3 cards are owned by that person. 368, that's going to be owned by somebody else. Now, if we gave this column right here, the foreign key, basically the card holder column, because it's a child, if we gave it the column characteristic not null, it would be required that every single row has an owner. That means we can't have a card in here that is either not activated and doesn't have an owner, or we can't have a card in there that is not being currently possessed by a card holder. Because you think if you have a credit card, somebody owns that credit card. But when you first make a credit card or something, or if you if you get rid of the credit card or something, it might be a credit card that currently does not have an owner. Does that make sense? So basically just a credit card that's not being actively used or is disabled or something like that and does not have a card holder. Well, if we wanted this database to be able to store cards that don't have owners, we would not want the not null characteristic because that's going to prevent it. So that's kind of how that works. So if we take that off, then we could have a card down here with the ID of 101 that doesn't have a card owner. Well, I know we've already explained this all, but now let's talk about designing. So let's just make this simple. We'll pay attention to the, we'll say one card. Well, this obviously is we're going to talk about a one-to-many relationship, meaning one card holder owns many cards, and we're also going to be talking about a one-to-one relationship, meaning one card owner owns one card. If we want to do a many-to-many, we just need an intermediary table. The same concept kind of applies, but we don't necessarily have to go through that. Just break it into a one-to-many, two one-to-many relationships. All right, so let's try this. So we have, over here we have the table. That's going to be the card owner. Over here we have the table for the cards. And there's a relationship between these two. That's a really big gap, but whatever. So let's start over here. We can say one card holder, because that's what we're just going to say, one card holder for each time. Let me bring this in some so you can actually see. One card holder can have one card. So what we just did is cardinality. We talked about this in the last video. Now let's do another example. We'll just do the same thing, and you'll see why in a second. Let's do another example. And then finally one more example. Running out of room here. So we have the basic relationships. Now we can add one more thing to say if it's nullable or not nullable. Basically, does the child, this is the child, which is the card, we're asking, does the foreign key column have the not null characteristic? So we have the possible relationships, one to one, one to many. Now, what we're going to do is we're able to add the modality in. And the way we do that is we add either a little circle or a little dash. Or you can think of it as a 0 or a 1, which actually will make sense, and you'll see why in a second. 0 or a 1. So, over here we have the card holder, one card holder for all of these examples. And then over here we have the card. A 0 means the column does not have the not null characteristic, meaning it accepts no value. So this is saying it can accept no value. So we have a one-to-one relationship. That's the maximum. The card holder can have up to one card, but it's not required. So 0 or 1 cards. 1 or 1 cards. 0, at least 0 cards, because you can have up to many, or at least 1 card. So this means not null, not null. Now when we design this, we're talking generally from table to table. So we would have card holder, and then card. And why do I have to say that? Basically because if we have a 0 here, that means there's not necessarily going to be a relationship between a certain row. So when we're talking about rows, we might not actually draw a relationship between certain rows. When we draw relationships, we talk from table to table. And those relationships explain what rows can have relationships with different rows. So in this example, let's just focus on the top one, just to make it easier. We would draw this within our database application. We would say we have the table, card holder, and then that has some kind of relationship with the table card. Now we could say one card holder can have 0 up to 1 relationships with one individual card. So we have a card holder with the ID of 7, and then we have a card with the ID of 68, owned by the card holder 7. So that points back, and that's acceptable. We could also have a card, 69, and we could have a person 8, and we could say, oh, it doesn't have an owner. That's fine. We could have another card 70, and it can have the owner 8, which points back to 8. And then we could have another person, which could be 87, and we could have a card. We could have a card 63, which has the owner 87, and that points back to the owner 87. So that's how those relationships work. Now, at first these can be kind of confusing, so just practice. Make sure you fully understand how each one works. Just review. We could have here's 4 possibilities we could have. Let me put that one up there, it makes more sense. One card holder can have 0 or 1 card. One card holder can have only one card, because you can have 1 the least, and then up to 1, and then you have one card holder 0 or more, and then one card holder 1 or more. These two are required, meaning every single child has to have an owner. Or every single card has to have an owner. Every single child has to have a parent. So hopefully that all makes good sense. I just want to introduce a topic, so in the next 3 or so videos, when we go over it, it's going to be like kind of not all new to you. You'll kind of have an idea of what's going on. So we're going over what's known as normalization. So normalization is a process where we go through our database plan that we have, and we start correcting things that may cause data integrity problems, or just repeating data, etc., etc., whatever you want to say. The normal forms are basically like a checklist that you're going to follow, and when you get to the end, you'll have a pretty good designed database. So yeah, there's 3 main forms, and these are named very conveniently, I have to admit. First, normal form. Second, normal form. And guess what the third one is? Yeah, you guessed it. Third, normal frame. I'm kidding, it's form. That'd be weird though. Alright, so we got first normal form, second normal form, and third normal form. These are the 3 steps of normalization for databases. Now, if you really want to get into database design, and you're just like, man, I love this stuff, I gotta get more. Well, there's tons of more steps you can add and make things all complicated if you really want. But for our practical purposes, these are the only 3 that you're going to really need. And I know there's like a glare right here because of these lights. And I know I'm just working on it. So give me a couple videos and I'll try to work on my lighting a bit. But for now, first normal form, second normal form, third normal form. Why do we have these? Well, it's because we want a systematic way to follow to produce a normalized or a good structured database. Alright, there's a couple things you should know when it comes to normalization. We still have to talk about the idea of things being atomic. We want everything to be atomic. You also have to kind of think about data depending on other data. So if you think of, like, let's say a primary key, you got 608, just a number, that could refer to anything. That could be a person, an order, an event, whatever it is. It's just a primary key. And that also is going to have different columns in the table, which have different attributes about whatever this thing is. So let's say it's a person, and we have a column for the name. And let's say this dude's name is Caleb. What a dumb name, right? This depends upon the primary key. So what I mean by that is if we change the primary key, we're going to also change the person, right? So let's say we have 609. Well, this is going to be a completely different person, right? Because they're 2 separate entities. This one's referring to some guy over here, and this one is referring to some guy over here. 2 separate entities. You can also think, oh, by the way, that process or that thing, this is called dependency. So the next 3 videos we'll be going over the first normal form, second normal form, and the third normal form. The other main thing is that these are kind of comprehensive, I guess you could say. So what that means is, once you have a first normal form, Now you can go on to the second normal form, but you can't go jump in right here. You have to have it in first normal form before you can get into second normal form. Same thing for second normal form into the third normal form. So that means if you have a database that is in third normal form, it is also in second normal form and in first normal form. So I know I'm just like getting all this technical on terms and junk. So if it's freaking you out, don't worry. It's really simple. Gotta get my hair out of my face. Alright. But basically, it's a list of steps, a list of things to do, and basically you can't do this step 2 until you do step 1. So this here, second normal form, that's step 2. Can't do this until you do that. So you gotta go through the process, and then once you're at third normal form, things are good to go. This video will be over the first normal form, which is the first step in database normalization. This normal form deals with data being atomic, or atomicity. Alright, so let's begin. Let's first look at 3 examples where there are problems, and then I'm going to explain a solution. If we take a look at this first example, we have a user ID, first name, last name, email, and address. I have some values in here, but those aren't really important in this example. The main thing you need to pay attention to is the address, because an address, if you think about it, actually consists of a street address, state, country, and so forth. So this column is not atomic. We're asking for multiple things within one column. So that is the problem in this example. The solution for this one would be to break it up into multiple columns, you know, a state, and so forth. That way we don't have a bunch of things within one column as an individual value. This example, you can see we have one row with a user ID, first name, last name, and email. But if you look closely, we have 2 emails. These emails were entered together as one individual value. So you can think of maybe on a website it'll ask you for your email. Imagine putting one email in and then putting your second email in the same box and clicking submit. Well, it's entered into the database as a single value, maybe with the comma or something, but it's still entered in as the email for this user. So 2 values within one, which is not atomic. In this example, the actual values given for the email are atomic because they're only one email, but we put 2 entries within our database. So now we have this in here twice, this in here twice, and this in here twice. And the primary key should never be in there twice. The only time you can see the primary key in there twice is if it's a reference as a foreign key, because the foreign key can be put in there multiple times. But the primary key of 5 should only be in there one time. So we have all that duplicate data. Now what if this Caleb Curry goes and gets a name change? Because that's such a dumb name, right? No, I'm just kidding, because that's my name. And I actually like that name. But anyways, if he gets a name change and he updates his information, what if only this one's updated? So now we have conflicting data. And see, that's the problem with data integrity. We need to make sure that doesn't happen. So in this example, the column is the problem. In this example, the values for the row is the problem. And in this example, the values for the row is the problem. So these basically have the same problem. How do we figure out the solution? Well, let's take a look over here, and as you can see, there is no solution. So yeah, guys, thanks for watching. I'm just kidding. Let's do this. The best solution for this problem is to have a user table, and I'm going to write the columns that are within this user table. So we would have a user ID, then we are going to have a first name, and we're going to have a last name. If you wanted the address in there, you could have street address, state, country, all that other good stuff. Then we're also going to have an email table. So the solution is to break off the problem column. You can see in this example, the email is the thing causing the problem. The address that we had earlier, that's fixable. If it's a problem in the column, we could just break that up into multiple columns. So we wouldn't have to make a new table for that. But since this one, even though the column's correct, it's the values within it that's causing the problem, we would need to create a new table for that. So that's why we have this email table. And now within here, we're going to have an email ID. And then we're going to have a email, which is going to be the actual email address, which in this case would be these. And then we're going to have a user ID. Now this is going to be a foreign key that references this user ID, the primary key of the user table. Now, if we wanted to put two individual emails, we could have rows within this email table. Let's spread out the email table and see what it might look like. Here's what the email table might look like. We would have an email ID, which is just a randomly generated number for each email. 608 is fine. And then the email, that's going to be the actual address of the email, so we could have this. I'll try to make it just as bad as handwriting. Perfect. Then the user ID of who owns that, which in this case would have been 5, because 5 was the ID that was used for this user. This would be our first row. Then we could have another row, and it'd be a new email, so we'd have a new email ID. It'd be a different email. We would use this one this time. And I'm going to make that beautiful handwriting that you guys love. There we go. And then the user ID for that would also be 5. Now, this repeating value is okay. This repeat right here, this is okay because this is a foreign key. And multiple emails are allowed in this situation. This email ID, this is not okay to repeat because each individual number should be a separate email because this is the primary key of the email table. Now when we look back at the user table, we don't have any repeating data because we're only going to have a user ID such as 5, first name, Caleb, and a last name, Curry. And there's no need to make a repeating row because we have all the information we need without having any problems. If we change the name, we would just update this, keep the same ID, change this to whatever we name ourselves or whatever the person names themselves. So there you go, everybody. That's first normal form. Now, second normal form deals with what's known as a partial dependency. That's when a column only depends on part of the primary key. So in order for it to depend on only part of it, you have to have a compound or composite key. So basically the primary key has to be multiple columns. Because think, if you just have one column as the primary key, a column can't partially depend on half of it. Does that kind of make sense? I don't know, maybe not. Let's say we just have a random table for people. So we have, you know, the persons, let's just use a person ID. And we have some attributes about this person. We have their name, you know, maybe their phone, or their pH level. And maybe their email. Let's first talk about what a dependency is before we go in and talk about partial dependencies. These columns depend upon the primary key. So in this case, this is the primary key. And there's a dependency here. Another way you can think about it is if we have another table about cars, we could have a car ID, which is also a surrogate key. Now this person's name, it does not have a dependency here. You can see this name is only dependent on the person ID, not upon the car. So this doesn't make any sense here. Another thing is that the person ID doesn't have an unrelated entity or an unrelated attribute about the car ID, so such as the car color. The car color has a dependency on the car, not the person. This isn't going to make any sense. That's what a dependency is. Now what is a partial dependency? So let's see what a partial dependency looks like using surrogate keys. You'll see this when you have a many-to-many relationship broken up with an intermediary table, which is the correct way to design a many-to-many relationship. So let's think of the example of books and authors. Because if you think about it, one author can write many books, and one book can be written by many authors. So conceptually, it's a many-to-many relationship. But we're going to store that in the database as one-to-many relationship on one side, and then one-to-many relationship on the other side. So we get this look at the table, intermediary table, and then a table. So over here, let's put the authors. So this is the author table. Then over here we have the book. So this is the book table. And then in between, we have the intermediary table of book authors, or book author. So this is the correct way to design it. Now when it comes to attributes, all the attributes about the author are going to go over here, all the attributes about the book are going to go over here, and all the attributes that have to do with both the book and the authors connected, those will go in this table. So first let's give them some surrogate keys. We'll give this one an author ID. We'll give this one a book ID. And this one's going to have two foreign keys of the author ID and the book ID. And those foreign keys together will be the key for this table. So that's kind of how you would set this up. Now things about the author go over here. So you know, their first name, maybe their last name, maybe their birth date. Whatever you want to put about the author. The book would have stuff about, you know, the ISBN, which is, the ISBN is the code on the back of a book you can look up. It tries to uniquely define that book, so the exact edition and everything else, so you can just use that to define it. You know, we would maybe have the page numbers or the publisher. The publisher could be a primary key or a foreign key to another publisher table, or you could just have it in that table if that's how it worked, but likely it'd go to another table. But we're getting off topic. Anyways, it would look something like this. So author information goes over here, book information goes over here. This is the correct way to design this table because when it comes to dependency, the first name of the author has only to do with the author, and it has to do all about the author. Now let's look at things that have to do with both the book and the author. We could have something such as the author position. Now what that is, when you write books, often there's a person who has like the first author position, which is what the big name is, and then you'll have the second and the third and the fourth. People often compete to try to get first author. This has to do with both the book and the author. Because if you think about it, if we put author position here, that's going to depend on what book we're talking about. We can't just put author position 1 and say he's first on every single book he ever is going to write. That doesn't make sense. We can't just say author position 1 on the book because it doesn't say which author we're talking about. Which author is 1? It doesn't make sense. That's why we have to have it in this table because it has to do with the book and the author. So we could say book ID is 17, author ID is 22, and the author position is 1. So that would say the book with the ID of 17 and the author with the ID of 22 is in the second or the first position on that book. It's a little complicated, but we combine that with joins to make more sense for the actual viewing of the data. But anyways, this relies on the book and the author ID. That's why it's in this table. This is correct. Now an incorrect thing would be something like the ISBN, because the ISBN has to do with the book only. So when you look at this, it relies upon the book ID. It has a dependency on the book ID, but it doesn't have a dependency on the author ID. This is an example of a partial dependency. Now the correct way to fix this in this case would just be to take ISBN and put it in the book table, which we obviously already did because I put that in there first when we started. But if you didn't have this table and you were working with just say like one table maybe, well then the correct way to do it is to take the book ID, the ISBN, drag them to another table, and then use a foreign key to connect to that table, which we already have it structured correctly because we understood how to design that many-to-many relationship, which is why relationships are useful to understand. But if you don't have it already set up correctly, you'll have to take the partial dependency and move it to another table and reference it with a foreign key. For second normal form, you want to first be in first normal form, and second, remove all partial dependencies by moving the columns as we did here. We took that ISBN, put it in the correct table. Now another thing you can think about is if you have a table where there's a primary key of only one column, you're already in second normal form for that. Like imagine it for this. How can birth date be dependent on only part of the primary key, which is author ID? Because there's only one. You can't depend on only part of an individual column. Third normal form. In order to get there, you have to first do first normal form and second normal form. So it's kind of like a ladder. You can't just start at third normal form. You have to work your way up there. So this one deals with what's known as a transitive dependency, which is when a column depends upon a column which depends upon the primary key. So I know that's kind of like confusing, so let me just kind of draw it out in a table. It'll make a lot more sense. So here we have a review table, as you can see. I'm kidding, you can't see, it's just a square. So we could say review. So like this could be on a website, it could be, you know, like a shopping website where you review a product, or it can be a review on a video or anything really. It could be a review on a book. Most likely it'll be on a shopping website where you buy something, whether it be a book or anything or cars or whatever. It doesn't matter. But in this you would have something like a review ID, obviously, which will be the primary key. You would also likely have what that review is, like in a text form, so like a comment. So you would have the actual review, and then you would have maybe a star rating or multiple star ratings. So you could have a star rating, so maybe 1 through 5, 1 being the worst, 5 being awesome, and then 4 maybe being like really sort of okay, you know? And then we might have something that has a star meaning. So that would be like sort of okay, right? And finally we might have something like either a user or the poster. I'll just put the user because likely you will have some kind of user account on this website where you can post comments. So this will likely be a user ID, and it will be a foreign key to a user table. But we're not going to put that in here right now because that's unrelated to the actual point. So foreign key, primary key. Now, let's look at right here. We have an issue. This is what's known as a transitive dependency, because the star meaning depends upon the star. And a way you can kind of try to figure out if it depends on it is, okay, well if we change the star, is the star meaning going to change? Well, if we take the star and we change it from a 4 to a 3, it might go from really super okay to really average. So the star meaning is going to change. So that's a dependency. But then the star actually depends upon the actual review ID. Because if you change the actual review, the star is able to change. So this is known as a transitive dependency, and it is bad. Now you can also have a multiple transitive dependency, which I don't even know what those are called. But that would be where a column depends upon a column, which depends upon a column, which depends upon a column, which depends upon the actual primary key. And it can go on forever for as long as you want. But you don't want it because it's bad, which is why we're going to remove it. So to remove this, you take the columns that are causing a problem, you move them to a separate table, and then you create a foreign key in replace of them, which references the actual other column. So let's do this. So since these columns right here are the ones causing the main problem, we take them, we put them in their own table. We have a star table. Within the star table, we're going to have a star ID, and then we're going to have the actual star, whether it be 1, 2, 3, 4, or 5, or whatever kind of rating system you're using. And then we're going to have the star meaning. And then over here, we're going to replace these columns. Let me make this a little prettier. And I just made it 5 times worse. But we're going to replace that with a star ID, which is going to reference this table over here. So now we don't have that problem because the only column over here is star ID. We don't have the star meaning, which was the real column that was causing the problem. Now over here, we could have, if we drew out this table, we would have, we could have a star ID of 3, and that star could be a 3-star rating, and it could be, it could mean average. Now, we're likely to only have 5 individual rows in this table, so it's kind of like a reference table. So over here, we could have a star ID of 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, or 5, 6, 7, 8, 9. It doesn't really matter what the ID is, because the ID is just a number used by the database and has no real-world value. So we would have 5 rows in here, and then we would reference them in the reviews table. So we could have, okay, this is too ugly. Let me just explain it. We could have one review with the star rating ID of 5, which could correlate to a certain rating from this ratings table. That's the main idea of the third normal form, is to take those transitive dependencies, move them to a new table, create a foreign key to reference that table. So in review, first normal form is making everything atomic, second normal form is removing any partial dependencies, and then third normal form is removing any transitive dependencies. This video we will be discussing indexes. The best way to think about it is just to take a book, look in the back. There's often an index here, which basically has a huge list of topics, and it says what page they're on. So you'd be like, oh wow, that looks fun, queries. Go to page 2078. Wow, it's right there. I found that so fast. I didn't have to go search through the entire book to find it. That's an example of an index. It's basically a list of where certain data points are. Another kind of index is, you can think of a phone book. You go to a phone book and you search it through the phone book, you find someone's name, we go to grandma, and it'll have their phone number right there. That's another type of index. It's where the data is sorted in a way that you can easily find it and the data is right there, versus an index in the back where it's a list of data pointing to where it's at. The one we first discussed is known as a non-clustered index. What that means is that the data is not actually where the index is. The index is a separate thing, and it basically just sorts the data, and it's basically a point that tells you how to get to the data. So the way it works in a book is you find the topic, and it'll tell you where to go. 365, for example. Go to page 365. That's a non-clustered index. A clustered index is like the phone book, where it actually reorganizes the actual data in a way that's easy to use. Non-clustered points to the data. Clustered organizes the actual data. So we can have multiple non-clustered indexes. That's because a non-clustered index is basically just a list of references that point you to the data, so we could organize it in different ways. But as for the clustered index, we can only have one of those. That's because it actually organizes the data that way. So think of a phone book, it's organized A to Z, or however. You go through there and you find it. That's a clustered index, it organizes the data. Well, what if I wanted to put the data in by the phone number? So the smallest phone number, like 0000001, which would be an awful way to organize a phone book at the beginning, and then 999999999 at the end. That's an awful way to design a phone book, like I just said, but that is another example of a clustered index. That's because it actually reorganizes the data. That's why you can only have one of those, because a phone book can't be listed A to Z and also by the size of the phone number. See what I mean? It's conflicting. You can't have both at the same time. You can only have, okay, this is sorted by name. Or, oh, this is sorted by phone number. You can't have both. Now you could make the phone number size or whatever as a non-clustered index, where it would be like this. It'd have the actual phone numbers in the back, and it would point to where it's located. So at the beginning of the index, it would be like, okay, the phone number that's 00000000001 would be on page 743. The phone number with 00000000002 is on page 242. You see that the actual data isn't organized by the phone numbers, but you can use that non-clustered index that sorts it that way and has a reference to the actual data where it's located. Now you guys are probably sick and tired of me rambling about this, so let me just explain how this makes sense in databases. Well, when we're working with a database, often we will use a certain column for certain things. And that column will be used frequently, and we want that to be like super fast. So we want the database to know how to use it the best way. So we create an index. The database understands the index, so that way when you tell it to do something, it can do it faster, rather than it having to go through all of the data, which is called a table scan. When you're working with a database with millions of rows, that can take forever. If you have an index, it'll use an index seek, which will basically know where to start searching for that data. That's awesome, because it makes our queries tons faster and saves a lot of resources. There's downsides to it though, because when you create an index, not only does the actual table have to update whenever you update it, but you also have to update the indexes. Think of like a book. When you add something to this book or you change something within this book, not only does the actual book content in the beginning of the book change, but also when you flip to the back, the index must also be updated. Otherwise, all this index information is going to be out of date and useless. So that's a downside to indexes, is when you update your information, it might take a little longer. In a database query, we might say something like select the first name, last name, and the phone number and the email of the user with the user ID of 72, for example. Well, I kind of said that in English, but when you're actually working with a database, it might be more like select first name, last name, email, phone number, where user ID equals 72. That would be an example of a database query. Now that where clause is using the primary key. So basically, the database is going to go through the table, find the person with the user ID of 72, and then display their first name, last name, phone number, and email. Well, that where is using a column that has an index. The primary key is usually the one that's going to have the clustered index, so that's the way it actually sorts the data. So now, it doesn't have to go through the entire table to find the person with the ID of 72. Because imagine if it was just random data thrown in there with no organization. You have 2 billion rows, right? And the database has to go through and find the one individual row with the user ID of 72. Go to the first one, nope, not 72. Second one, nope, not 72. Third one, nope, not 72. And keep going on and on until it finally found the person with the user ID of 72. Basically, that would take forever. But with a clustered index, it knows, well, 72 is going to be in this part of the database. It comes after 60 and comes before 80, because that's the way it's sorted. So it's going to be like, boom, got it, done. That is how indexes kind of work. So clustered indexes are going to be faster and better, but you can only have one. That's usually the primary key, but it doesn't always have to be depending on the database and what your goal for the database is. The non-clustered indexes, which are like the index in the back of a book, those are still good and they are recommended if you're doing something where you're like, where first name equals John. Now, it has a list of all the Johns and where they're located on the database, or on the table, I guess. That's also a good thing. But you don't want to have an index on something you're not going to be using a lot, because you'll just have to have another thing updated. Another thing, you don't often want to do where clauses, which is like where first name is Caleb, without that column that you're searching being a indexed column, because it can take forever. Another reason for indexes is to increase the speed of joins. So the way the join works is it takes data from one table and then another table and combines it together by the primary key and foreign key connection. So think of a users and comments. So a user posts a comment. So you'd have a user table and you would have a comment table. And let's just draw rows on here. So we have this guy. I'm just going to draw pictures just because it's funner. So we have 3 people over here. And we have 4 comments on a website or review, or it doesn't really matter. Well, this one comment is posted by one person, and one person can post multiple comments. It's a one-to-many relationship. Well, when we want to output this to where we can review the data, we want to use a join so it's not across multiple tables. Because if you're thinking like, this comment was posted by the user with the user ID of 72, you're not going to know who that is right off the top of your head, because that's a foreign key connection. So rather, you want to replace that 72 with the actual name of that person, or the username. That's a join, and it's all done after the database is created. It's all for the query side. So basically, this is what is defined in our database, and we want to output with a join a new table that looks more pretty and easier to read. When we do this, we're going to do something that says the user ID of this the user ID of this table is the same as the user ID in this table. So if a comment has the user ID of 72, we know that it's done by the user with the user ID of 72. That's a foreign key connection, which we've talked about like this entire series, so I'm not even going to explain that anymore. But now down here, in this table, it's going to say Caleb Curry. Then it'll put the comment, and it'll join that. Well, this is also done with a where clause in some cases. For different databases, the terms might be a little different, but basically, that column that you're connecting by, which in this case would be the primary key, needs to be indexed to make it faster. So whenever you're joining a certain column, the 2 tables, the column you're joining should be indexed. You can also have something that's known as a composite index, which is an index that is an index on 2 or more columns. So think of like a first name and a last name, or last name, first name. Now the thing about these is, when you use the indexes, so let's say you select where first name equals this and last name equals that, you have to do them both or it's not going to use that index. Now there are exceptions to this. Think for MySQL actually, if you order them in a certain way, like this, if you put an index on the last name and then also the first name, you can do a where clause for both the last name and first name, so finding everybody with the last name Curry and the first name Caleb would be really fast. But the way this is set up, you can also do the leftmost one too. So you could say, find the person with the last name Curry. That's going to work. But in this case, you couldn't do it with the first name because it's not on the left. So that's just the way MySQL has it set up. So different database systems might have it set up differently, where you can't search with them individually, or you can. But most likely, when you make a composite index, you should expect to always use that index by itself. Unless you have it set up to where you make a pretty awesome index that can be optimized to do multiple different queries that you need to do. Like if I'm going to make a ton of queries where I put the last name as the where, and then I'm going to make a ton of queries where I put last name and first name for the where, This would be a good way to set that up because I'm making one index for last name, first name. That can also be used for just last name. So yeah, that's just the basic introduction to indexes. Yeah. I'm not going to be giving you tons of syntax to actually making them because, like you should know by now, this is a database design course. We're just trying to learn how to design our indexes on our tables so that our database works good. So that's something you may have to learn more once you actually program a database, because you can test the speed of the actual indexes to see this for speed optimization to make the database as fast as possible. You can't really do that if you're only designing a database. You can only get so far when designing indexes with the database, but you can get pretty far because, I mean, obviously you'll likely be using the primary key for where clauses and joins, so that's something that's good to have a clustered index on. What a data type is when you create a column. Every single value in that column has to be of a certain data type. So you need to tell that column when you create the database what data type it is to be. Also, when you're designing, you usually put the data types there as well, so that way you have an idea of how your database is going to work. So there's three main categories of data types, and the naming conventions or the names of these data types from one database management system to another database management system might vary a little bit, but in general they're organized into three main kinds. That's date, numeric, and string. So basically we're going to be going over these in a little bit of depth. We're not going to go super in depth because right now you just need to understand what these are and just understand that your database application might be slightly different from others. Let's start from the bottom up just to make things fun. String. String is any characters or like letters. So basically you put these within quotes. So, hey. This is an example of a string. Even a number within quotes can be used as a string. In this case, this would be used as a string. Basically, the 3 doesn't have any mathematical value unless it's converted to numeric. Within string, you often have some subcategories. You will have something that's either char or varchar, which those just mean character or variable character. What that means is it's just like a list of characters. The character or char usually is stuff that's set in length, so like a phone number or a zip code, something that doesn't change size-wise. So basically with a char, you have it something like char 8, and every single value within that char column is going to be stored as 8 individual characters. Now even if you don't put 8 characters, let's say you put 6, then there's going to be 2 blank characters in there, so they're all stored as 8. Varchar, on the other hand, is variable, basically meaning that the size can change. You can have anywhere from 0 up to 8. There's also often the subcategory or sub-data type of text, which is often used for larger things such as comments, messages, and so forth. That's basic summary of the string data types. As for numeric data types, these are numbers. That's different than this. This is a string that has a number in it. That's used differently than the numeric data type. The numeric data type doesn't have quotes, it's just the numbers that you're using. Just like string, there's often some subcategories of decimal and then floating point or double. Decimal works in base 10. Now, I know we haven't really gotten much into bases, and I'm just going to put date back up here since we haven't got there yet. But I think it's really important to know. And in fact, I've made a lot of videos over binary, hexadecimal, and stuff. Basically different numbering systems that use different bases. Well, decimal uses base 10. It's the number system we're used to counting in. You know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes back to 10. 11, 12, 13, 14. It's base 10. That's what deci means in decimal. Well, there's also binary. So we have decimal, and then we have binary. Decimal is base 10, binary is in base 2. So binary, we only have the options of 0 and 1. Now, you don't really need to understand how to calculate in binary, but if you want to know that, I do have videos for that. But just know when we're working with decimal, it is working with a base 10 system. When we're working with floating points, we're working with binary, which is stored differently. It's stored in binary, and then you can have it presented as decimal for math or whatever. So what's really the difference? Do you use decimal or do you use floating points? It just kind of really depends. Decimal generally is more accurate on mathematics to a point. There are problems that can come up with decimal, but you'll just have to research those. But basically, this one has some errors. Binary, it has problems with certain mathematical equations or numbers. For example, when we want to store 1/4, it's stored like this. We have 0.01. And the way this kind of works is we have anything after the point that divides the number basically in half. So we would have half, but we don't have half. So we have half of a half, 1/4. Kind of makes sense? So the place values would be, this one right here would be, we'd have half. This place value would be 1/4. And then anything after that would be 1/8. And anything after that would be 1/16. So right now, the way we have it, we would take 1/2, multiply it by 0 to get 0, because we don't have anything there. We take 1/4, multiply it by 1, since we have it there, we'd get 1/4. 0, 0. We add those up and we get 1/4. Basic adding and multiplying to understand how it works. But when we have a number such as 0.1 in decimal, that is basically impossible to store in binary, simply because we're working in a base 2 system and we can't get to 0.1 very easily. Because 1/8, that doesn't quite cut it. You'd have to basically have a combination of a bunch of different fractions to get as close as possible to 0.1, but you can never really get there perfectly. So that's a problem with the floating points. So if you needed to store something like that, you would, if it needs to have that accuracy, you would have to have it stored as a decimal, which stores it differently. Oh, that was a lot. Sorry if I completely overwhelmed you with that number stuff. And if I did, don't even worry about it. That was a little too fast. If you need it slower, please check out my introduction to binary video. It's a super long video where I basically explain it step by step so you understand. And then I have a couple other videos adding and subtracting, and also fractions in binary. You will also have an integer type, which will only store numbers that don't have any decimals after them. So only whole numbers, like 5, 12, 28, -52, so forth. With numbers, we also have to worry about whether they are unsigned or signed. If they are unsigned numbers, that means that they can't be negative. If they're signed, that means they can be positive or negative. You're probably wondering, why would you ever do that? Well, if you're working with something that doesn't go negative, well, then you wouldn't need it to have that negative. When you have a signed number, and it can be positive or negative, the range of potential values stays the same, but since you include negatives, the maximum value is different. It's not as high. Think about if you have a range from 0 to 1,000, but then you include negatives, now you have from -500 to 500. That is going to be told with the data type. So you might say something like double unsigned. That would work as a number. That's enough for numbers. I don't want to talk about this anymore. Let's talk about dates. Dates. Well, there's a couple different things you need to know about dates. There's date, then there's time, there's date time, and then there's timestamp. So let's talk about date time first, because it makes sense the best. It basically just stores a date, such as, 02 for February, then you might have a colon, you might have 22 for the date, the 22nd, and then a colon, maybe 1998 for 1998, the year. Then you have the time, which could be whatever. It could be 12, 30, 22, which would be the seconds. And you might even be able to have some milliseconds or microseconds. That's how you would store a date time. The way it actually looks might vary from database management system to database management system. Some might have colons between the numbers, some might have hyphens or commas or whatever. It doesn't really matter. I don't want you to think about that right now. I just want you to think about the date being a date and the time being a time. Date time being the combination of a date and a time. So that's pretty much that for dates. The only other thing is the timestamp. The timestamp is an exact moment in time that's recorded to establish when something was created or done. It can be in milliseconds, or it can be in the month, and the day, and then the second hour, and then the seconds, and then the milliseconds. Or it can just be a number of seconds, so forth. It varies. But anyways, that's going to give you a number when something was done. It's usually for something like when an account was created, or when a transaction was done, or when something happened. When you update a column, that timestamp will often update, and that's going to keep it to like when that row was entered into the database. So if you enter a new row and one of the columns is a timestamp, it's going to give you a value as soon as you submit that and it's put into the database. The timestamp's created and it says, okay, this row was entered at this time. That's the main thing with timestamps. So basically we got three types of data types. We got string, it's numeric, and then date. All of those classifications have different data types for each one, but in general, as long as you know like the gist of what is what, you'll be fine. You don't have to worry too much, because when you get in actually programming a database, you will have more specifics on what data types to use. So this video will be talking about joins, and in fact the next whole group of videos will be about joins. So it's going to be a lot. Now, joins are a complex subject. They can be confusing and tricky and very syntactical. I don't even know if that's a word, but basically the syntax from relational database management to another relational database management system can be confusing and complex, but rather than diving in just learning all that stuff, we're going to be talking about the concepts of what the types of joins are. And I know you might not even know what a join is yet, so you're probably thinking, I don't know what you're talking about. Well, that's what we're talking about today. So, thank you for joining me. Let's begin. So, a join is when you take something that's structured in a database in a confusing, non-user-friendly way, and you're presenting it in a user-friendly way. Now, this is done so that way we can store our data in the database in a way that's the best structured, to where we protect our data integrity and it's normalized and separated across tables with the proper relationships and data types and keys and indexes and everything. But when we actually want to present that data, for example, on a web page or in a program, or to the analyzer person who goes and analyzes and does calculations on our data, or just views those calculations after the database does all the work with the analyzation, well, that end result is often in a way, and it looks in a way that is organized and structured. It makes sense to us. That's the purpose of a join. So it takes a mess and puts it out in a way that looks beautiful. And this can be done over multiple tables. So for example, we could have a table here, and a table here. And these could all be three different tables with relationships between the tables. We won't get into any specifics of what kind of tables, but basically a join is going to take all of this and it's going to present us with a generated table that is more pretty, it's more beautiful and more structured, and it makes more sense. Now the way this is done is using foreign key, primary key connections. So when we have these relationships between these tables, where I drew these arrows here, that represents a foreign key connection that references a primary key. So one of these tables is the parent and one of them is the child. And we want the end result to combine them together into one. Now, when you do this, these columns that are connected are going to be indexed to make it much faster. Now, when you join tables, often you will replace names of things with more user-friendly names. So, for example, we could have, let's say we had a comment on a website, and it says, "Wow, lame." And then this is posted by Caleb. Well, you can see that if you have that username here, it might actually be a user ID in a comment table. So for example, we could say, this up here is the comment table, this is the user table, and there's a foreign key from the user ID referencing the user ID in the user table. Well, when we present that data on a database, we will want to replace that user ID with the actual username. So rather than having, we could have it to where it's like user ID of 4,582, and then you're like, oh, I don't really know what that means. Well, since this is all within the comments table, now we're going to take information from the user table and put that username instead of the user ID. That is how a join works conceptually. That's another important thing. All this, think of it conceptually. These videos are going to be helping you understand the concepts of the different kinds of joins. And throughout it, I'll be giving you some examples of how you would type that in SQL maybe, but I'm not going to be getting into the specifics. That's because joins are done differently from database management system to database management system. So what you just need to know is how the joins work and the expected results. And then, when you start working with MySQL or SQL Server or Oracle Database or whatever else, then you can just figure out how to do their joins. You will already know what the results are going to be because you understand the joins, and then you just type it out and boom, you got a join there. Now this is one other thing to know that's important, is all of this is data manipulation. Most of what we've been talking about before is data definition. So that was in basically DDL. But now we're going on to DML. So DDL, data definition language, and data manipulation language. These are two parts of SQL. And we all talked about this in the older videos, but we're on like way farther now, so you guys might have forgot this. But this is important to know, because now we already have the definition, the structure of the database. The database might already be completely designed and structured with the columns and the rows, but now we're manipulating that data to look a certain way. So by doing joins, you're not actually changing the structure of the database. You are changing the presentation of that database. That is extremely important to know. Now you may be wondering, why exactly do I need to know this? Because if I'm a database designer or whatever, really all I need to do is design the structure of the database, and then the database administrator or the software engineer person or whoever can go in there and use my database that I designed and created, and they can do all the data manipulation stuff to fit their application, right? Well, maybe, but not likely. That's because the joins are also very important to understand, because when you design your database, you need to think of it in a user-friendly way and then normalize it, make it confusing, and then present it in a user-friendly way. It's kind of confusing because you start with, let's say you're really bad at database design and you're structuring a table and you have it to where it's like comments, comment table. And within this you have a user name, and then you have the comment and then maybe the blog post or video or whatever. It doesn't really matter. You can have some IDs in there. Basically, you don't know what you're doing, and you put the username. We'll just go with Caleb C. Comment lame. Then we got another one from Caleb C. Cool. And Caleb C. Awesome. When you look at this and you show it to your grandma, she understands it. She's like, okay. She might not understand it, but she gets, if you explain it, she might. Caleb C. posted the comment lame. Caleb C. also posted the comment cool. Caleb also posted the comment, Caleb C. also posted the comment awesome. But this isn't the best way to do this, because we learned about data integrity and also repeating data, because now we have this in here 3 times. So instead we use a user ID, we get rid of Caleb C, and we get rid of the username, we have the user ID, and then in here we have the user ID 6. Let's not use that number. 777. And then over here we have a user table with the user ID column, which has all of our user IDs for each individual person. So we started off with this friendly design, but in reality it doesn't work because it's not normalized, there's repeating data, but it looks pretty. Once we have that, then we can break it up and normalize it, so that way we have multiple tables. So we have this table, and then we have this table over here. But that's not the only thing we do. The next thing we have to do is we have to take up those pieces of the puzzle and put them back together in a join to get the final result. So we basically want to replicate the original table we had here by using a join of our normalized database and recreating it. So what we're going to do is we're going to take the user ID column, and we're going to take the user ID. Can you guys see that all good? It's over there. This will likely also have a username column, so I kind of ran out of room here. But username, and that user ID of 7 will be connected to Caleb C. Using a join, we are going to connect these 2 tables by basically using this foreign key, which points to 7, and finding the associated username with that user ID, and our join will look like this. Username, comment. And the name of the table can be, whatever you want. It could be generated table. Or it doesn't even need a name if you're just putting it on a website or something. And then under the username column, it'll be Caleb C. And then Caleb C. And then Caleb C. And then under the comment, you're going to have lame. And cool. And awesome. But this wasn't just like this to begin with. We got the username from this table, and we got the comment from this table. So not only do you have to design the structure of the database, but you have to structure the joins to basically put our database back into simple language or grandma readable tables. Okay? That's basically what we want to do. So let's say you get a job or you're working for a developer or something, and they say, okay, on my website I want a table on this users page where I can sign in with my username, password, and I can see their username, their password, their email, their date they signed up, and everything like that. And if I want, I can go in there and edit it. That way they don't have to go in and type SQL. You're going to have that programmed in the actual application to send that SQL. But we need to structure the tables. We need to make a join that's going to be able to combine those all to one pretty table, which that's the job of the database designer, likely. I mean, if the applications or the database is huge, you might have someone who does the designing, and then someone who does the implementation, and then someone who does the joins, and then someone who does this other junk. But I mean, if you're just working on your own and you gotta do everything, you're also gonna have to design the joins. And I highly recommend you do that before you go in and programming your application. And then you're like, oh crap, I don't know how to do this, or oh, my database is structured wrong. You want to do this all beforehand. Don't rush into things, because then you're gonna be like, dude, dog, my application ain't working right. And the reason is because you didn't take the time to structure your database the right way and develop your joins. Man. Okay, once you got that, you're good to go. And yeah, so there are a couple different kinds of joins. There's inner joins, outer joins, cross joins, unions. There's all kinds of different things that we're going to be talking about. Okay, so the way an inner join works is it's going to take one table and another table, and then wherever there is rows from this table and this table that are connected, it's going to present them in a new generated table. So let's just break this down and see how it works. Let's go with an example, right? Because you gotta use examples. We're gonna have a customer table, and we're also going to have a card table. So think of like a bank, for example. You're going to have a customer table where you're going to put all your customers in there, and then you have a card table where you're going to put every single card that's been given out or will be given out to people who have credit cards. Or you could make it to where you can even include debit cards in there, but we'll just worry about credit cards for now. So basically, we're going to draw this out, and we're not going to have it required that a card has a customer or a customer has a card. So neither of these columns are going to be labeled as not null. So basically, the card does not need to have a customer, and a customer does not need to have a card. So we'd have one table over here, and another table over here. And generally this would be designed as a one-to-many relationship, because one person can have many cards, and usually one card is owned by one person. You could design it as a many-to-many relationship where you can joint own a card or multiple people can own a card, but you can modify the examples as needed. So let's say this is the customer, and this is the card table. Now we might have something like, of course we're going to have an ID for the customer, so we're going to have the customer ID. You know, their first name, last name, their address, their date of birth, all their personal information that we need for their data for the bank. That's where that's going to go. Over here, we're going to have a card ID, and then we're also going to have a customer ID. And because this is a one-to-many relationship, we have the child and the parent. If this is a one-to-one relationship, we could have it to where there was also a card ID in the customer table if we wanted. But I'm not going to do that. And we can get into one-to-one relationship design best practices in another video. But for now, the customer ID is going to reference this customer ID. And here we can also have more information about the card. We could have the total amount, or the limit, max amount I guess I could say. Max amount. You could have monthly bill. And because this is a really simplified example, we don't really have to worry about other tables such as, you know, bills and invoices, and all that other junk. We're just keeping it simple here. And let's say this is how we structured our database, and we want to make it more user-friendly with a join, to where we join information across the table. Because we don't want to have the customer ID for the card. So we create a join, and we make this new generated table. I don't know why I made that as like circle, but oh well. And within here, we could say it's the card customer. For example, it doesn't really matter what we give the title of the actual table. And what we're going to do in here is we decide which columns we want to take. Well, the first thing, we always start with the ID, because that's how things are going to be joined. And we don't necessarily have to return that ID within our table, but we need to think about it because that's how we connect the tables. So, generally, the ID is just for the database's sake. It's usually not something you use outside of the database. It doesn't have any real-world value, so we usually don't need to record it in the join for a viewed application or whatever we're using this for. Now, if you're the database administrator and you want some more presentable tables like this, but you want to keep the IDs in there, that's fine too. But we're not gonna return the customer ID. There's no need to. It's just a number. But since it's in both tables, if we did join it down here, it would only be in one column. So we would have, customer ID. And that's going to take the combination of these. We're going to have the customer ID, like let's say 62, and then card ID be like 7, and then customer ID 62, and card ID 8. So that's kind of how that would work. But we're not going to return those. So what we're going to do is we're going to return just the first name, last name. And we're also going to return the, let's add another column, amount paid. So basically that's saying like how far they paid off their credit card bill. Let's say you borrowed $10,000 and you owe $6,000 and you've paid back $4,000 so far, just to see how far people are getting to paying off their bills. And like I said, this is a very simplified example. You could make it to where it gives a percentage, and you could have more tables for bills and invoices and all that junk. But just so you guys understand the join concept, it works the same for basically any columns you use. So within here we could have first name, last name, and the amount paid. These are our columns within our table. I'm just going to open this up so we can write some. And we could say that we have individual people. We could say Caleb Curry, and then his amount paid on one of his cards is $2,200. Then we also have Caleb Curry, and the amount paid is $720. And if you wanted, you could go in and edit the join at a max amount. So that's basically, we could have a column on here such as amount owed. And we could have that in here too. And that would basically say how much they paid out of how much. So it'd look like, but then here we could have amount owed, like 3,000. Which is basically saying 2,200 out of 3,000. If you wanted to do that, you could do that, but for simplicity's sake, let's keep it like this. And then we could have Jimmy John, and the amount paid could be 2,800, and so forth. You could make more rows if you wanted. Now you're wondering, okay, what's an inner join? We talked about that earlier. Well, basically an inner join is going to take only the rows that either a card has a customer and a customer has a card, where they intersect. So this new table, this joined table, is going to eliminate any customers that do not have a card, and it's also going to eliminate any cards that do not have a customer. So I'm going to erase this. I'm just going to draw a little illustration to show you how this works. Now, you can find more pictures like this online, which I'll link to in the description if I can remember. Think of it like this. Here is the left table, which was the customer, and here is the card table. And this part in the middle, this is kind of like the join table, or where they intersect. So here are the customers that have a card, and here are the cards that have a customer. So within here, this is going to contain all of the rows that have a customer that also owns a card, or a card that is owned by a customer. So if you have a card with no customer, it'll stay out of the end result, and if you have a customer with no card, it'll stay out of the end result. So this is what you can think of it as. All of these things within this part of the Venn diagram or whatever, that's going to be returned. Now there's different kinds of joins where it will only return, for example, this side or this side, but that's what we're going to be getting in future videos. So if you want to do a left join, or if you want to do a left join and go on here, or a right join and go over here, but an inner join is just the intersection of both of the tables. I don't know. I have this habit of just like wiping it off with my hands, and then my hands are like dark green. So I'm trying to be a little more civilized, you know. So how do you do this? Well, it's done within a select statement, because remember we're using data manipulation language, which is done through selects. So it would be something like this. Now to warn you, the syntax is going to vary a lot from relational database management system from relational database management system. But the concept stays the same, so you just gotta replace a couple things, insert a couple things, boom, bada bang, you got a new join. So we're gonna say select, and then whatever comes after the select, I'm gonna scoot this over some. Everything that comes after the select is going to be the columns that we want in the joined generated table. So in the last example we had first name, and then we also had the last name, and we also had, what was it? Amount paid? I don't remember. But something like that. So that's going to be the columns we want returned. Then we are going to say, what table are we getting these columns from? So we do from, and then we say, okay, well, you may be wondering, well, there's multiple tables, so how do we know which one we're going to use? Well, we're going to put the left one first, which in our drawing we had the user, or the customer, and then we had the card. So we're going to put from customer. And then you're going to do a join, and join the other table to the customer. So we're going to say inner join, and then you're going to say the other table, which was card. Now what you're going to do is say, how are these tables connected? So the way we had them connected, or the way we want to join these tables, is by the foreign key connecting to the primary key. And the way you signify that in the syntax would be with this little statement here. On, which is basically saying, what are we joining it by? And you're going to say customer dot customer ID. And what that dot is basically saying the first part of this is the table. The second part is the column. The reason we have to do that is because both tables have a customer ID. And then you're just going to connect that to the other table by saying equals card dot customer ID. Now, that's basically all you have to do for this. It's going to connect, if you look at the syntax, it's going to connect. Here, let me get a different marker here. Colors makes things so useful, right? I'm going to use black. Okay, we got the customer joined with the card. Those are the tables. And then we're going to say what columns we want to return in the new join. And that's first name, last name, and amount paid. And then we have to say how they're related. That's the customer ID of the customer table is equal to the customer ID of the card table. And that's how you get your joined results. So the end result would of course look like this. And you're going to have first name, last name, and then amount paid. There you go. So that is how an inner join works. The next thing we're going to be talking about is left joins and right joins and all the other cool kinds of joins. Main thing though, don't worry too much about the syntax if it's overwhelming. Just worry about the concept. Understand that if you do an inner join, it's going to exclude all of the rows from either the left or the right table that aren't in both tables. It has to be in both tables in order for it to work. That's the most important thing to understand when it comes to these joins. Because if you understand that, all you got to do literally is look up, let's say you're using MySQL, just look up MySQL syntax inner join. And then you're going to get a little syntax code, replace the columns they gave you with the columns you want, and the tables with the tables that you want. It's really simple, so you don't really need to yeah, obviously you should learn this in the long run, but if you're new to this, don't worry about diving in, studying that for 20 years. Worry about the concepts, because once you get the concepts, it's easier to pick up on this junk. So, this video we'll be discussing inner joins across multiple tables. So, you're probably wondering, okay, what does that mean? Well, when we have a join, we join multiple tables. But what if we want to join that join of multiple tables with more tables? So basically, we're going to have a join over 3 or more tables. I'm trying to find my green marker, I can't find it. There it is. Okay, how does this work? Well, let's just draw some boxes just to kind of get an idea of how this might look. Okay, so you might be like, okay, cool, we figured out inner joins and how those work, but how do they work when you have 3 tables? Let's find out. Here we have 3 tables. And when we do an inner join, let's say in the last example we joined these 2 tables, we had some kind of join condition, which was something like customer ID equals card.customer ID, you know? Well, it doesn't always have to be that, it just depends on what you're doing with it. But basically you're going to have a join condition right here. And you're also going to have a join condition right here if you want to join in another table. These tables don't necessarily have to be connected, like a many-to-many relationship. Because when we designed many-to-many relationships, it looked like this with like the intermediary table. It's not always the case. For example, this table could have a relationship with this table, and this table could have a relationship with this table. But this table doesn't necessarily have to have a relationship with this table. Think of it like this. When you do the join on these 2 tables, you're going to get a result set, right? Then if you want to know what your next results are going to be when you add this table in, think of joining these, and you're going to get a final result set. So if you do an inner join across multiple tables, the end result set is going to be smaller than this. Because you think about it, if you join these 2 tables, you get a result set. But now, you have to take all of these rows, and you're only going to display the ones that meet the requirements of this join condition, which is going to decrease the size or the amount of rows in this table, and it's going to be shorter. Most cases. Now, let's talk about this a little more. Let's go through the example we had before with the cards and the customer, but we're going to add a new table, right? So we're just going to draw this out a little bit. This is the customer table, and we had a customer ID, a first name, last name. You can also have any other junk you want to store about the customer in there. Then we had the card table. We had the card ID, and then the customer ID, and then the max amount or whatever else you want to store about the card, or the bill, or whatever, the price, or the interest rate. Now, let's throw in another table in this equation. Let's throw another table into this equation. It's going to be a card type table. So you know when you get like a credit card, because all you college students are like, yeah, I need pizza. Well, that card has a type, such as Visa, MasterCard, or whatever else, American Express. Well, that's kind of like the card type. Generally, a bank would just give out like one card type, but we could say that they can, like, we could just say what kind of card type the card in this table is. Now, when you structure it that way, how many different card types are there? 4 or 5 main ones: Visa, MasterCard, American Express, maybe 2 other ones that are somewhat popular. There's not that many. So if you were to store that in a column in this one, you're going to get a lot of repeating data. And then, for example, if MasterCard decides to change their name or they get bought out by somebody else, and all the cards now are named UltraCard, then that's going to cause problems, because all of the you're gonna have a MasterCard and then UltraCard. It's going to be confusing. So what you can do is use a lookup table, which we discussed in a long video ago, and that's just going to be basically a reference to another table with all the possible options. And that way, if you needed to add a new option, you can do that easily and then just reference that. Or if you need to update an option, or if you want to put extra information about that option. For example, if MasterCard has a standard fee or something, you could put that within the card type table rather than within the card table. Because if you have the card table, like look, if you have card ID, and then you have card type, and then you have something about that card type, so card type interest or something, well, this is a transitive dependency, which is a violation of the normal forms. I believe second normal form. Did I forget? Third normal form. I'm sorry. Anyways, that's not good, so you'd want to take these and put them in a new table. So a lookup table is a defense against problems like that. And it also reduces integrity problems, and it can also reduce repeating values. So now let's design this. We're going to have a lookup table, which is card type. And this is going to have card type ID, and then the card type, which is going to be like the name of it. And then you could have any other rows about the card type in there. And then in the card, we're going to reference that with a foreign key, so it's just looking it up the values through the lookup table. So we're going to have card type ID. That is a foreign key. Now let's draw these connections. Customer ID is a foreign key to the customer, and the card type ID is a foreign key to the card type. So you can see we have all this information spread out over 3 tables, and we want to join these and create a new generated table that contains information from all 3. We want it to be an inner join in this case, but you can do the same thing with outer joins and other types of joins. We'll be discussing this soon. But for this, we want it to look like this. This is what we want our generated view or our new table to look like. We want to select stuff about the customer. Just gonna add some columns in there just to put them in here. We could have the first name, last name, email, phone, amount paid, and then we could also have the card type right here. Need some more room here. You guys want to know something cool while we're completely off topic, just for a second? I always drew comics as a kid, and I always drew a bubble around either a thought or a talk, and then I try to fit all the words into that, and it never worked. And then my master drawing friend was like, "Dude, draw the words first and then draw the bubble around it." It was the best idea ever, but I still don't do it. I mean, I always have to erase the sides of my database tables to fit more junk in there. I should always write the words first and then draw a square around them. But this will work. These are all from this table. This is from this table. The card type is from this table. It's a join across 3 tables, and you could of course add more. Now, the join conditions, well, it would be, for this, the customer ID is the same as the customer ID, and the card type ID is the same as the card type ID. So this table first is going to exclude, here I'll just write out what it's going to exclude. This isn't part of the table, but I'm just putting it here. It's going to exclude customers with no card, cards with no customers. That's going to be the first join condition because we're going from here. And then the second join condition, it's going to remove cards with no card type and also card types with no cards. And that means basically if you have MasterCard as a card type and you haven't created any card rows that also have the foreign key that references MasterCard or whatever I said, then that's not going to be included because there would be nothing to put with it. And just say MasterCard, no, 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 no. That's because no cards have it and no people have cards that have it. So that's what inner join is going to do. It's going to do all of this. So the end result is going to basically get smaller and smaller and smaller for every single table you add. Now, there's a couple other things to think about here. It has to do with things being null or not null. Okay, let's talk about it. The way we have it set up is the customers, they can have a card, but they don't have to have a card. That's because there's no required column in here that says you have to have a card ID. So you could have a customer that has multiple cards, for example. We also have a card table. And the way we have it set up, the card doesn't necessarily have to have a customer. If you want to change that, you could take this customer ID right here, and you could make it not null. That is going to change the end result, because now every single card is going to have a customer. That means cards with no customers, although functionally it's removing all the cards with no customers, every single card has a customer, so the end result doesn't eliminate cards with no customers. Functionally it does though, because that's what the inner join does, but since there's none to remove, it doesn't do anything. So you can kind of think of it as not doing this, even though functionally it does. Remember that. It's a difference. Alright. Now, we also have it where the card, I would say it should have a card ID, or a card type ID I should say, because almost every card you're going to get ever is going to have a card type, right? Unless for some reason they wouldn't, you'd likely have that as not null. So functionally this is going to remove cards without card types, but since it's labeled as not null, every single card is going to have a card type. Therefore, in the end result, it doesn't really remove cards with no card type, because every card has a card type, so there's nothing to remove. Now, card type, there might be a possibility you're offering a new card type, such as, let's say, I can't think of any cool names, like legit card type 12, and like a new company comes out and you get a legit card type 12 card and all through your new bank account, and that might, when you first get that, there might not be a card that has been issued that card type yet. So in the end result, you're only really removing the customers with no cards, and I guess the card types with no cards, I'm going to keep that, so that's going to stay. So these two are going to be removed, and this is the end result here. We're going to keep card types with no cards and customers with no cards. That was a big one. Man, my throat hurts. We talked about it in the last video, but never actually talked about the join conditions very much. So I'm going to go over a new example in this video. Let's do this. So, we're going to have a user table, not a customer table. User table, and then we're going to have a comment table and a video table. So think of like a video sharing website, like, what's that one called? Starts with a U. I don't know. But anyways, we have a table here. We also have a table here. We also have a table right there. Alright. And these are all connected, right? Boom, boom, boom. I'm just going to write the name of the table. I'm not going to really write any comments in here just because it's low on space. So we got the user, we got the comment, and then we got the video. So the only way the user has any connection with the video is through the comment table, because a user posts a comment on a video. Does that make sense? Hopefully it does. I don't even know why I ask you that still. I'm trying to stop. It's driving me crazy. What are the join conditions for this? If we want to do an inner join, let's discuss the conditions and also the results we should expect. Okay, so let's just define the keys that are going to connect these tables. So we have a user ID, and then we're going to have a comment ID, and then a user ID, and then a video ID, and then this video ID will be referenced in this table by a video ID. Okay, now if you think of this as a many-to-many relationship between the user and the video, you could potentially get rid of the comment ID and just use the combination of user ID and video ID. But that is not the best way to do it. One user could post multiple comments on one video. So, you see, like, if we had this comment table, we could have user ID, and then we could have video ID, and then we could have comment. And we could have the user ID was 7, video ID was 106, and the comment was lame, and then the user ID of 7, video ID of 106 could be JK. So this is a bad idea. You wouldn't want to use those combined unless you were working on some kind of thing where you can only leave like one review on a product, to say instead of just user review product or user review whatever. In that case, you could use user ID combined with the product ID or the video ID to allow that, but I'm going to use the comment ID in this, and this is going to be a surrogate ID that's going to be used as the primary key, and these are only going to be foreign keys. The user ID and the video ID, they're only going to be foreign keys, and they're not going to be part of a compound's a compound key in any sort of way. They're just another column that's a foreign key referencing a table. Just so you guys understand the structure of how I set this up. Alright, now there's going to be a join condition right here, which basically a join condition is what columns are in both tables, right? You don't always have to say user ID equals user ID, or customer ID equals customer ID, or comment equals comment ID. You can do other stuff with like greater than, less than, and all those fancy things, but we're just going to be using equals because it's the most common one and it's the easiest to understand. The one here is going to be the user ID, so we're going to have user.user ID, and it's equal to comment.user ID. This is the first join condition. Now for this, we're going to have a second join condition between these two. And the only thing we can use is the video ID because it's the only thing in both tables. So we're basically going to have a comment.videoid equals video.videoid. We got to say what table they're in because they're in multiple tables. So we have to use the dot syntax. Table dot column equal to table dot column. I know you guys probably can't even read that. I wrote it so small, but it's okay. As long as you understand, this is the join condition for these two, and this is the join condition for these two. When you join these, you're going to join them by those columns. And now what about not null and null columns? What are they going to be returned as? Well, the way we have it structured, a user can comment on as many videos as they want, so they can be in the comment table multiple times. So we got one to many there. Now, a comment can only be posted by one user and can only be posted on one video, because each individual comment is going to be a separate row in the comment table. So for video ID, we're going to have that set to not null. And also for user ID, we're going to have that set to not null. That's because there should never be a comment that doesn't exist on a video, and there should never be a comment on a video that wasn't posted by a user, right? Now for video, we don't necessarily have to have comments on it, so there's nothing we need to worry about that. Just like a user, we don't have to worry about having to have a comment. So the only time we need to put not null is on these two columns to make sure the comments exist with everything they need. You see, the user ID would be not null because every user is a user and every video is a video, but we don't have to say every user has to comment. That would make it impractical. So that's the setup for the not null and the relationship types. So then when we do an inner join, in this case, what are we going to get? Well, I just want to think about that for a little so we can kind of understand what our end result is going to be. So what do we want? Well, we want a table that looks like, now let me move this up a little bit. We want a table that looks like this. And that's because we wouldn't want it any other shape, right? I'm just teasing. But basically, we're going to take the user with the user ID, and likely we'll have more information about them, such as their username. So if you wanted, you could also include that in the table, which would likely be done from the beginning, because you likely do your joins and stuff after that. So make sure you put your username in there. You don't have to add that in there, because then half your users won't have a username and half of them will, which isn't good. So username from the beginning. You'll likely include your username, and then we'll likely include the comment. So we would need to include the actual comment in the comment table. The reason I didn't put these in there earlier, because I just wanted to think about the keys for now, but now we can put those in there, so that, since we're designing this, right? And then we also want the video title, and maybe a link. But we'll just go with the title for now. So these are the three columns that we want to include, and we could have set it up in a table, and each individual row is going to be a new comment. Well, let's think about what can be excluded from this, so then we can decide which ones actually will be excluded. Well, let's just ask questions. Can a user be excluded? Well, if we're using an inner join, we're only going to return users that posted a comment on a video. So yes, any user that did not post a comment will not be included. Now what about videos? Will videos be excluded? Well, since it's an inner join, we're not going to include any videos that do not have a comment from a user. So yes, videos can be excluded. They likely will. So videos, we're just going to put X by to say that it can be excluded. Users can be excluded. Now, can comments be excluded? Well, let's think about each individual key. We have the foreign keys user ID, which is labeled as not null. So that means every single comment is going to have a user, and also the video ID is not null, so every single comment is going to have a video. So in this situation, all of the comments will be returned, so we can't remove those. So within here, every single comment is going to be included. So if we had 10 comments, we're going to have them labeled 1 through 10. We actually want to label them, but we would have all 10 of them there. And then only some users would show up here. And all of their comments, all the comments would show up in this column. So it would be like, it'd be like, and lame. And then the video title, only some videos are going to be included here. Pizza. Subscribe. That's how that's going to work, and let's just see how that goes. So, yeah. Let's see this in action. Here I have some snapshots of some tables I created, and I'll just be illustrating this, and I'll be drawing on the screen as needed. And I have one of them Wacom tablets, and if I am drawing all over the place, it's because I haven't installed the software, not because I can't write better than a kindergartner. Alright, So let's begin. Here we have what would be like a user table or something. We got the user ID, email, username, and the pass, which is like just encrypted basically. And this is going to be joined with the comment table over here. I mean, sorry, that's the video table. Here, let me. This is the comment table. All right, so here we got each comment and foreign keys to the user ID and the video ID, as well as the actual comment. And then we have the video table. The video table has the title of the video and also the description, which would go like under the video or on the side or appended to the title, whatever you want to do for your website. And this is just what the video is about, right? And as you can see, I'm advertising my database design course, which is pretty awesome, right? And what we want to do is we just want to join these, so we have the username, the title, and the comment, all from 3 different tables. So the username comes from the user table right here, and then the title comes from the video title right here, and then finally the comment comes from the comment table right here. So let's go back to the joined table. What we want to do is if we're using, let's say, the comment table, we want to replace the user ID with the username and the video ID with the title. So let's look at the comment table. We want to replace all these numbers in the user ID column with the username, which means we have to reference the user table. And then the video ID we want to replace with the video name, which means we'll have to reference the video table. And then the comment ID, that's just the primary key for this table. Alright, so let's just kind of look at how this works. So yeah, this is how it works. The username from the user table, the title from the video table, and the comment from the comment table. Now let's go through how the join looks. I have all the tables here now. It's kind of small, so sorry if you can't see well. But we have the join table right here. This is the joined table. That's the join. Then we have the comment, the user, and we have the video. And we're going to basically just borrow some columns. So the title, that's going to come from the video. So I'm just going to go over here. It's going to come from over here. And then the username is going to come from up here. And then finally we have the comment. And the comment is going to come from right over here. If you can even see that, probably not. Okay, so there's a couple things though. Not all of the columns values are included, so not every single row. That's because this is an inner join. Now, if you look at the username, we got All Sky Pizza. Let's follow this user. So let's go to the user table. We got All Sky Pizza right there. Then we got, if we keep going down this table, we got Ha 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 12, which of course is use my mouse now, right there. Then we got Pablo is all which is Pablo is awesome. Then we got Milk and Coo, which is milk and cookies. And then we got Yellow Swag Ha, which is yellow swag hashtag. YOLO swag, sorry. And then we got, I don't even know what that says, which is this person right here, best speller in the world. Okay, I made these a while ago, so you can see these two people though, they're not included. That's because it's an inner join and they are not part of the end result. Now let's look at the videos. So we got the videos, we got database design 1, 2, 3, 4, 5, 6, 7. Where's 8 though? I don't see an 8 on here. Well, you can see 8 on the video side right here. It's not included. So 8 is not included. Basically, we're taking different columns from different tables, but not every single row is included. That's because they don't meet the qualifications for the inner join. So the syntax for something like this would be like this. So I have the select and then the username, title, and the comment. These are all from different 3 tables, but it might vary on how it looks for your database management system, but it'll look something like this. And then from the user, comment, and video table, and we just do the inner join the comment by the user ID and the comment user ID, and then the inner join of video by the video ID being the same as the comment video ID. So what's the difference between an inner join and an outer join? That's what we will be discussing in this entire video. It's going to be about 20 videos, so hold it. No, I'm just kidding. It won't take too long. Once you understand what an inner join is, picking up outer joins and the other junk is like super easy. Okay? Kind of how like once you learn one programming language, the second one is only somewhat less hard, right? You can see I have some junk written behind me. Let's look at it. Alright, so we have what's known as a join condition. That is at the end of the join statement. Do you remember doing this? I can't hear you. I'm just kidding. Okay, so we got the customer.customer ID and card.customer ID. That means there's 2 tables, the customer table and the card table. And then both of these have a column customer ID. It's basically just simple dot syntax, the table dot column. And this is making an association. So this is saying that we want to join 2 tables and the rows that need to be connected are connected by the column of customer ID and customer ID. So the 2 columns here, this is going to make a connection, and our join is going to be built upon that, so we know where to connect things. So the way this would work with an inner join, let me just show ya. Let me just redraw those 2 tables real quick. We have the customer, and then we have the card. So this is like a bank, and people can get credit cards, and a person doesn't necessarily have to have a credit card because they can go to that bank without having a credit card. And also, a card doesn't necessarily have to have a current owner, because it could be a disabled card, or it could be a card that hasn't yet been activated, or something else could happen to where a person doesn't own that card. So, there's no required columns for this. Now when we join these, the join table is going to only include customers who own a card. That's going to be the end result. That is with a inner join. So we have the customer, card, join table of card and the customer that is exclusive, pushing away all of the customers with no cards and all of the cards without an associated customer who owns that card. The outer join works a little differently in that it's still going to return all of the rows from one of these tables. You can decide which one, whether or not they have an associated entity on the other side. So that join statement comes in here, it's important. So we had it to where it was the customer ID. I'm just going to put C for short. If we have it where we have it what's known as a left join, I'm just going to write it over here. It's going to basically ignore that statement, and it's going to return all of the rows from the left table. The right one, though, is still going to be obeying that join statement. So the join statement, let me write it out, was a customer. So with this left join, all of the rows are going to ignore this on the left side. So it's going to return back every single row. On the right side, though, it's going to only return the ones that have a customer ID that has a customer ID of the same value within the customer table. So for example, we could have a card with the ID, the customer ID of 7. So that's customer ID, not card ID. So that's referring to the person who actually owns the card. Alright, we could have that person over here. And since if you basically insert this into the join condition, we have 7 equals 7. Because this card customer ID has an equal value in this table, which means this card is owned by that person. It's kind of how it works. But with an outer join, we are going to ignore that and basically say we're going to return all of the rows for either the left or right side. So there are three main classifications of joins, outer joins that are. I'm going to write them all, and then in the next videos we are going to discuss them. There's a left outer join, right outer join, and an... did I seriously write outer join? Ugh, I am so dumb. I meant to write full outer join, excuse me. Oh man. But basically, we're going to be discussing these two right offhand, and full, that can be a little more complicated for some database management systems. So we're going to probably discuss that a little farther down the road, hopefully. Now, the right outer joins work basically the same way as the left outer joins, but instead of the left table, it's going to be the right table that keeps all of the rows. Now, if you don't know what I'm talking about, please watch the last video or two. That's going to solidify your knowledge, and you'll be like ready to tackle this. Because I'm not trying to get you to watch my other videos, I'm trying to teach you something that's a requirement to understand this, and I don't want to have to reteach it all for the sake of one little concept. So let's draw this out a little bit. We have it to where we have two tables, a customer table, and a card table. So this would be like for a bank or something. And let's first see what a left join would do. A left join would take all of these customers, and then it'll take only the cards that have an associated customer and return those. So we'd basically connect the dots. And then we would get a join view, which is going to list all of the customers, but only the cards that have a customer. So it's just going to be like customer, list a card they have. And if they have another card, it's going to list that customer again, list the card they have. And we discussed that in depth in the last video. Well, for a right join, it's going to work the same way, except now it's going to do it for the other table. So we're going to have the same exact setup. We're going to have a customer and a card table. And a card table. Now, if we set it up with a right outer join, it's going to take all of the cards, put them in the join table. So we'll have every single card, and then it will list the associated owner of that card. So, card, and then the customer. Now, there's something to consider with this. If we set it to where within the card table we have customer ID, we give that a column characteristic of not null, that might confuse you a little bit, because then every single card here is going to have an associated customer, which that's the whole point of the right outer join, or the left outer join for that sake, is to include the rows that don't have that association. So if it's set to not null, it's going to return them all anyways, whether you use the right outer join and so forth. You guys understand? Because basically, if we use the right outer join for this, it's going to return them all, but it's going to return them all anyways because every single one has an associated card. We'll discuss that more in the future, don't worry about it. Now there's something else to consider. This basically works the same exact way as the left outer join, except it's switched around. So, when we discussed in the last video how you could say which table was the left, right, where the from, so you have basically the form would be like select, maybe, and then you'd have like the columns first name, last name, and a card amount, or you could have, yeah, card amount, that's good. and then you have something that says like from. Well, the column that you put right here, or the table you put right there, is considered left when we're talking about this design stuff. So, in theory, you could switch it around to where a left join works the same way as a right join. You're just switching the direction of the tables. So, in practice, most people don't even use right joins. I'm only teaching you so you understand when you see one. Instead of using a right join, they'll often use a left join, and then they'll just flip the column, the tables, I'm sorry. So like this. You have your two tables, and I'll give you two possibilities that are going to give the same result. You could have your customer, and then the card, and you can use a right outer join, or you could have it to where you have, over here, you have the card and the customer with the same exact columns and same exact foreign keys. Nothing changed except in design you just switched the things, and when you make the SQL statement you're going to switch the location of the tables within that statement, but overall the function works exactly the same. And now you're going to use a left outer join. These are going to return the same exact thing, because if you do this one, it's going to return all of these rows and the associated columns with those rows. If you do this, it's going to return all of those rows and all the associated columns with those rows. So either way, you're getting all the cards in part of the customers. See? So in practice, a lot of people only use left outer joins for consistency and clarity. So if someone else sees it, they already know it's a left outer join. They don't have to worry about left or right and then draw it out and get all confused. Most people just use left outer joins, but you can always use right outer joins if you really wish. That is up to you. Well, I've been talking a little bit about not null columns, basically columns that aren't allowed to have no value. And that can cause some confusion when it comes to joins, because you might get results you don't expect. And I'm just going to be explaining that just a tiny bit more. This video will be quick, so if you already understand it, go right ahead and skip it if that's what you wish. Alright, so I'm going to be going over an example of a user comment system. So basically you're going to have a table with the users, and then you're going to have something such as a comment table. And you might have a table such as video or blog or whatever you're commenting on, but that's out of the illustration for now. Don't worry about that. Well, in this example, we have some columns that are labeled not null. And what this means is that you're not allowed to have them to where there's no value in that row for that column. So for example, if in comment we had comment ID and then we had user ID and we gave it a column characteristic of not null, well, what is that going to do? That's going to basically say that every single row within this comment table has to have a user ID associated with that comment. And that would be the person who posted that comment. Now, the user, on the other hand, doesn't have to post a comment. It's a one-to-many relationship, and the user does not have to post a comment, but a comment has to be owned by a user. That's important to know. So there's three real possible options of joins that we could do on this table. The first is an inner join. I'm going to put these in caps because it's probably just better to do that. Now the inner join does not matter which one is left or right, because it's going to take the middle of both of them. So the positioning of your tables within your query of the select statement does not really matter. All that matters is that you're using the inner join. What is the inner join going to give you? And the inner join will give you all of the users who have comments. That's because if a user doesn't have a comment, it's not going to be in, his ID won't be in the comment table, and he'll be left out. If there's a comment that doesn't have a user, well then it would be left out too, but that's not the case because it's not null. Right? The other option is a left outer join, and I'm going to go into places in a second. Left outer join, and then we could put the comment on the left. So if you need help thinking about that in your head, switch these two tables around. But I'm not going to do that because that's part of the illustration already. We're good. All right. The other option, well actually let's talk about what that's going to do first. Left outer join is going to give you all of the comments and then give you the associated users who have posted those comments. So every single comment will be included. So the return result will be all comments and associated users. Okay, now think about this though. These things are actually going to give you the same exact thing. That's because if you do an inner join, it's going to give you all the users who have comments. Okay? So it's going to take you all of the users who have a comment, put it in there, and then it's going to take all the comments that have a user and put it in there. You hear that? All the comments that have a user, all the comments that have a user. So these are going to give you the same result. So just understand that. The third option is to flip the left join, the tables that is. So we got a left outer join with the user table on left. Okay, now what is this going to do? It's going to give you all of the users and the associated comments from those users. Now, let's talk about, so we're going to have, it either includes them all or excludes some of them. So basically, if it includes all of the users, I'm going to label it with a star. If it only includes some users, I'm going to label it with an X. Same for the comments. All the comments is going to be a star. Some of the comments is going to be an X. So, users who have comments. Well, only some users are going to post comments, so that's going to be X on the user end. But all of the users who have comments, that's going to include all of the comments because all of the comments are labeled as not null. So every user posted a comment has a row within the comment table. So it's going to return them all. So it's going to return them all on the user end. That's a star. Now left outer join with the comments on left returns all comments and associated users. All the comments, so all the on the comment side, it's going to return them all, but the users, not all of them, just part of them. Now left outer join is going to return all users and associated comments. So the first one is some users, all comments. The second one is some users, all comments. The third one is all users and all comments. That's what you kind of need to do when you're trying to plan out which join you need to use. Go through all the possibilities with that join and just write them out. So you see that these two are actually the same. This one is just a tiny bit different in that it includes all of the users. So you may be wondering, well, which of these two should you use? Well, to be honest, it doesn't really matter. If you wanted to return all of the comments, don't worry about whether it's not null or not. Just use a left outer join with the comments on the left, and then you're guaranteed to have that. You don't have to worry about whether it's not null or not. So that's what I would do. If you only want the users and the comments included, and you don't want to include any comments that don't have a user, which is never going to happen, then you do a inner join. So what you do is you just think and pretend all the columns are nullable, or they don't have to have a value, and then you plan your joins around that, and it can still work the same way if that's what you'd like to do. Otherwise, you can just plan it out like this and realize you can use either one of these, and it's going to work out fine for what you want to do. In this video we will be discussing using outer joins when there are 3 or more tables. We will be discussing the example using 3 tables, but you can basically apply it to any example as long as you understand the concepts. I really recommend that you watch the video about using inner joins when there are 3 or more tables, because the concepts are going to be basically the same except different results will be returned. So for this, the best way to think about it is, let's say we have 3 tables, ignore these two right now. We have a user, comment, and video table. So basically, it's a system where you can comment on videos. Each video that does get a comment will be in this table, and every user that posts a comment will also be in this table connected with that video, right? What I'm going to do is I'm going to use a left outer join on this side and a right outer join on this side. And we will just see what those results are like. Alright, so first thing is first, let's join the user and comment table. That's the best way to think about it, is to imagine these two tables being joined here to make a new temporary joined table, and then imagine this new temporary table being joined with the third table to give a final result joined table. So if we do a left outer join here, every single user is going to be brought down to this table. In the situation of a left outer join, it will only take the comments that have users, because there has to be an association of the user ID in both tables for that. But it's likely that every comment is going to have an associated user, because that user ID column will likely be set to not null. That way you don't have comments that aren't posted by anybody, because that would be weird. So this will also return all comments. Great, now that we have that new table, you see we basically just took everything from up here. Let's imagine taking this and joining it with the videos. And we're going to use a right outer join. So this is going to be right outer join. For a right outer join, we are going to take all of the videos and bring them down here. That's basically how right outer joins work. They will automatically take every single row from the right table. And then we're going to take any row in this table that has an association with the video table. So that means the comments will have to have a video, which all of them will. Alright, so what will be removed here? Well, some of the users will be removed. The reason that is because some of the users aren't going to be in the comment table. And if they're not in the comment table, they can't have an association with the video table. So think about the join statements here. We'll likely have something where it's like user ID over here is equal to the user ID over here, and then we'll have it to where it's then we'll have it to where it's a video ID over here, and that's equal to a video ID over here. So when we grab all of these, we have all the users and all the comments, because all the users will have a user ID, and we don't have to have those users in the comment table because it's a left outer join, which automatically takes all of the users. All of the comments will be returned because every comment will have an associated user. But once we get over here, it gets a little different. Now it's about the video, not the user. So we're going to take all of the comments that have a video ID and all of the videos that have a video ID. Because it's a right outer join, we're going to take all the videos, whether or not they have a video ID, in the comment table. So the first thing, take all the videos. We're also going to take all of the comments, but we're only going to take some users. The reason that is because if a user, let's give some example data. Let's say we have a user over here with the ID of 7, and he doesn't leave a comment, but because we do a left outer join, he comes down here anyway, so now he's in this new generated table. Well, he has a user ID, but does he have a video ID in the comment table to be associated with the video ID in the video table? No, he does not, so he wouldn't make it on past this stage, and he wouldn't be in this final outer table, or this joined table. So the final result is going to be all videos, all comments, and some users. That's just an example of using right and left outer joins when there's 3 tables. You could do the same thing with inner joins. So if you did an inner join, it's only going to take the users who have comments. So, I mean, you can basically apply the same example to a lot of different situations to get the results you want. as long as you understand how a left join works, how a right join works, and how an inner join works, you can get essentially everything you really need to get. The only one we haven't really discussed is the full outer join, which you might need sometimes, and that's a little different, so we'll be talking about that soon. This video will be taking a quick break from joins that we've been discussing for the last 8 or so videos, and we will be discussing something that's a little unrelated, but kind of related, if that makes sense. But anyways, we will be discussing aliases. So an alias is when you rename something and you give it kind of like a nickname or more of a user-friendly name, or a name that you are more used to seeing. And you can do this when you're writing select statements in SQL, and you can do that to either make it easier to write or easier to read. So when you want to give a table an alias, you will use the as or as keyword, and that's going to say anything that follows is what we want to call the table. So let's say we had that user table, and instead of using user, you wanted to say customer. Well then, when you use the table in the rest of the query and you use your joins, rather than using user, you can use customer. And often you won't take a short name and make it into something longer. You will do something like replace user with a U, and then instead of you doing user dot user ID, you would be u dot user ID. That's an example of an alias. When you do it on tables, it's often to make the select statement easier. But you can also do it for columns. Now, when you do it on a column, it's going to work a little differently. So in a select statement, you put all your columns at the top. So here's just an example of what you might say to a database. You're going to select the email, first name, and last name. When you use an alias with columns, not only do you change what the column is called, but it's going to change what it's presented as. So when you get that new structured view, that generated table, and it looks something like this, rather than saying email, first name, or last name, you can make it say email FN, FN, LN for first name, last name. Or you can take out that underscore and you can replace it with, first space name. This works similar in the way that the other alias works for the tables, except you put it right after the column. So you could say select email as contact, comma, first name as, and then you put in quotes. You gotta quote it. That's because you're telling it this is what you want it to be. You want to put it in quotes so that way it's understood to be a string. You can see here I put that space there, and without the quotes that can just cause a problem. Comma, and then underscore last name. You guys see all that? That's basically how an alias works. You can take the alias to make things easier to write, easier to present, and also it can change the way the view looks so it looks more pretty, right? In the next video we're going to be talking about joins that you reference the same table, or a self-join. And basically you're going to take the table you have and basically tell MySQL you want to make a copy of it essentially and join these two tables which are the same. And the only way that's going to work is if you give it an alias. So this table will be called T1 and this one be T2, for example. So that's an example of when you would use an alias other than renaming your columns or your tables. The way a self-join works is you take a table and you are essentially joining it with itself. And that's what kind of makes self-joins confusing, and a lot of people can't find practical purposes for them. I'm going to be giving you... I dropped my marker. I just got white marker. Oh. Self-joins are complicated, and a lot of people can't find practical purposes for them. In this video, I'll be giving you at least one good reason for them, so hopefully this video is helpful. So when you have a self-join, think of basically duplicating the table you have and making an exact copy, and then joining those two tables together. That's a good way you can think about it. So for this example, I'm going to be using a user account system on a website, And you know how some websites have like a referral option? Basically, if you refer somebody, you get like 20% of their money or their points, or 10% of their money, so forth. That's like referral marketing. And when you do that, you are assigned a person who referred you, right? And it can become a chain, like this person referred this person, referred this person, referred this person. So within a user table, you might have a user ID, and then on top of that, you're going to have, email, first name, last name, and the person who referred you. I am putting the person who referred you within a column known as referred by. And this is actually a foreign key to the same table. So within here, you're going to have numbers such as 12, which is going to point back to the user ID of 12. So for example, the user ID 11 might be a person who was referred by the user with the user ID of 12. Now the only way that you can make this really work for a join is if you use a self-join. Basically what we want to do is we want to replace referred by with the ID. We want to use a join to replace this number with that user's email, which I also forgot to put in here. So, just throw an email in there. So we'll take this, and then our outputted result will look something like this. And this is the table that we're going to have, and then we're going to insert data into that table. So we might have a user such as Caleb Curry, and his email is going to be swag@yolo.com. And then it's referred by that we're going to replace that number with a user's email such as hot sauce at yahoo.org. So that's just an example of what we can do with this self-join. Now in order for this to work, we have to tell the database that we're going to be using the same table in basically two different tables. And that can kind of be confusing. And in order for that to work, you have to use what's known as an alias. I talked about those in the last video, so be sure to check those on out. So to begin, we just kind of think of a name of what we could call each table. We could have the first table, which would also be the user table, and then the second table, which would be another copy of the user table. Now we're not actually like copying the data. This is just for illustration point. It's going to use that data, that same table, to withdraw the data from. And we could say this one is V1 and V2, for example. Those are our aliases. And in order to define those, we put as after our data, after our table, and put V1. So we could say user as V1 and then join user as V2. This is something kind of like what you would do. So now we have a user as V1, and then we're joining user as V2. And it kind of gets the idea that, oh, this person wants to use the same table for this situation. Let's try to figure this out. Let's begin. We are going to put this within a select statement. And I'm going to give you some specific syntax just so this can kind of make sense. So we have a select statement. Then right after the select statement, we always put the columns we want to take our data from. Now, this can get kind of confusing though, because we have two different tables that we're going to be taking data from. So we have to think which table we want to take which columns from. The way we had it set up before is we have this table and this table. This was V1 and this was V2. Well, let's kind of, in our imaginary brains, which we don't have, we're going to say this table is for the user and this table is for the referrals. So we're going to take from this table, we'll take the user ID maybe, or the first name, the last name, and the email. And then from this table we are going to take the email of the person who referred you. So we'll take the referred by person's email. So the way this will work is we're going to have the user ID such as 7 and Caleb Curry, and then their email, and then it'll have an ID of 7 or 8 for the referred by, and then that's going to go to the second table to get that person's email. You got to keep this in mind, and you have to figure out what you're going to name your tables before you start to select, because now that we are going to say the columns, we have to qualify those columns by putting a dot before them and saying what table they're from. and we can just use the alias name that we've had or made up. So we could say select v1 period or dot, and we could say first name, comma, and then we could say v1 dot last name, comma, v1 dot email, comma. Finally, we're going to take v2 and we're going to take that person's email, or you can do their first name or last name, whatever you want to put in that referred by thing. If you wanted to say their first name, you can say v2 dot first name. If you want it to be their last name, it can be v2 dot last name. Or if you want a combination of both, you can use a concatenation function or something. So we're just going to use the email. So we're going to take the v2 dot email. Now that we know what columns and what tables that we want to take the data from, we actually have to put the from statement still and say something like from, and then put the table we are taking this data from. This is where we are going to define our alias. So we could say from user as v1. That is going to basically tell the database that the user table is known as v1. Now we can do a join. Join, this is going to default to an inner join if you just use join like that. We could say join user as v2. That is going to basically tell them that user is also going to be known as v2, but it's going to be considered a different table in this situation. Then you're going to do the on, which is going to say where we are going to join these things. Now this is where it can get really confusing because there's so many possibilities that you can put right here. For this situation, we are going to take v1 and we're going to take the referred by column, and that is going to be the same as v2 user ID column. So if you can think about this, imagine literally two tables with the same exact data. Here's v1, here's v2. And we have a user ID, and then within here we also have a referred to by, or referred by, I guess. That's going to reference the user ID of the v2 table. So that means we need to basically make this connection and say that if there is a 6 over here in the referred by table, it needs to be the same as the user ID over here that has 6. If you need more practical data to understand this, imagine we have this guy over here, and his name's Samuel, and we have this guy over here, and his name is, yeah, that's his name, and referred Samuel. That means is going to have the user ID of 6 within this user row of the user ID of, let's say, 12. So Samuel has the ID of 12, and he was referred by the person with the user ID of 6, which is and then this other table, which is also the same user table, it's going to refer to the person with the ID of 6, which is this guy. Hopefully that makes sense. But in reality, you're not going to have two exact copies of the data. It's smart enough to understand that these are all one table, so it's basically going to take that referred by and then go back to the user column and join that into what would look like taking two tables and putting them together. That's why it can get kind of confusing. But when you take this query as it is and you put it in your database, you will get something that looks like a normal joined table. It'll be one really big table, and it will have the columns that we selected, v1.fn. On top of this, we're also going to have the v1 last name and the v1 email and the v2 email. Then if we were to put example data into this, it would look something like Caleb, Curry, an email, and then the v2 email would be like another guy's email, so such as swah@swah.com. That's what it would look like, and it would just give you all of the rows for that. So yeah, you can mess around, do all kinds of cool joins and all kinds of stuff. But there's one more thing that I want to tell you, and that has to do with aliases. Well, you know, this might not be too pretty how you have it right now, and it might be confusing having an email and then right beside it another email. Like, what do those mean? Well, you might want to say that one column is the user and another is the person who referred them. So you can use an alias for that too. So for that you also use as, but instead of putting it in the from, you're just going to put it right after the column that you want to change. So you can put here, 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 and here. So if I wanted the table 2 email, or the person who referred, you could make it say like v2.email as referred by. And this you're going to want to put in quotes to say you want that string as the title for that column. And then when you get that new table, that join, instead of saying email, it's going to say referred by, and then it'll list the data. Yo, what's up my homies? This video, or this section of the video I guess, we'll just be discussing this in a little more depth by showing this real example that I explained on the board. So you can see I have a user table, and within my user table, you know, I got user ID, pass, email, first name, last name, and a referred by. And this referred by is a foreign key referencing the user ID. It's kind of interesting how that works. So you can see here, it was this guy, llamaswag@yolo.com, was referred by to, which in this case would be himom@lololol.com, which he basically referred everybody. That's why he has a 0 here. And if you scroll down, we also have some people who are referred by 1. Basically, what we want to do is we want to replace this referred by with the person's email. And to do that, we can use a self-join. And who knows, there might be a way easier way to do this. So if there is, just be sure to let me know. Alright, so here's a query that would work to do that. So let me just refresh this. And here's what it's going to do. It's going to select the first name, last name, email of the person who was referred. And it's also going to take the email of the referral person, the person who referred the other person. It's a person within this referred by column. Okay, so you can see here we got the first name, last name, email. That's one thing, and then the referred by email. So how does this work? We can take the columns, and we also replaced the email of the referred by and put referred by. That's why it shows up right here, which is what we want. That's good. Then we say what table? We're going to take the user table and call it v1, which you can basically name it whatever, as long as you update right here, then it'll still work. That's just a name I made up. I couldn't think of something cool, but basically version 1, you know. This inner join is we're taking our other version of the table, and just so you know, this inner is optional, so you can take that away and it's going to work exactly the same way. Then we're going to say how it's related. So basically, this referred by email, that needs to have an ID in that table that refers to a person. So the referred by is going to have an ID, and that needs to match a user ID. So within the first table, let's go back to the user table. This to, for example, that needs to reference an actual person. It needs to be actual data within that second version of the user table. And it's going to go to the second version of the user table, find that person with the ID of 2, and it's going to take that email and display it right here. So hopefully that makes sense, guys. And of course you can mess up this query. You can just mess around with it and put your own stuff in it to get your own results. And you can even change this statement right here to get even more crazy results. So yeah, guys, thanks for watching. Peace on Earth, and catch you in the next video, and subscribe. As well as v1.lastname and v... It's a 1, not now, moron! For the aliases of the table, we're going to tell MySQL, crap nuggets. I mean, it's not MySQL's database.